In this video, we'll be going through all of computer science and software engineering in 10 real projects. One project for each field. Everything from AI to VR, desktop to mobile. We'll even go from NFCs and physical security to networks and cybersecurity. And if you're one of the few who make it to the end of this video, I promise you two things. You'll have learned 3 years of computer science without paying hundreds of thousands of dollars per year. Plus, you'll have the skill and experience it takes to be a FANG-level engineer. And I can promise you both, because, well, I've done both.
This is our headquarters. This is Facebook's office. We just moved in here about a couple of months ago.
So again, on screen here are all the projects we'll be completing. Keep in mind, the whole idea of this video is the understanding of computer science knowledge combined with its real-world application in software engineering. We learn a lot of theory in education. Those of you studying computer science will know. But this is very different from the practice of actually building things, working with systems, taking an idea and making it something real. That is the beauty of engineering that I fell in love with, which is starting to become a lost art amongst the dread of poor job markets and existential AI crises. Things like creating a whole new VR world from a meme tweet just because you can, or building a web server you can access from anywhere in the world with this little board we call a Raspberry Pi, getting our hands dirty with APIs, neural networks, the blockchain, and so much more. So okay, that does sound kind of cool, but two questions. One, who am I and why should you listen to me? And two, who is this video for? Let's start with question one. Like I said, I've gone through formal computer science education, and my first real job out of university was at a big FANG company. So I've spent years and years teaching myself, teaching others, and building cool things at all different levels. But if that's not enough for you, I've even gone to the trouble of having every one of these projects in the video reviewed and approved by an industry expert. So you can trust what you're about to see is grounded in real-world expertise. And secondly, who is this video for? Most obviously engineers, especially computing or software engineers. This video is to not get left behind. A reminder that no one ever learnt to ride a bike by reading a book. I've interviewed a lot of people who can recite the time complexity of sorting algorithms backwards while doing a handstand, but they can't tell me how they would build a simple app or how the internet works. You know, real things. So the idea is to take you from this blob of disconnected concepts into a well-rounded engineer capable of connecting different disciplines to build real things. Next, this is for those of you who want to wield magic. And I'm not joking when I say this, it's a very powerful concept, and why I love engineering, it's the closest thing you can get to knowing magic.
When I was young, I didn't really know what I was going to do, but then eventually I thought that the idea of inventing things would be really cool. Technology is indistinguishable from magic. Being able to fly, that's crazy. Having effectively, with the internet, a group mind of sorts, and having access to all the world's information instantly from almost anywhere on the earth. This is stuff that really would be magic, or would be considered magic in times past.
And quick intervention from future Stony to all builders. You may have noticed this video was taken down and some projects in the list are redacted. I intend to share my love for engineering on this platform for many years to come. My intention is never to promote any kind of misuse of technology. With these great magical powers comes great responsibility. So I have made changes, cut things, and re-uploaded this video. But I must stress everything I do is with third-party consent, for educational purposes only. You will not find content that violates terms of service in this video, or anywhere linked externally like on the Patreon. So as I said, some things which cross the line may be cut, but all the core educational principles remain. Okay, public service announcement over, back to our great magical powers. Even after this video, for example, you'll understand how us engineers manipulate invisible waves like Magneto to bend the world to our will, or create whole new worlds in VR, something like Professor Xavier, or for the anime fans in the room, like Itachi's Genjutsus. So for those of you interested in wielding this craft, the power of making something from pure thought, then this is for you. And finally, this is for the curious individual. Maybe you're wondering which subjects to choose at school or university, or maybe you're just a gardener interested in the different fields in software and computer science. Today, you'll be able to see exactly the kind of things we do, which areas you like and which you don't. So for that reason, you don't have to be an expert power level 9000 to watch this video. Everything will be explained and nothing will be assumed. Although it must be said these are 10 real-world projects, not to-do lists or tic-tac-toe beginner basics. So of course, not every line of code and detailed step can be explained in today's video. However, the good news is is, every line of code and detailed step is available on the Patreon. Each of these projects have tutorials with extensive background knowledge sections, a full step-by-step guide on how to complete the project, and of course, all the code so that you can play around with this stuff yourself. So if you think something's not explained in the video, it's probably definitely in the tutorial. And let's take a second to remember why it's so important you build these projects or do anything for yourself. Sure, you can definitely watch through this video and learn a lot, but how long the stuff you learned sticks with you is the real question. Just please trust me on this, doing the real thing is undefeated. So build the projects with me, maybe watch through first, and after you can choose the one you like best. Feel free to make it your own, put it on your CV, or even add new features and sell the project. It's completely up to you, and I've already seen some members from the Patreon Discord do just that. I've also included the entire document script of the video, over 400 pages stuffed with helpful links and images if anyone wants to follow along like a kind of easy to read textbook. So for those of you interested in learning more or just supporting these videos, the Patreon is linked in the description. There's already a lot of great stuff and a lot more planned. Second important mention before we get into things, there's a lot of hardware and custom software used in this video, so I've decided to make a small store over at store.stonycodes.com. This is for those of you interested in following along with the video yourselves without having to look for spare parts on Amazon every half an hour. And again, it helps support these videos. I've stuffed everything used in this video in a hardware kit. I'm talking Raspberry Pi, smart cards, a smart card read and writing device, cables, SD cards, and a whole lot more. I've made a very small batch of these to start as it's a totally new thing for me. And in fact, I've made it even smaller because I've been giving away some of the components to supporters in the Patreon as a thank you. On top of that, I've included my web app template. It's something quite precious to me that I've spent a long time perfecting. It's what I've used in the past, completely separate to this channel, to launch software apps and make my first bit of money online. I was unsure if I would post it because it's like a child to me, but I'm not one to gatekeep, as you can tell from today's video. So that's up there too, and we'll also be using it later. Now let's begin our journey by understanding our place in the universe. I'm a big believer in building out knowledge from the trunk of the tree before branching out. We are over here in the corner, closely related to electrical engineering. You see, computers evolved from electrical engineering when engineers began designing and improving transistors, combining them into logic gates, and packing them into integrated circuits in the 1950s and 60s, creating insanely powerful and ever smaller processors, essentially blocks of computation which laid the foundation for modern computers. And we'll take a deeper look at what all these things are throughout the video. So from that, computer engineering spawned in, focused on combining this hardware with computer science theory to continue to develop physical computers and also software, using these machines for things like networking and early software programs like inventory management, as well as gradually more complex systems like check processing and banking, and as we'll see, all the way to modern day applications like browsers, AI, and gaming. And it has to be said, this little field of computer engineering in the corner here is probably the most influential across all other fields. Civil engineers use simulation software to design their bridges, biomedical engineers use machine learning to build new drugs, and satellites and spaceships use flight control systems. So what we do in our little corner here has an enormous impact across the space of engineering and the world as a whole. So let's take a closer look at our corner and see what's going on. And to be clear, we're now looking at computer science, not computer engineering, so there are some differences. As you can see, a lot more theory, further emphasizing why it's so important to practice real engineering. A quick scan of this image to get some context on the stuff we'll be working on in this video. In the theory area, we have algorithms and data structures. This will be a lot of the leet code kind of stuff from my last video and in the Patreon. We also have some cryptography, the basis of secure communication, allowing us to do pretty much anything sensitive or transactional on networks like the internet, or build blockchains and cryptocurrencies. We have logic gates and hardware, which we mentioned earlier, and related to this, away from pure theory, we have computer engineering chilling over here in the top right. And now we can recognize that this lower level stuff like computer architecture and the cumulative abstractions from hardware all the way to modern programming languages come from their origins in electrical engineering. And using these programming languages, we can build things like operating systems upon which we can build software and different types of applications. So let's see some of the different applications that we can and will be building. We have AI, building deep learning models for image processing processing, and also working with NLP models via the OpenAI API. There's our virtual reality application with our Unity project, and a wealth of software principles throughout each project. We're talking clean code and architectural design patterns, as well as all different kinds of development tools, and just straight up getting things done. We have cybersecurity and access control with our Wi-Fi vulnerability analysis project and our radio frequency identification project, database management through hosting our web app on the Raspberry Pi web server, looking at networks and the cloud in several of the projects also, like the Bitcoin full node, which also deep dives cryptography, or our deep dive into CPU execution and operating systems in our desktop app. A lot for us to get busy with, so I'll cut this next part short. I've written out my version of a more specific software engineering map as opposed to computer science, using a lot of ideas from my personal learning doc on the Patreon, which I regularly update, covering the entire field as I learn new things. But I think it'll be pretty boring for me to sit here and read this out to you. Ultimately, they're all somewhat related, and understanding other fields makes us better engineers. Finally, to keep us motivated, after each project, I'm going to hit a trick shot that hopefully at least one of you finds kind of cool. So here's one from the office to get us started. We're kicking things off by looking at NFC cards and wireless communication. Not the most traditional software project, but just trust me on this, it's the best starting point for understanding computer science foundations and working our way from there. And let me tell you where this one all started. Somewhere far away from computer screens, in the gym. You see, my gym has a keypad for access which requires an 8-digit PIN number. And this 8-digit PIN number followed by an OK key takes on average 3.2 seconds. I go to the gym on average, say 5 times a week. That's 32 seconds a week spent typing my key code in and out the gym, adding up to 27.7 minutes in a year. That's 27.7 minutes I could have spent training in the gym because Git told me I have to resolve my conflicts manually. So I decided I was going to take this into my own hands, quite literally. The gym I go to sells ID tags / key fobs which we can use to tap in and out of the building. Each one of these tags has a unique ID which we can link to our membership account online. So I bought one and tested the time it took for access, 2.1 seconds. Over a year, that totals to 18.2 minutes, saving me 9.5 minutes over the keypad. That's 9.5 minutes that can now be spent in daily stand-up telling everyone I did what I said I'd do yesterday and I'm going to do what I'm supposed to do today. But the ID tag wasn't enough. I know we can do even better. Like Thanos or Frodo, I wanted a ring. A magic ring that could get me in and out, no messing around with my keychain, sub 1 second timing. And that's how this project started. And note, I'm good friends with the gym manager who gave me the okay to do this as an insight into their access system. I will not be showing the data transfer steps here or anywhere else, only the information the access control manufacturer themselves have published. On top of that, keep in mind performing this stuff without consent is illegal. Now back to the project. On the most basic first principles level, we have some data in this tag here that we want to copy onto a ring which we actually don't have yet. But that's our idea. To even begin figuring this out, a good first step is always to gain a bit more context on the problem. And this is what's great about all these projects and one crucial ability I'm aiming to pass on which separates the great engineers from the mediocre. When I first started, I didn't know how to build any of these projects. I had to learn things, break things, fix things, and eventually complete things. University, startup, or big corp, junior or senior, it's all about finding a way to get things done which you may not yet fully understand. And Einstein put it like this, but I like the saying, you're not dumb, you just lack the prerequisites. And it's something I found holds true, particularly at work when I was the noob in the lobby and a senior engineer looked at me with all of his wisdom and said,
"To go fast, go slow we must."
I didn't understand it then, but
I understand it now.
For example, we don't just start by copying the data over, so let's put that back. It'd be a good idea to know how the tag we have even works, maybe what type it is so we can buy the same type of ring, and since I know it must transmit some kind of unique ID related to the gym membership, I know we have to figure out how this data is stored and how we can read it so we can copy it over to the ring. So it's time for a quick physics lesson on how these tags work, starting with the tag reader. The reader sends an alternating current through its antenna antenna oscillating at some specific radio frequency. Let's pause there and break that down. We know an electric current is simply a flow of electric charge through a conductor like a wire. Typically, this charge is carried by electrons. That's common high school knowledge, I hope. Side note, historically, current was thought of as the flow of positive charge from positive to negative, but in modern physics, electron flow is what's used to describe the actual charge movement, the direction the actual particles flow from negative to positive. So don't let that confuse you. An alternating current is just an electric current which reverses this direction back and forth multiple times per second at a constant rate. Both current types generate magnetic fields, literally this invisible force field, directional lines of force that can push or pull other magnetic materials or moving charges nearby with a strength proportional to that of the current. But AC current is good for us in NFC technology because it generates a changing magnetic field around it, back and forth directionally, and we'll see why this is good in a second. But why all these things? Well, that's just the way the universe works. It's a law of physics that currents generate magnetic fields. So we said the card reader sends an alternating current through its antenna. We know the current part, now the antenna. An antenna is just a device. On a physical level, it's some conductive component like a coiled wire, shaped and placed in a way that allows the AC current flowing through it to generate a stronger, more usable magnetic field. And we'll see the purpose of the antenna in NFCs in a second. So we get that an alternating current goes through this antenna, which we said helps propagate the magnetic field. So far so good. But we also said the current is oscillating at some specific radio frequency. Let's understand this final part. The frequency, in general, just means the number of times something happens in a specific time period. In this case, it refers to how often the current changes direction, or oscillates. And because the current is oscillating, the magnetic field it produces also oscillates at the same frequency, constantly expanding and collapsing around the antenna and changing direction in sync with the current changes. We measure frequency in hertz, equal to 1 cycle per second, named after Heinrich Hertz. The wave doesn't need to complete a full cycle within 1 second. The frequency simply tells us how many full cycles occur per second on average, as we can see in the diagram on the bottom right. So a current oscillating 13.56 million times per second will generate a magnetic field also oscillating at 13.56 MHz frequency. This is a commonly used frequency within the radio frequency range, defined as anything between 3 kHz and 300 GHz frequency by the International Telecommunication Union. We'll soon see throughout this video there's a governing body for anything and everything you can imagine. So now we understand each of the individual components of the sentence. The card reader sends an alternating current through its antenna, oscillating at some specific radio frequency. But here's where it all comes together. When a magnetic field changes, as it does here due to the alternating current, it generates an electric field. This is part of Faraday's law, which powers the card reading process. We'll look at it more, but for now, remember the main point. An oscillating magnetic field generates an oscillating electric field. What these fields actually are is good to know, but not the important part. What's important is that this oscillating electric field also generates an oscillating magnetic field. This is Maxwell-Ampere's law. It's not only a current that can generate a magnetic field, but an electric field too. So both these fields are generating each other in some kind of infinite money glitch. The chain reaction is not only self-sustaining, but also pushes the disturbance outwards through space. This was another of Maxwell's key insights. And this outward propagation results in a wave. What type of wave? Well, that depends on the frequency of the alternating current. If we use a 13.56 MHz frequency, we'll get a radio wave. Whether it's our phone, a laptop, or the tag reader, they all abide by the laws of physics to communicate in NFC technology implemented in this way, an alternating current through the antenna oscillating at some specific radio frequency. So all that to say the card reader emits a radio wave. And this is where the tags come in, our near-field communication NFC tags. The tags are made with a small antenna, a long coil of wire, and a tiny chip to carry out some specific functionality and computation. A chip is shorthand for integrated circuit, an electrical component capable of processing information, running code, and storing memory. These chips come in different shapes and sizes in your phones, TVs, credit cards, and gym passes. And this chip on the card is exactly what an embedded system is. Some dedicated computer system made up of the CPU, some memory, maybe a basic OS and interface, just the constrained resources it needs to carry out some specific specific function, embedded as part of a larger device or system, just like our chip in the larger card. The iPhone is another good example. A large system with embedded systems, each serving a purpose. The Face ID system using a specialized infrared camera to process authentication, or even the NFC module to perform tasks like payment processing or tapping into metro barriers. Anyway, back to the card. We explained the wave, and through this radio wave, devices can communicate over long distances. Typically not emitted from a device like a card reader, it needs to be a device designed for long distance. For example, an antenna designed with long-range radio wave communication as the goal. And we'll see how this wave is used to communicate information in a second. But not for the card reader we've been talking about. It does produce a radio wave, but that's a byproduct. Card readers and NFC tech operate via near fields. I mean, it's literally in the name, near field communication. In short, the current through the wire generates the same magnetic and electric fields. Closer to the antenna though, there exist fields that do not propagate, driven primarily by the current, not the infinite money glitch, and they oscillate near field, centimeters around the antenna, still oscillating at some frequency, in this case also radio of course. So to recap, long-range communication via far-field waves, and short-range via electromagnetic near fields. Now back to the card again. As you can tell, these cards have no power source.
Not today!
Instead, in the presence of the card reader's near-field electromagnetic field, the card powers up. More specifically, the card reader's oscillating magnetic field induces an electrical current in the tag's antenna. This is called electromagnetic induction, as described by Faraday's law. And the card's induced current, drawn from the reader, results in a coupling to the same shared near-field electromagnetic field. Here's another example. As you can see, we have a changing magnetic field sweeping through the coil, same as the changing magnetic field caused by the AC current in the card reader. This generates an electric field in the coil, which in turn pushes the naturally free electrons in the wire to move with its electromotive force, resulting in a current, an alternating current. Altogether, we've seen the four Maxwell equations in action, so it will be no surprise to you that these same laws enable the card to communicate back to the reader, since of course the alternating current inside the card will also generate near-field electromagnetic fields which couple back to the reader. And as we said, we can actually communicate information back and forth through these non-material fields. But before the how, what are we communicating? The chip on the card is designed with non-volatile memory to store data without power. When the chip has power, it can access whatever data it needs, like a unique membership ID, and send this data back using the near field. It does this by adjusting the physical properties of the shared field, like its amplitude, the frequency, or the phase. We call this signal modulation. And in fact, this is how most wireless communication works. Long-range, Wi-Fi, Bluetooth, mobile data, satellite communication, or closer near fields for access cards, payment by phone, or even those big anti-theft gates by store entrances. Of course, all using different kinds of signal modulation depending on the use case. For us, the chip on the NFC card most likely carries out amplitude shift keying. Since the amplitude is essentially the peak voltage of the wave, we can control the voltage to change the amplitude. So by slightly varying the voltage of the circuit, like a little floodgate, the card changes the amplitude of the shared near field, allowing us to transmit data. For longer range radio wave communication, a powered transmitter actively modulates the propagating electromagnetic wave that it itself emits back. But now, focusing on short range, the card and the card reader will of course follow the same protocol. For example, defining that, say, anything above an amplitude of 0.5 represents a binary 1, and anything under, say, 0.2 represents a binary 0.
It's not Morse, or if it's binary. Thick is 1, thin is 0.
And at 13.56 MHz frequency, we can transmit a lot of data in the wave or field every second. Or take a look at 5 GHz Wi-Fi, 370 times higher. That's a lot of information we can convey. Since higher frequency means more waves per second to encode information, higher data rates measured in bits, megabytes, or gigabytes, and so on per second. Of course, the actual protocols are a lot more complex than our example, and we'll check these out later, as well as how the binary data we're transmitting transmitting represents useful information. But that's the core mechanics. A genuinely beautiful combination of electrical and computer engineering that powers so much of the modern world with invisible physics. And side note, it's actually a good thing that we can only see a small portion of the electromagnetic spectrum. Otherwise, we'd be blinded by all these waves and activity in the modern world. So to recap, bring card close to reader, physics happens, data gets transferred, and access gets granted. Well, that's great, but what now? Now we know this tag uses radio frequencies and definitely most likely not beaming around deathly gamma rays. Knowing that, we now know we need to buy a reader that can work on the same radio frequency as the tag to see what the data is and also what type of tag it is. But not a regular card reader, of course, a reader for developers. One that allows us to extract the data off the card, or in our case this gem tag / fob thingy, and also write that extracted data onto a ring. Enter the Proxmark, an industry standard tool for radio frequency analysis, a Swiss Army knife for the radio waves. It can read and write on different frequencies for different protocols. This device has it all. And of course, it's available in the hardware kit at store.stonycodes.com along with a bunch of tags and cards for testing and playing around. For now, let's skip the boring setup. There are docs online and again in the compiled Patreon tutorial. It's not too hard. So it's plugged in, tags on the antenna, and if we run the help command using the PM3 client, this is the software we install in the setup that communicates with the device, then we'll see these are the commands available to us. Radio frequency identification devices can be high frequency, like the 13.56 MHz that we mentioned, or lower frequency, like 125 kHz, depending on the use case. We can try a low frequency command, but I'll save you the trouble, nothing will be detected. Instead, let's check out the high frequency commands and run this search one. The Proxmark will cycle through a bunch of NFC protocols to detect a tag. When it finds one, it will output the tag details, letting us know for sure it's a high frequency NFC tag, along with a bunch of information like the tag manufacturer, the specific type of tag it is, the unique ID, the protocol it uses, and a lot more.
Nice.
So we're making progress. This tag is a MyFair Classic 1KCL2, which some quick googling will tell us is a popular identification card used in a lot of access systems using the ISO 1443 protocol, where MyFair refers to a family of card tech owned by the manufacturer NXP Semiconductors. Classic refers to the original first generation MyFair product line, with features like a proprietary Crypto 1 encryption algorithm for authentication, AB key-based access support, a 16-byte memory block, and a few more things which we'll see as we carry on with this project. 1K means the card has a kilobyte of memory, which is actually 1024 bytes to be specific, since of course 1 byte is 8 bits, and CL2 refers to Cascade Level 2, a step in the card reading process. In short, this CL2 means the card has a 7-byte UID instead of the standard 4 bytes, as we've seen in the output of the search command, hence the extra step in the reading process. That's also what this double refers to, even though it's not actually double, but whatever, take it up with NXP. And remember, this is all just a complicated way to define the language we're speaking over these radio waves. It could be English, it could be Morse code, it could be the pitch dogs bark at, but instead we use standardized protocols communicating via signal modulation. So that's the overview of the tag type. Next, let's start by looking at the memory, since the unique ID is probably stored in there. At the very base of things, this 1 kilobyte of memory on the chip is organized into 16 sectors, each containing 4 blocks of 16 bytes. And that's all we need for the card to function, storing both user data and the card's configuration information, capable of storing ones and zeros without any power through the magic of transistors. And we store these ones and zeros in these 16 sectors of 4 blocks, different from linearly addressable memory like RAM, fundamental to general purpose computing, which we've looked at in our data structures video on the Patreon. But if you're unfamiliar, it's just a memory type where you can access locations by unique address directly, like jumping to a page number in a phone book. And we'll touch a lot more on RAM and computer architecture later in Project 5. Instead now, let's focus on the memory arrangement in the MyFair card. In total, we have 2 types of blocks, data blocks and sector blocks. Data blocks are for the organization, like the gym or a company, or you the developer to store some general purpose data data, like the user ID or their access level. There are 3 of these blocks in every sector. Block 0, Block 1, and Block 2 are all data blocks. Sector blocks are the third and final block in each 4-block sector, 0 indexed of course. This block controls who can access the sector using keys and configurable access bits, defining which read and write actions are allowed on each block in that sector. And it's that time again, future Stony intervention time. From here, we're going to speedrun the educational learnings from the rest of this practical, saving the good stuff and removing the cloning steps that could be misused. First, if we check the high frequency commands available to us, we see MF for the MyFair protocol. Here we can run a command like rdcs, read MyFair classic sector, where we can specify a sector and print it out. Each block, all 16 bytes, represented in hexadecimal values, a base 16 number system that uses digits 0 to 9 and letters A to F to represent values, making it a compact way to express binary data in computing. For example, E5 here just means 229, and a lot more on number systems and binary in Project 2. Secondly, there's also the concept of permissions. In this case, which permissions we have to read and write data on the original gem tag. We're talking about authentication and authorization, an important pair of words every developer will continue to come across, especially in big tech, where your team's product or service is always being monitored with new security campaigns and compliance issues. And of course, don't forget the random bots non-stop trying to access your stuff. Whatever it is, there are many different types of authentication and authorization techniques and approaches depending on the project. In our case, we use 2 keys to authenticate a user for each sector. These are the first and last 6 bytes of the sector block and 4 access bytes in the middle to define which operations, read and write, a user is authorized to perform. We could also take a look at these access bits in more detail, how they're arranged in memory, mapping each set of bits to the authorization of one of the remaining 3 blocks in the sector, and which bit value combinations define which type of authorization. But you can read up on that in the tutorial. Because next is another important learning point, how MyFair store the ID in Sector 0, Block 0, also known as the manufacturer block, as well as a look at the card reading process. You see, the manufacturer block is a special block, read-only, unmodifiable, and so the perfect place to put an identification number. On genuine NXP cards, Block 0 is physically write protected all the way down to the silicon chip level, no matter what the access bits say. But that's actually fine though, because we just need to read the ID. It's the ring we'll be writing on, reading either the first 4 or in our case the first 7 bytes as defined by NXP in their own docs. And let's be clear about this. The ID in this block is the card's ID, set by the manufacturer without any input from the gym. These bytes are literally just the serial number on the physical tag itself, the same serial number we link to our gym membership on the gym website. So when we scan our tag, this ID in bytes is transmitted to the scanner by the power of physics and most likely sent to the gym servers on the back end over the internet, where the server maybe converts that UID to a decimal string, checks its database for that ID, finds it's linked to our gym membership ID, and confirms that Stony has paid his fees this month like an upstanding member of the community, letting him in to pump some weights. Although life is never that simple. When we communicate with a card reader, it's not just the UID being communicated. There are several layers of identification and security using configuration bytes in the manufacturer block like the ATCA, a 2-byte value sent by the card during anti-collision, and the SAC, a 1-byte value sent by the card confirming its type and which protocols it follows. We're not going into the full reading process today. It's for sure interesting to see how such minimal data on the card is used in such a complex process, so there's a lot more in the tutorial. The important thing to note, as you can generally see from the tables on the screen, the MyFair protocol gives meaning to the 1s and 0s in memory. It defines which position and combination of binary digits means which characteristics, like which type of card it is and which features it supports. For example, for both ID sizes, the reader initially fetches the first 4 ID bytes. A SAC value of hexadecimal byte 08, according to the MyFair protocol, indicates the ID is complete for both card types. As you can see for our double ID size gym tag, we have hexadecimal byte 88. This tells the reader the ID is not complete yet, and it needs to use the extra CL2 step we mentioned earlier to fetch the rest of the ID. So I'll leave it there for now, because in the next project, we'll dive deeper into more useful protocols that will better help us become well-rounded engineers. Instead now, I want to quickly talk about one other part of the manufacturer block before moving on to the ring. This BCC, block check character value, value that's used during the initial communication. It's nothing crazy, but pretty cool because it's a real-world application of a LeetCode question, one that I actually received in my interview, which you may remember from the last video. You see, the BCC is a checksum, a small piece of data calculated from another piece of data to verify the integrity of the original input. After calculating the checksum value, it's stored in the original data, like our check bytes in the manufacturer block, then verified by recalculation and comparison, for example by the card reader. Checksum functions are a general technique, not necessarily just an addition of the values as the word sum may lead you to believe, although that is one implementation. For example, in our case, the BCC value is calculated by XORing each UID byte to give us the BCC. The term XOR just means exclusive OR, a logical operation used in computing that compares two bits and returns one if they are different. We call these logical operators, and they are in fact the basis of how computers process information at the hardware level. We make logic gates out of transistors and other hardware components, combine logic gates to make circuits like simple adders and ultimately entire processors. And we'll see a lot more of this stuff as we continue. Now back to the BCC on the tag. The BCC is computed by the card's digital logic from the UID bytes and transmitted during the anti-collision exchange. But taking a default 4-byte UID example and plugging this into a BCC calculator, and we get a BCC of 44, which tells us our block is valid. So here's where this gets important. If the card reader received a malformed UID over the air, the BCC of 44 would not match, as we'd get a different result from XORing the ID bytes, so it's a nice safeguard early in the reading process. In fact, on MyFair cards and tags, if this messed up, it can brick the card, since the reader would outright reject it. Finally, the only thing remaining is how to complete the transfer of data onto the ring technology itself, and also how I bricked this ring and recovered it, all done and clutched using the Proxmark. Well, the Proxmark and the council of scholars who roam the quiet channels of obscure pursuits in the halls of Discord. Ultimately though, I'd rather not have my channel sent to the gulag, so I'll leave it there for now and call this Project 1 complete. We've covered a bunch of foundational computer science and engineering, physics and wireless communication, logic and embedded systems, working with low-level byte systems in memory, authentication and authorization. We broke things and fixed them, all while working on a real, practical project, saving ourselves 20 minutes of gym access time that I definitely blew hitting this next trick shot. Let's now take it back to a more traditional software engineering project, building a local web server on this little machine here. Follow along on this one and you'll learn how to take a Raspberry Pi, this general purpose single board computer, turn it into a web server and host a real web application on the internet. We'll be looking at Linux, networking and the internet, Apache, our web server software, Node.js to build our web app, alongside our Postgres database and a lot more. So let's start with the internet. No question, hands down, the greatest invention to date. One giant network connected by millions of cables and wireless signals. Imagine you're in bed at home and you want to access Google, Facebook, or maybe you want to visit zombo.com. You type it in the browser or open an app and your phone talks to the router via Wi-Fi.
Welcome to Zombocom. This is Zombocom. You can do anything at Zombocom. Anything at all.
Wi-Fi uses radio waves to transmit data, which we know all about from the last project. So your phone and router are connected. This is an example of a network. A network is simply a group of connected devices that can communicate. Specifically, this is an example of a local area network, a LAN, which, as the name suggests, is a network within a limited geographical area, like a home or office building, wired, wireless, or both, it doesn't matter. That's why we call those old school gaming gatherings LAN parties. And I hope you've had the pleasure of experiencing one of those. So we tell our router we want google.com. The router goes through a process called DNS resolution, which we'll look at in more detail in Project 10. But for now, we can say it's the process of fetching an IP address from a domain name. Since google.com is the domain name, a human-friendly way to address things on this big internet network the router is connected to, and each domain name maps to an IP address. This is the real, lower-level, machine-readable address of the resource or device we are after on the internet. And each public IP address registered on the internet is unique and refers to a specific device or server connected to the internet network, capable of sending and receiving data by communicating with other devices by their IP addresses. So google.com is actually just a nice way to say 142.250.190.14. And we can literally test this out if we type the IP address in the browser instead of the domain name. We'll still reach google.com. And you can test this out on any browser for any website if you know the IP address. So we get the IP of the domain name during this resolution process, and our browser will cache the result for the next time we request that domain. If it helps, think of the IP like a house address. When I tell my friend to come to my house, I say come to my house. My friends say let's go to Stoney's house. That's the domain name. I don't say come to 123 ABC Street, XYZ Town, 789 EFG every time. That's the IP address. Also, there's a new version of IP going from 4 to 6 since we've run out of unique addresses in 4. But we'll stick with IPv4 in examples for now since it's the most widely used, easier to read, and better supported in everyday networks and home setups. And google.com, this resource we are after, is actually just some files on a computer somewhere. A computer programmed to reply to requests over the internet and serve up resources. So we call it a server. Literally just serving up text files like HTML, CSS, and JavaScript, which when put together for us by our browser, whether it be Chrome, Firefox, or Safari, will work behind the scenes to put together the website we see on our screens. And we'll see exactly what this behind the scenes work is in Project 5. So altogether, that's our highest level starting point on how the internet works for this project. Trust me, we're going to get a lot deeper in this project, and throughout the rest of the video, we're slowly building the pieces. And I think this is a good time to go low level on how networks communicate, these mystical green lines here, and build up a full picture of the scale of everything that goes into visiting a website. So these HTML files on Google's computers are just data. All digital data eventually breaks down to bits, ones and zeros stored in memory made up of components like transistors, different layers of rules stacked on combinations of ones and zeros. Like in our card cloning project, the positions of the ones and zeros in memory defined how the card behaved according to the MyFair protocol or the magic card configuration. We also looked at sending these ones and zeros through the radio wave by changing its properties like the frequency or amplitude. The more bits we can transmit per second through a higher frequency or more advanced signal modulation, the more information we can communicate. To the regular person, this means faster internet. In a wire, like a fiber optic Ethernet cable, it's not radio waves, but pulses of light. On means 1 and off means 0. Again, at insane speeds, gigabits of data being read per second. This can also be electrical pulses in a cable like an older copper wire Ethernet cable or more short range like USB-C. And in fact, it can go over a lot of people's heads, but this image from the learning doc on the Patreon shows it perfectly. The internet at its core is one giant wired connection. The internet backbone it's called. This global network of pipelines made up of an insane amount of these fiber optic cables with light pulsing through them underwater and over land. And we'll take a look at how this all started in another project. For now, let's go back to the router, which has figured out Google's IP address, told the Google server we want the homepage, and received the response back with the HTML file. Of course then, this HTML has been received as ones and zeros via these wires and wireless signals. So the question becomes, what to do with all these ones and zeros? Well, just like our card and card reader, we need rules on how to interpret them, giving the ones and zeros some meaning. And this is where protocols come in, the agreed upon rules that define our communication. This entire stack is the set of all protocols used in the internet network as it evolved over time, agreed, standardized, and improved. And we'll check this out. But first, it's worth noting this stack follows a larger conceptual model in networking we call the OSI model. And we'll build our understanding of this as we continue. But as you can see, the model standardizes how data is transmitted across networks by dividing communication up into 7 useful layers, from physical light pulses to applications at the top of the network, like in the internet's case, web browsers and emailing. Each device responsible for passing the communication on knows how to handle the data according to that layer's protocol, before passing data on up or down the stack. So the question was, what does the router do with the ones and zeros it receives? Well, the router is here on the network layer, and you can see it uses the IP protocol. This is the language the router speaks, and the IP address we mentioned is just part of the IP protocol. That actually pretty conveniently stands for Internet Protocol, defined in this RFC 791 doc you can find online. So the IP protocol also gives us the rules for how data should be transported at this layer, after the more physical layers 1 and 2 too, which we don't really need to worry about. For example, IP divides data up into chunks we call packets. Each packet with an IP header that has a bunch of useful routing information, like the source IP address, where the packet came from, and the destination IP address, where the packet is going. Encapsulated inside that header is the body, or the payload of the IP packet, the actual data we're trying to move around. And let's be clear here about a couple things. First, we're breaking the data up and sending it in many packets, not just one. As you can guess, this is better for reliability and makes it easier to send this data around the network. And we'll see why it's better and how it all gets reassembled soon. And second note, this IP packet is encapsulated inside another packet, or frame as it's better called. This is so it can be transmitted over the physical network medium like Ethernet in the link layer, which has its own protocols. Of course, by the time the router receives the data, the physical network card has already handled reading the frame, stripped it away, and passed on the IP packet to the router's software-based CPU on layer 3. So actually, the router works on multiple layers. The more physical data link layer and the more abstract network layer. That's why we see the router more than once in our OSI model. So in summary, the IP protocol's purpose is to define how packets are addressed and routed across networks, end-to-end delivery between devices using unique IP addresses. And link layer aside, the router operates just on this network layer, designed and manufactured to deal with IP. The router doesn't know what the data inside the payload is. It's incapable of reading it. And so it doesn't care whether the data is a HTML file of Google's homepage, an update to your character's position in a Fortnite lobby, or a Twitter debate over who would win in a war, a trillion lions, or the sun. Let me know what you think in the comments. I'm going with the lions. So for the last time, when the router requests and receives a resource, we now know it's broken down into IP packets, which are just bytes through some physical medium with its own protocol, like signal modulation in radio waves. And the final piece of the puzzle, we now should be able to understand that the router is programmed to interpret these bytes it received through the wire according to the IP protocol. For example, the protocol says bytes 0 to 19 should be the IP header of the packet. The protocol says where the destination IP address is, and the router, through its own mapping, which we'll see in Project 10, knows which device on the LAN the packet maps back to. But before we start looking at forwarding the data to devices on the local network, let's take a step back, because at the point our router figures out the IP address, it doesn't just start firing off data to the server. The router first tells our device the IP address we're after, and we need to initiate a TCP connection. Why, what, and how? First of all, IP is stateless, meaning it cares about delivering things from one place to another, sure, but it doesn't care enough to make any promises or track if anything's been delivered successfully. Packets can take different paths, arrive out of order, and even get lost. We call IP a best effort protocol, designed to try and deliver the packets best it can, but if the packet gets lost, oh well, on to the next one, no guarantees. It's down to the higher layers in the OSI model to handle loss in a way that makes more sense for them. For example, some applications over the network, like live video streaming, they don't care about losing a packet. It's more important to stay in sync with the real-time event using the next packet. But if we're loading a web page, well, we probably do want that lost packet, and we don't mind waiting for it. Otherwise, things will be broken. How we handle this situation is where TCP comes in. TCP, short for Transmission Control Protocol, is the layer just above IP. While IP is all about where things are going, the next layer is about how we talk to that place, the rules for the reliable transport of our data. So that's the why. What this connection is nothing more than a shared state on the two devices, saved locally on both client and server. Working together, we can confirm which data has been received and in what order. You see, TCP, the layer above IP, is also a self-contained packet, or TCP segment it's called, another wrapper inside our Russian doll data block going around the network, again consisting of a header with all the useful transport layer data and the body with data for the upper layers. It includes things like sequence numbers to track the order of the incoming data, so that if the IP packet is out of order, the TCP segment tells us where it should go. ACKs, or acknowledgements, which basically confirm for our shared state which data has been received successfully. Window sizes for flow control. These tell the sender how much data the receiver can currently handle before overflowing, as it continues to process incoming segments. So as you can tell, the receiver/client, for example us requesting a website, we also send segments back to the sender/server, for example the Google server. Even if it's not containing data in the sense of some resource, we're still communicating back important information, like acknowledgements or window sizes, or flags, which in this image should be read downwards, like fin for finished. These indicate actions to keep track of the connection lifecycle. So TCP segments via this shared connection enable a client and server to maintain a reliable connection despite loss or other issues. That's the what. And so quick recap, recap, this image should be making sense. From bits in a physical medium to TCP segment. It's all protocols up and down. Finally, the how. To initialize this pipeline, after figuring out the destination IP address, our browser talks to our device's operating system, a lot more on operating systems later, to initiate the TCP connection request, and our device follows up by sending a series of IP packets carrying TCP segments inside them. These segments make use of the TCP flags like SYN and ACK to complete a three-way handshake, and that initializes the pipeline for the data flow and shared state. So back to our practical example. Browser requests google.com. Router figures out IP address, passes it to device, and browser initiates TCP connection with the destination server. And don't forget, since the router is on the network layer and not the transport layer, it checks the IP address in the packet header and forwards the packet to the device on the private LAN using its internal mapping, which we said we'll look at in Project 10. Of course, since the IP address uses numbers and it's received in binary, it can easily be read by our router. So back to our device. Our phone or laptop or whatever it is receives the IP packets through the network interface card, either wired or in our example wireless, interpreting the Wi-Fi radio waves, making sense of them using the lower level protocols, and passing the data onto the operating system of the device. The networking portion of the OS checks the header of the IP packet for the destination address and says, hey, that's my IP address, no more passing this data around, let's see what's inside. It strips away the header of the IP packet and we've reached the next layer. The OS checks the bytes 20 to 39 after the IP header, where the TCP header starts, the payload/data of our IP packet. Using the TCP protocol, our device knows how to read the segment, which bytes in which positions represent which things, whether it's receiving a flag during the handshake or where the data for the application layer begins. You'll also notice right at the top we have ports. This is a numerical identifier that tells the operating system which application or process on our receiving device the incoming data belongs to. We'll dive into processes a lot more later. For now though, all we need to know is a process is some program or code running on a computer for some specific purpose, like a calculator process or Google Chrome, which as we'll see runs multiple processes. Or it could be something in the background like a Bluetooth manager. Reminder then, the IP address is which device. The TCP port is which program on that device. So the OS strips away the TCP header, updating the shared state, letting the server know it received that segment. This can be part of the initial three-way handshake or after, where the connection has been established and the device OS can start streaming the TCP payloads into the process in the correct order as they come in using the sequence numbers. In our example, this is the browser process. And to be clear about these ports, a bit of common knowledge that will help us later on. Servers listen on well-known standardized ports like port 80 for HTTP traffic, 443 for HTTPS data, or 22 for SSH connections. And we'll cover all these use case processes as we continue. But main point, this standardized approach allows clients to know which destination port to list when connecting to servers. Clients, meanwhile, use OS-assigned temporary ports or ephemeral ports to initiate connections. These ports range from 49,152 to 65,535, as defined by the Internet Assigned Numbers Authority. Remember, we said there's literally a governing body for everything. Yeah, it wasn't a joke. Clients use this range to avoid conflicts, since each port number can only be used by one process at a time, and IANA has already reserved the lower ranges for registered, well-known services typically running on servers. So to put things into perspective, what most people refer to as the internet in common speak is this segment of data using TCP ports 80 and 443 in our tech bro speak. And final note, we've looked at TCP segments, but it could also be UDP datagrams, another transport layer protocol, without the ordering, more applicable to our video streaming applications where we don't care about losing some packets here and there. So we said after the TCP connection is established, we can start streaming the payloads into our browser application. But before that happens, we need to tell the server what we actually want, the website where we started this whole adventure. And that's where HTTP comes in, Hypertext Transfer Protocol, our application layer language that the browser uses to talk to the web server. HTTPS is the secure version of this protocol where data is encrypted using Transport Layer Security, TLS. But we don't need to worry about this for now. The HTTP message includes everything concerning the usage of our data. We're no longer just moving messages around the network. We're talking application now, and HTTPS messages have a familiar structure, a header and a body, of course carried around inside our TCP segments. On screen we have a HTTP request, like that coming from our device, and the HTTP response coming from the web server. The headers of the messages contain a bunch of useful information about the message. For example, the HTTP HTTP request includes the intention of the request message. We call this the HTTP method. For example, back in our journey inside the TCP connection we've just established, because we entered google.com in our browser, we're sending a HTTP GET request to the Google web server asking for the home page. In that case, we don't need to send a body, just the method. Similar to our TCP flags earlier. Usually, when we visit a site in our browser, Google, Facebook, Zombo.com, we're sending a GET request. Then when we carry out some action, like uploading a picture, we're sending a POST request, and we'll include a body containing the image. On the other hand, the header of the response also contains useful information. For example, the status code, a standardized number indicating the result of the request. For example, 200 means OK, whereas numbers in the 500 range usually mean an error on the server side, or the 400 range an error on the client side. For example, 404 requesting a resource that does not exist. We also have the content type in both request and response messages, necessary if we're sending a body. The content type tells the receiver what kind of data is in the HTTP body. So if we're posting our picture to Facebook, we'll put a post method in the header and a content type image/JPEG, letting the web server know how to process the bytes correctly, since this JPEG arrangement of bytes follows a different format from, say, a PNG image or HTML text, or as we'll take a close look in Project 4, MP4 video. And you may have noticed these pieces of information in the header are in plain English, the content type, the method, and more. That's because HTTP is a text-based protocol. When the message is received from the operating system, our application, like the browser, decodes the raw bytes in the header into characters. And we know how because HTTP headers are always in ASCII. ASCII is a character encoding. A character encoding is just a standard to follow that maps numbers to characters. Of course then, we can also use bytes to represent these characters. For example, the number 6501000001, which is 41 in hex, represents the letter A. And since ASCII only defines 128 characters, 0 indexed of course, we only need 7 bits to represent any character, fitting perfectly inside 1 byte, which is 8 bits. I'll take a second to explain this briefly, but there's a great LeetCode question on it from the previous video. Us mere humans use a base 10 system, also known as the decimal system, 10 digits from 0 to 9. Take a second to look at this table in front of you. The way it's presented might seem strange, but after taking it in, the system should be pretty clear. If not, then you may want to message your grade 1 teacher for some help. Binary uses a base 2 system, meaning we only use digits 1 and 0, and we can use this column view to help our understanding. Every time we shift leftwards, we increase the value the number in that column represents by taking the base, which is 2, to the power of the column position, 1, 2, 4, 8. For example, using only one column, we can represent numbers up to the value of 1. We either have a 0 or a 1, where a 1 in this column means 2 to the power 0, which equals 1. With 2 columns, we can represent numbers from 0 to 3, from 00 to 11, where 11 is 2 to the power 1 plus 2 to the power 0, or 2 plus 1, which equals 3. Jumping to 4 digits in binary, or 4 columns, we can represent numbers from 0 to 15, because 1111 is 8 plus 4 plus 2 plus 1, and we can contrast with our base 10 system, where with 2 digits, or 2 columns, we can represent any number from 0 to 99, where the digits 99 mean 9 times 10 to the power 1, which is 90, plus 9 times 10 to the power 0, which is 9, giving us 99. So all that to say yes, we only need 7 bits to represent any ASCII character, or in other words, 1 byte, from 8 zeros to 0, 1, 1, 1, 1, 1, 1, 1. And of course, this is the encoding used on the application layer by applications like browsers to read HTTP headers. So going back to our example, hopefully you can recognize the end-to-end now. That when we sit down at home and type a website into our browser, we send a DNS request forwarded on by our router for the IP address of the site, or more specifically, the IP of the server hosting that website resource, like the Google web server. Router performs the DNS resolution, which we'll see more of later. Then our laptop or phone or whatever device initiates the TCP connection, starting the back and forth handshake with the TCP flags inside IP packets. Inside TCP segments, we also specify the destination port. By default, a HTTP URL will use port 80 and HTTPS port 443. Ports let the server know how to handle the request, what type of data is incoming, which process on the other side it's for. So once the TCP connection is complete, our device can start communicating with the server over HTTP, sending a HTTP GET request, for example, inside a TCP segment, inside an IP packet, inside the data link frame, through wires and waves over the air as binary. The server listens and responds by sending back the requested data in the form of multiple numbered TCP segments. However, we also also have other transport layer protocols that might be used like UDP in applications like Zoom for video calls.
Okay, so hi.
What's up?
Are you, can you please not eat during our interview?
I'm not eating.
Okay.
The server breaks the response into chunks. For example, one packet might contain the start of the HTML, and later packets could contain more HTML, CSS style sheets, JavaScript, or images. Since IP packets can get lost or arrive out of order, the numbered TCP segments help the OS reassemble the data as it comes in the correct order, stripping the TCP header and passing the HTTP messages inside to the browser. The browser decodes the HTTP header bytes using ASCII, sees the content type of text HTML, and this will include another character encoding like UTF-8, which we'll look at in a couple projects later, letting the browser know how to interpret the raw bytes of the HTTP body. Then the browser uses these HTTP messages to build the web page, which again we'll see how this happens in another project. Desktop app project 5 to be specific. So all of that so we can visit zombo.com.
You can do anything at Zombo.com. Anything at all.
So that's us on the client side. On the server side, there is the machine we requested for the website files. Also, of course, capable of sending and receiving messages on the internet, using the same protocols where all the HTTP web responses pretty much boil down to one of these status codes. It all works pretty much the same. So let's say one day you want to put something up on the internet instead of just accessing things. It might be your brand new Y Combinator backed startup, your portfolio site, or maybe your new video vlog.
Here in my garage, just bought this new Lamborghini here.
Whatever that piece of data is, it needs to be publicly accessible on the internet. You could use a web server on a cloud provider like AWS, Google Cloud, or Cloudflare. However, this can get pretty expensive pretty quickly, especially if you forget to put two-factor authentication like me and someone uses your account. Not only that, but you're also at the mercy of the cloud provider. They can kick you off because they feel like it, maybe you're not following some rules, or you're short on your bill for the month. To protect ourselves, and for a bit of fun, we can build our own web server. We don't need 10 infrastructure engineers and funding from Nvidia. We just need this Raspberry Pi 5 with 8 GB of RAM, available in the kit on store.stonycodes.com. So finally, we can get into the project now. Let's speedrun the physical setup, apply the heat shield, connect the cooling fan, HDMI cable to the monitor, but let's not plug the power in just yet. First, let's prepare the operating system of our machine. The Raspberry Pi doesn't have any built-in memory, so it uses an external SD card to store everything from the operating system to any files and applications. This keeps the cost low and the device more open to user configurability. Our Raspberry Pi uses Raspberry Pi OS. To be specific on this, Linux is an operating system, just like Windows or macOS, and there are many different Linux distributions with different aims in mind, and within each distribution we have forks, with even more tailored experiences. Raspberry Pi is a Debian-based fork, although some call it a distribution since it's independently maintained and centered around the Raspberry Pi. The SD card and OS work well together as a lightweight approach. Typically, more intense usage devices like a laptop running 52 Chrome tabs, Spotify, Excel, and FL Studio, all while watching minion edits in the background.
Papoy? Baka na papoy? No. Papoy. Papoy.
Well, that will probably need a bit more muscle, and so we'll rely on a larger RAM for active memory, but also use an SSD for longer term storage, although both are just types of flash memory. And here's a look at all the different types of memory we'll go on to see throughout this video. Remember, volatile just means the data is lost without power, and the name flash just comes from erasing or rewriting entire blocks of data in a flash compared to older memory types. So back to the speedrun, microSD into computer, download the Pi Imager, install the Pi Imager, follow the wizard, safe eject, SD into Pi, power to Pi, make user, connect Wi-Fi, update OS, job done. So our little machine is ready. Just look at him go. Right now he's this little blob of circuitry. No reason in the world, just surviving. Power and no purpose is a dangerous thing. So let's perform some divine intervention and let this poor guy know his place in the world. He is a web server. He will serve up a web application over the internet. And because he is my web server, he will do it from the comfort of my house, not those cold soulless data centers over at the cloud providers. So let's install Apache, open source web server software that can run on several operating systems. We'll run the following Linux command to install it and make sure the program is running with systemctl. So to go back to our technical perspective, at this point Apache is just a process running on the machine talking to the OS, listening by default on TCP port 80 for incoming data, nothing special. And we can check this in the terminal. The only difference between your client device and my web server is this Apache process that's running. Remember, in isolation, no Wi-Fi, no mobile data, both are just single devices not connected to the internet. We can also check if Apache is running by taking the Raspberry Pi's LAN IP address and plugging it into the browser on the Pi. You should get served up the default Apache web page. Basically, what's happening is the browser is talking to the OS to create the TCP connection to this IP on destination port 80 using a randomly assigned ephemeral source port. The OS sees the destination IP and says, "Hey, that's me," looping back the request internally to destination port 80 where the Apache process is listening. After receiving the HTTP GET request, Apache by default responds by serving up a pre-existing HTML file that looks like this. And by the way, this should work from any device in the local home network, since it's the router managing the internal LAN, assigning private IP addresses to devices in a process called DHCP, making the router a DHCP server. So as long as both the device and the Pi are connected to the same router, they should be able to communicate. Cool. So if you could follow all that, I think we are definitely starting to understand the core mechanisms behind how networks work. Also, we can find these ready-made static files that Apache serves up at var www.html. Replace them with our own HTML, CSS, and JavaScript, and we can host our own simple static site for now. We said the router assigns the Pi its IP address. One thing worth knowing is that LAN IPs are not forever. The protocol by which the router assigns IP addresses to connected devices, like we said, is called DHCP, and the D stands for dynamic. Depending on the configuration, this means the router, our DHCP server, might update IP addresses once a day, once a week, or even every time the device, our DHCP client, reconnects to the network. Whatever it is, we want our Raspberry Pi to have a static LAN IP, because in our setup, the router will be our publicly accessible endpoint, so people will be able to enter the router's public IP address in their browser, and the router will forward requests to the Pi on the local area network. Later on, this forwarding approach requires us to manually enter the Pi's IP address, so keeping it fixed is necessary. Again, there's a lot more detail in the tutorials, but the main thing here is we want to find this dhcpcd.conf file on the Pi. This controls how the Pi manages its own DHCP network settings when connecting to a new network. Here, we want to open up this file and plug in the following config. First, we're telling the Pi on the wireless Wi-Fi interface to use a static IP address of 192.168.0.100 with a subnet mask of 24. We have a few more options for the total config in the tutorial, including the choice of the Pi's static IP address. For now, we're just taking the dynamic IP it was already assigned, although there are other options since this could break later down the line, but it's fine for now. And the subnet mask is nothing crazy. It's just a number to specify which part of the address is the shared network part, 192.168.0, and which part identifies the device. For example, for the Pi, this is 100. So this 24 tells the Pi that the first 24 bits of the address belong to the network, and so the Pi now knows which devices are on the LAN and which traffic needs to go to the router. Speaking of which, we also need to tell the Pi the address of the router. So we do that, and we can grab it with a command like ipr grep default. And we can also add the DNS server, which we can grab from resolve.conf. So the next time the Pi boots up, instead of requesting an IP through DHCP, it will assign itself the static IP we configured along with the other manual settings. So let's restart the DHCP client for the settings to take effect. And that's job done on the Pi. Now it's time to tell the router to forward incoming web traffic to this static IP we just set up by doing something called port forwarding. This step should be fairly quick and easy. We just log on to the router's admin page, which we can get from typing the router's local IP address in the URL of our browser. And by the way, you can literally do this in any network you're connected to, in public or at home. Don't forget, you can check the physical router box for the login details. We find the port forwarding page and add a rule like this. There's two examples on screen of different internet service providers. Of course, we set the internal IP to be the Pi's static address. And for now, let's just go with port 80 HTTP without the secure encryption in the interest of time. The HTTPS setup is covered in the tutorial. The protocol is TCP. We know the router forwards the entire IP packet, but when we're port forwarding, we need the router to inspect a little bit deeper into the packet to layer 4, the transport layer. This means it will only forward the specific traffic on the specific port we care about. Of course, better than just blindly forwarding all IP traffic to our device. Okay, so the router can forward TCP data to our Raspberry Pi, whose local address is going to stay the same, running our web server and serving up our image of Michael Scott and the boys playing Fortnite to any incoming GET requests. Oh, and by the way, this is now accessible by anyone, anywhere in the world, since our router is a publicly accessible device registered on the internet. In other words, an internet host. So the router is connected to the wide area network, the internet, and our devices are on the private local area network. Internally, Apache by default listens on 000,080, a special /reserved IP, meaning it accepts connections from any IP address assigned to the server, including the port forwarding connection from the router sending requests to the Pi's internal LAN IP on port 80. So you can type in your router's IP address in the browser from anywhere in the world and enjoy this great image. But no one is going to visit or remember your site with a name like 203.57.146.89. So let's head over to our domain name marketplace like Namecheap or GoDaddy and find a good catchy name that no one has thought of in the last 50 years and is also cheaper than my life savings. We'll grab mySuperAwesomeDomainName.com, add to cart and check out. Inside the settings page for the domain, we can apply a DNS record. This A record stands for address and maps our domain to an IP address. So when people type in mySuperAwesomeDomainName.com in their browser, remember that they perform a DNS query to find the real IP address. Their query will reach Namecheap's DNS servers where we registered our domain. Namecheap will see this A record and replies, mySuperAwesomeDomainName.com points to this IP address, which belongs to our router. So then devices know to send their requests to our router, which forwards connections to our Raspberry Pi. And that's pretty much it. We can now hit our Raspberry Pi web server by typing in the domain name from anywhere in the world. Let's now quickly do some honorable mentions before we get into hosting a more impressive website, all of the following of which we of course go through in the Patreon tutorial. So back on the Pi, we can set up a virtual host in Apache, which is just another config file where we can tell our web server, hey, please redirect any HTTP requests to HTTPS. This is done using a HTTP 301 redirect, telling clients the site has permanently moved to the secure HTTPS version, so please request that site. I'll keep it high level for now. Like we said, the S in HTTPS refers to SSL, which is actually TLS, but anyway, it's a way to secure our HTTP messages over a network, so people can't spy on our passwords and do other evil and mean things to us. To enable this, we can talk to a certificate authority like Let's Encrypt, a trusted organization that issues us an SSL certificate with their special signature. To get this certificate, we go through some under the hood process using, yes, you guessed it, another protocol named ACME, and we basically end up with a file in our server, meaning we are who we say we are and we allow encrypted connections. Honorable mention number 2. For the same reasons routers rotate IP addresses in their LAN, ISPs, the bigger fish that assign routers their IPs, will also rotate the public IP addresses. So we cover some things we can do to fix that also, like contacting our ISP, changing some admin settings, or setting up dynamic DNS, a service that automatically updates your domain name's DNS records to match your changing public IP address. But finally, onto the more important stuff. Let's put something of substance up on our server. This office LAN party picture is cool, but we can do better. There's a little game I made to guess movies based on the Google Maps location. It's not exactly a Series A startup, but it has all the same components of one. It's a Node.js application running on our Raspberry Pi, using a database we also set up locally on the Pi, again keeping us free and independent from the painful bills and awful dashboards over at your local cloud provider. And trust me, we'll deep dive Node.js a lot more later. But for now, just recognize that major applications are not too far off. Netflix, for example, is just a resource on a web server, serving up the HTML homepage to HTTP requests, using a database to store the movies, for example in MP4 file format, with database tables for users making sure they've paid. And like we said, our app has the same components. We serve up HTML files over HTTP, where all the map locations are stored as objects made up of strings and numbers in a database. database, and we make sure only signed up users can play with a table in the database for users. We'll skip over the code because that could be a whole video in itself, but if you're interested, the template I used to build this is available on store.stonycodes.com. I spent a lot of time building this and still update it regularly. It's the template I used to make my first dollar online with a web app, and it's there if you want it. It has sign-ups with email verification, resetting passwords, easy to use payments with Stripe, ready-made components, database integration, hosting, and a full walkthrough document with video tutorials. So instead, let's just get back to setting up this app on the Pi. We can run some Linux commands in the terminal to install PostgreSQL. This is an open source database management system. Basically, just software that acts as an interface for us to create databases and store and manage our data. After installing that, we can run some SQL commands inside the PostgreSQL shell, like this, to create a Postgres user and get the database up and running. Quick breakdown, there are two types of databases. Relational, where we have organized tables or relations connected through keys, and non-relational databases where we don't use tables, but instead a variety of options from documents to key value pairs to graph databases. And those SQL commands we just ran are structured query language, the language used to interact with relational databases. Okay, so finally we can connect the two separate processes, our Node.js app and the PostgreSQL server, by setting a variable in our app which points to the address of our database and provides the user credentials needed to open a connection to the database server. Remember, since PostgreSQL is a database management system, a process that requires actively communicating over networks, for example, so other machines or applications can connect and send queries, it uses the TCP protocol to ensure reliable communication. For us right now, it works over TCP locally. In that case, it will also need a well-known port for clients to know where to connect. So Postgres uses 5432, as assigned by IANA, the Internet Assigned Numbers Authority. The application layer used is PostgreSQL's own binary protocol. Like we said, all just layers of protocols stacked on top of each other. We'll run our Node app on the Pi with a start command, after installing the dependencies and installing the thing that installs the dependencies. This will start our Node app, which listens for incoming HTTP requests on TCP port 3000 by default. I have the data of movie names and location coordinates and all the rest ready in a file inside my code package. To make things easier, I can just fill the database using this file with another command, npx prisma-db seed. We call this seeding the database. So we have our Node app, which is also a type of server, an application server, waiting for HTTP requests locally on port 3000. Our database in the background, managed by our PostgreSQL server, listening for requests from our Node app on port 5432. And we also have our Apache web server listening to incoming HTTP requests on port 80 and HTTPS on 443 from incoming clients, currently serving up our static files. All that's left to do is change this unconnected setup by telling Apache in our virtual host config file we mentioned earlier, hey, forget this old junk of static files, let's instead forward incoming requests to port 3000 on our local machine. This sets up Apache as what's known as a reverse proxy, a fancy word that basically means the server sits in front of one or more backend servers and forwards client requests to them accordingly. Now, when someone visits mySuperAwesomeDomainName.com from anywhere in the world, we know exactly how their ones and zeros travel across the seas and skies to reach our router, how our router alley-oops the request to our Raspberry Pi via port forwarding, and how we've programmed this heap of Raspberry Metal to be able to read the incoming ones and zeros with Apache using protocols from our OSI model, passing the data to our Node app, which talks to the database. Also, you can guess Disney, sci-fi, and fantasy films in my Game Awards Game of the Year. No cloud bills, no middlemen. Here's trick shot 2. So the internet is this big old general purpose network for the transport of all kinds of data. Now let's take a look at another network of sorts, one that rides on top of the internet, Bitcoin. You may think of Bitcoin as the cryptocurrency, but the name also refers to the network and application layer program built to enable one thing, money without gatekeepers. So it's a currency and a network. There's also the blockchain and decentralization. You may have heard of consensus, proof of work. There's also that other one, proof of stake. There's wallets and miners, cryptography and keys. What does all this stuff mean? mean? Let's start with the foundation, the network. Bitcoin is a network. Essentially just tens of thousands of computers running software called Bitcoin Core talking to each other over the internet. The messages travel on top of the standard internet stack we saw earlier, sending TCP IP messages, but instead of HTTP, at the application layer we use the Bitcoin peer-to-peer protocol. These computers running the Bitcoin software we call nodes, using the same internet backbone as before and TCP port 8333, not officially registered with IANA, but defined by the protocol and accepted by the community. Although let's get one thing straight, ISPs like AT&T still own the physical networks, governments still regulate the ISPs, and big tech still dominate the cloud services. These entities can view, throttle, and censor traffic, including Bitcoin traffic, literally if they just pull all the wires out or block the ports Bitcoin uses. Governments in countries like China have done this already by mandating ISPs to censor specific protocols or IP ranges. The key behind Bitcoin's decentralization, however, is that at the application layer, there is no single point of control. Anyone can run a node contributing to the management of this digital money system, and everyone must follow the same protocol. Okay, so that's cool, but what's a node and what's the protocol? Well, we already said, a node is just a computer running Bitcoin Core, and this is the software that executes the Bitcoin peer-to-peer protocol. This protocol handles how the nodes talk, sending and receiving their messages, where the messages are again made up of a header and body, a message transport design that stood the test of time, and these messages transmit information like new transactions to other nodes. If it helps, an easy analogy is to think of Bitcoin Core like the browser. The browser implements the HTTP protocol, our software package implements the peer-to-peer protocol, defining how we communicate with others. Finally, as part of the protocol Bitcoin Core enforces, we have this thing called consensus rules. Strict rules every node must follow, keeping the decentralized money system fair. Things like making sure transactions are valid and nobody is spending coins they don't own. We can loosely think of this in our analogy as the HTML and JavaScript, the application logic. To begin to understand these consensus rules, we must first know what they are talking about. The decentralized digital money system we call Bitcoin. The way that system is implemented is the blockchain.
To keep it as literal as possible, the blockchain is just bytes stored on your node's disk.
It's given meaning because each node in the network agrees using the consensus rules on the correct set of bytes.
And ultimately, this agreed set of bytes tells us the correct state of the money system.
It's a ledger containing the history of all transactions, also showing us who owns how much money, or, in other words, the balances for each address.
Moreover, this set of bytes can be read by anyone.
It's publicly accessible and mutually agreed. That's why it's a distributed ledger. And in our larger computer science picture, we're now in the realm of working with distributed systems. So that's our high-level picture. Let's now pick it apart and we'll see how it's all the same basic computing systems we've seen before, or that you may have heard of, just stacked on top of each other and combined in different ways to make cooler and better things. So to recap, this blockchain that the nodes agree on is somehow used to create and manage a brand new money system. First of all, the bytes, according to the Bitcoin protocol, literally just form a chain of blocks. I mean, it's literally just a singly linked list, a data structure we've seen and practiced many times. Pretty amazing how ubiquitous these seemingly trivial data structures are. Anyway, before LeetCode PTSD sets in, each block looks like this, and we'll go through each of these components in a second. But main point, again, header and body. A bunch of metadata in the header and our payload in the body. Where have we seen that before? But first, just to prove it, we can head over to blockchain.com to take a look at the current state of the Bitcoin blockchain. We can see the latest few blocks in the chain, and we can open any of them up and see the data from the block header plus extra info the website adds. So there's data in the block header and transactions made using Bitcoin the currency in the body, of course made over the Bitcoin network. Common sense then tells us that all the blocks together in the chain record every transaction ever made. That makes the blockchain the distributed ledger of all transactions, and by following the protocol's consensus rules from before, every node can independently verify which is the valid chain and not an attacker abusing the system. This allows nodes to grow the chain with new transactions, safely maintaining the decentralized money system. So we understand Bitcoin as a network by now, and we said transactions use the Bitcoin currency BTC, a digital representation of value. Historically, we've traded items for items, like meat for textiles.
Good sir, give me your meat.
Before moving to medium of exchange items that hold value due to their rarity like gold.
Good friend, give me 10 coins.
And more modernly to government-backed currencies like the dollar, which on a physical level holds close to no value. It's the trust in the issuing authority that keeps it going. Bitcoin somewhat similarly holds no physical value. We know it's just agreed upon data called the blockchain that claims which wallets have how much money. But again, similarly, it's the trust that gives it value. The difference is the trust is not in an authority like the government, but the code. We don't need the big greedy banks who can turn off our accounts or change our balance in their server, no questions asked, and they can understand because at the end of the day, it's just an SQL database. We don't need the Federal Reserve who can just print more money and influence the value, meaning we have less. And we definitely don't need the government telling us who owns what and their say is final. Over here, we've replaced trust in institutions with trust in math and code. It's the rules of global consensus through the peer-to-peer network that upholds the system. If we go one level deeper into the code, Bitcoin doesn't store balances in accounts like a traditional finance database. User balances are determined from UTXOs, unspent transaction outputs. You can think of a UTXO as a chunk of Bitcoin just sitting there, waiting to be used like an old DVD player. Except, unlike an old DVD player, we can use UTXOs in full or split them up for change. I can send one or more of these to you, and they are mine because I have a private key that allows me to prove it. UTXOs and keys may be a level too deep, especially if all you want to do is finish the project, but it's the perfect use case to introduce one of the oldest and most important fields of computer science, blending math and programming, called cryptography. The study and practice of methods for securing information by transforming it in some way so only those authorized have access. This stuff is at the heart of Bitcoin's security and decentralization. Without it, none of which would be possible, including any type of sensitive interaction on the internet. So now we're going to see where the crypto in cryptocurrency comes from.
To enable the trusted transactions on the Bitcoin network, we'll be using public key cryptography, and it's not only used here. Public-private key cryptography is a widely used method to secure communication and verify identities. We've already seen HTTPS, where the server proves its identity with a digital certificate. This is signed with a private key. Remote login with SSH is another example, where only users with authorized private keys can access remote servers, and we'll see this in practice later in this project. Of course, each application implements this public key technique in slightly different ways with different algorithms. Let's take a look at how Bitcoin does it. You have a wallet. A wallet is just a piece of software that helps us carry out transactions. It stores our addresses and keys, like our multiple banking accounts and passwords. It can be an offline cold wallet for maximum safety, or an online hot wallet for better convenience. Inside we have a few things. Like we said, our keys, addresses, and other useful information. Let's focus on these three core components. A private key, literally just a randomly generated 256-bit number. A public key, this is a point on a graph derived from the private key using elliptic curve multiplication. Technical speak for the public key is derived from the private key with some fancy mathematical algorithms. Oh, and it's pretty much impossible to reverse the public key into the private key. Computationally infeasible since it literally requires more time than the age of the universe. And third, we have the address, which is a string derived from the public key. If you're interested in exactly how the address is generated, I've thrown it up on screen, but I wouldn't worry too much about the algorithms and derivations, just understanding that this is our box of stuff and roughly where they will come from. How we use this stuff to engineer secure HTTPS messages, remote SSH login, or trusted Bitcoin transactions is the next question. Hash, sign, verify. 3 steps for secure communication using public key cryptography. The sender has some original data. Generally speaking, this is the message or transaction data, for example, and they hash this message. Hashing is the process of converting some input data into a fixed size output string of characters using some mathematical function. Theoretically, any piece of data can be hashed, from simple strings to 10 GB MP4 movies, since hash functions work on the bit level. And as we well know by now, all these pieces of data are just ones and zeros. So the output of the function is also in bits, and based on the function we're using, we encode the output bytes into characters, which also we know all about by now. The same algorithm and the same input will always produce the same output. This makes hashing deterministic. Aside from verification purposes, as we'll see in a second, a big reason we hash data in public key cryptography is to reduce its size, keeping things consistent and efficient. Smaller data to work with, but just as trustworthy, since changing even one bit of data will completely change the hash. In our example here, we're using the hashing algorithm SHA-256, producing a 256-bit fixed length output from any sized input. And we're doing this by using the SHA-SUM command line tool, and we can immediately see how just by adding a full stop to the input, the output changes completely, making detecting patterns and reverse engineering practically impossible. That takes us to step 2, signing. The sender signs their hash data with their private key using a digital signing algorithm like ECDSA, RSA,
or provide DSA.
In Bitcoin's case, we use ECDSA, creating the digital signature for the data. So to be clear, signing the data with the key produces a unique signature, which put simply is just two large numbers packaged into a byte string that only the private key could have produced, as we'll see in the next step. And again, pretty much any piece of data can be signed, but it's far more efficient to sign the hash. And of course, any data change equals different hash equals different signature completely. This keeps your signature unrepeatable, and you probably wouldn't want to, or even be able to, send the exact same message or transaction twice with the same signature, since any good system would stuff some metadata in the message, like timestamps and unique IDs to keep things secure. So the sender sends over their original message and their signature to the person on the other end. In some systems, like we saw in HTTPS, we'll include a third-party certificate, like from Let's Encrypt, but as you know, we don't need third parties over here in Bitcoin land. Why we need it in HTTPS is another problem for another time, but the details are on screen. So leading us into the final step, the receiver also requires the sender's public key, which they can get in some trustworthy way, and the details of that depend on the application. And now the receiver has their box of stuff: the original message data, the sender's signature, and the sender's public key, which the receiver will use to verify the message. So from the receiver's perspective, we hash the original data using the same algorithm as the sender, which we know since we're following the same protocol like the Bitcoin protocol, which tells us which hashing algorithm to use. Then we, the receiver, use that hashed data along with the public key and the signature in a verification algorithm to confirm whether the signature matches that hash. In Bitcoin's case, we use ECDSA. You can think of the algorithm as having two parts, one to create the signature and one to verify it. Out of the check, we get a boolean, true or false, confirming whether the signature was created by a private key linked to this public key. Of course, since the public key is derived from the private key, again using ECDSA, it's mathematically guaranteed that only the holder of the private key could have produced a signature that verifies successfully with the corresponding public key. Altogether, this builds us a digital signature system using public key cryptography for legitimate and secure transactions on the Bitcoin network. And before we move on, it's important to note the goal of this system is authenticity and integrity. The data moving between participants in the network, like transactions, are not secret. We could encrypt messages using the same tools with public key cryptography, but in Bitcoin, we don't actually care about that. Privacy isn't the goal. In fact, it's the opposite of that. Transparency is a feature, as we'll see later. So the protocol keeps messages in the payload as unencrypted plain text, and anyone on the network can spy on these messages. But we don't care, as long as we have a way to prove transactions are being made by the rightful owner of the coins. And that brings us back to UTXOs, this chunk of unspent Bitcoin, a continual output of transactions that gets passed along. Under the hood, they are just pieces of data, cryptographically locked to a Bitcoin address. Let's see how this plays out when someone tries to spend a UTXO. First, we must recognize that the lock means the UTXO is tied to the address. And remember, an address is just a human-readable encoding of the hash of the public key. So to unlock a UTXO, the spender must do two things: provide a public key that hashes to the same address the UTXO is locked to, basically just confirming the address, which bank account of ours we're using, and two, provide a digital signature of the transaction data, proving the spender controls the private key corresponding to that address. The digital signature can then be verified the same way as before. So that's the sender proving they own the UTXO, like walking into a bank, giving the account number and providing a passport to prove your identity. So to spend this UTXO, our wallet builds a new transaction, writing down the transaction, like the address we're sending our coins to and the amount, signing the transaction with our private key to generate the signature, and including the public key in the transaction so people can verify the transaction. Since we can include multiple UTXOs in a transaction, it can result in higher fees by the nodes that add your transaction to the blockchain, since more UTXOs means more inputs into the transaction and more bytes that need verifying, storing, and sharing across the network. It's like ordering a $5 coffee and handing over a bunch of change. The cashier is going to need a lot more compute to figure out the amounts versus just handing over a crisp $5. But of course, wallets are smart enough to try and include the UTXOs you own which minimize these fees, or other different algorithm choices you may prefer. So back to this transaction. Before it's added to the blockchain, the nodes of the network need to verify it's valid, that the rightful owner is spending these UTXOs and there's been no tampering. Well, just like before, nodes have everything they need. One, they can pull the public key from the transaction and hash it to check the output matches the address address that the UTXO in the transaction is locked to. And 2, they can verify the digital signature of the transaction using the verification algorithm, plugging in the signature, the public key, and the hash of the transaction. If both checks pass, the verification is valid. The old UTXO is marked as spent, basically destroyed, and we get some new ones locked to the recipient's address, plus any leftover change for the sender. And that's how you transact. But here's something cool. Remember, we said Bitcoin is this transparent, decentralized system. In order for that to be true, anyone must be able to set up a node, join the network, and take part. And if they want to, each node can actively participate by validating new transactions before they are added to the chain. In order for that to be true, the set of all UTXOs must be publicly available in the network. So if you know who owns an address, you can see how much Bitcoin they have. For example, we can check the address that received the very first Bitcoin ever from the first block we call the Genesis block, mined by Satoshi Nakamoto, the creator of Bitcoin, who nobody knows who this actually is. It was kind of published under a fake name. We can also check the total distribution of all Bitcoin, and even the addresses with the highest balances. But it's just an address, not a name in a database in some server at a bank with a real-life house address attached. So in my view, it's just as, if not more safe than traditional banking, with the added bonus of the stateless transactions and a scalable design. A design which, as we'll see, offers rewards to nodes for verifying transactions. And that's it really. That's all Bitcoin is under the hood, a cryptographically secured system of digital value and exchange. So back to these nodes, the 20-something thousand hard workers supporting the new money system, sharing the blockchain and updating it with new transactions. These could be businesses, developers, or just regular people who want full independent trust, access to the network, and to provide support. A subset of these nodes are miners. Miners are the nodes who, as part of the Bitcoin protocol, agree in trading their computational effort for rewards. The effort of verifying new transactions and putting them in blocks, and the reward being brand new Bitcoins generated by the protocol, as well as any fees offered up by the senders in the transactions. And for my finance bros out there, here is some monetary economics and policy for you. The supply of new Bitcoin is solely through this reward, and the Bitcoin protocol reduces this reward over time, helping control inflation as the total money supply approaches the limit of 21 million Bitcoin. If new coins constantly flooded the market at the rate of initial block rewards, each coin would be far less valuable today, just like the government printing too much cash in one go. The more there is of something, the less valuable it is. Kinda cool how we're coding up economics. Okay, so we know anyone can set up a node and join this network. This means I could build my own blockchain explorer like we saw before, or some API and sell it as a service. I could host my own personal wallet with Bitcoin Core, I could just run a regular node, or I could be a miner node and collect some new Bitcoin. Valuable digital currency, not Robux, not FIFA points, and not V-Bucks. But spoiler alert, there are massive Russian, US, and Chinese state-backed Bitcoin farms, as well as private-owned, running on insanely expensive purpose-built equipment. And as we'll see, to earn coins, we have to compete with them. In the tutorial on the Patreon, we look at how we can get around this and earn some Bitcoin worth our time, for example, by working in a team with pool mining over the Stratum protocol, the different types of mining software out there, like NiceHash with auto-profit switching features, and the options of running this stuff on CPU, GPU, or dedicated ASIC machines. Today though, we'll just focus on setting up a node and joining the network, taking a closer look at all that goes on under the hood. From that point, all the things we mentioned are possible. So we said a node is just a machine running the Bitcoin protocol, so we need a machine. My Raspberry Pi from the last project is adorable, just look at him go. But to ask him to store the hundreds of gigabytes of the ever-growing blockchain is just not gonna happen. We could run a pruned node which only stores the last few blocks, 550 megabyte hard minimum. That could work on the Pi, but we may want a bit more horsepower to handle downloading and processing the chain, verifying the existing transaction blocks, and potentially mining some new blocks too. So yeah, big tech overlords, forgive me for what I said earlier about your cold and soulless data centers. Maybe they weren't such a bad idea. In AWS, I'm going to launch a remote server using EC2. This will be our Bitcoin node. AWS is a cloud provider, meaning they offer us computing services over the internet, and EC2 is one of those services, offering remote computing. computing. Oh, and guys, for the second time, please remember to use multi-factor authentication. This was definitely not a fun experience. For the availability zone, where we're launching our server, we'll go with anywhere in the US to speed up synchronization with the blockchain, since it seems like there's a substantial number of nodes in that area. And of course, the tutorial covers every option on the setup of this EC2 page, what it means and what's best. So for now, we'll cover the main things, starting with this machine image. Let's go for the latest long-term support Ubuntu server available. Remember, this is a Linux distribution of the Debian fork. It's lightweight and highly customizable, especially when it comes to network settings. There's also a bunch of the required dependencies for Bitcoin Core natively available, which we'll see in a second when setting up Bitcoin Core. When it comes to the instance type, the spec of the machine, there's a bunch of options, and it's just a trade-off you have to decide between cost, performance, and storage. Higher-end instances like the i3 family offer NVMe storage, non-volatile memory express storage, a next-gen SSD with significantly higher read-write speeds, which reduces the blockchain sync time. The 4-core CPU option runs at $0.31 an hour on Linux, while more budget-friendly families like T3 offer lower costs at almost half the price, but of course will perform more slowly. We'll go with a happy medium C5 extra large. We'll also want to generate a new SSH key pair. SSH stands for Secure Shell, and it's the protocol for how we'll securely log into our remote server on the other side of the world. The same public key cryptography system used for verifying Bitcoin transactions. By signing a message with a private key to prove I hold the private key that generates this authorized public key via some mathematical verification algorithm. When prompted, we'll go with ED25519,
a more modern and secure signature algorithm than RSA,
and probably best to stick to a PEM file. This will download your key pair, private and public, so try not to lose it. And for storage, we'll choose 1 terabyte of data to cover the current blockchain size, plus some buffer for the future. And finally, a very important part, the network settings. You can use the default VPC or a custom one as long as it has access to the internet, meaning it has a public IP, of course, so we can communicate with other nodes. AWS servers and other resources live inside VPCs, virtual private clouds. A VPC is your own private virtual network inside AWS's massive infrastructure. Think of it as your own little house in the cloud, separated inside the LAN with software, not physically. And inside this house, our isolated network bubble, we can configure the environment exactly how we like at different layers of the network stack. For example, at the top level of a VPC, we can configure things like the IP range, subnets, routing, and internet access, layer 3 in the OSI model. A basic use case example is one where we define 2 subnetworks in the VPC, blocks of IP address ranges with certain config for that subnet, a public subnet with internet access to host our web server, and a private subnet with no internet route for our internal database. So that's the VPC we're choosing our remote server to live in, with no preference for the subnet. But as you can tell, within each subnet, our rooms in the VPC house, we can place whatever resources we like, storage services, virtual machines, or databases. And here we can also define rules on the resource level using security groups. It's nothing too difficult. Basically, a set of rules we can create and attach to resources. And these rules make up our firewall. Firewalls control network traffic based on things like IP addresses, protocols, and ports. Layers 3 and 4 of our OSI model.
And we'll see a bunch of this in Project 10 looking at cyber attacks.
A common use case example here would be something like a load balancer, distributing traffic between multiple resources while the security group ensures only the right kind of traffic is routed through. We have only 2 rules for our node. First, inbound TCP traffic on port 8333, as we know defined by the Bitcoin peer-to-peer protocol, and this is coming from any IP, letting all other Bitcoin nodes talk to us. And secondly, inbound TCP traffic to the server on port 22. This is so we can SSH in, and it may be a good security measure here to limit this to your own IP. Just don't forget to update it if you're working from somewhere else or using a VPN. That's an hour or 2 of debugging in 1 sentence for you. So we'll select this security group we just made, and to be honest, that's kind of it for the setup. Maybe a few little extra things here and there. All that's left to do now is wait for this machine to boot up. Our server is ready to go. We can use our private key to SSH into the instance in our terminal. The public IP of the instance we can find in the AWS console. On first connection to the server, you, the SSH client, will be prompted to accept the server's public key. In other words, its fingerprint. Earlier, we showed how the client proves their identity to the server using public key cryptography. Well, the server does the same. On first connection, we store the server's public key. Then, whenever we, the client, want to connect, we also challenge the server to sign some data we provide so the server can prove it controls the private key corresponding to this public key, protecting us the client from middleman attacks as we can now detect any changes to this key. Although yes, the very first time we connect, we have no way to be sure we're really talking to the server. It's called trust on first use, TOFU. We could find ways around this, but it's okay for now. Also, if you see a bad permissions error like this, it just means your key file is too open and SSH wants it to be only readable by your user on your computer, which is exactly what this chmod 400 command will do. After that, we should be okay to connect. And this is where the use case of public key cryptography in SSH and Bitcoin differs. In Bitcoin, we only prove our identity as UTXO owners by signing transactions. The receiver on the other end is not a concern. There is no ongoing trust relationship. However, in SSH, both parties must prove themselves and maintain that trust over time. So enough talking, we're logged in, let's update the machine. Next up is to prepare this remote machine in Amazon's warehouse to become a proper node by installing Bitcoin Core. Usually installations are boring. We just click a few buttons and follow a wizard. In this case though, we are building from source. This means we will be compiling the source code ourselves into executable binary files on the machine, and compilation is just the name of this process, of translating human-readable source code into low-level machine instructions that the CPU is able to execute. And we'll see a lot more of this throughout the rest of the video. We could just use the precompiled binaries the Bitcoin organization provides on their website, but the GitHub repo is usually further ahead with more recent updates, plus it's a good manual learning experience, and you shouldn't be surprised. Remember, we said nodes on the Bitcoin network just run the Bitcoin protocol, which is done through this software called Bitcoin Core, which anyone can run. Well, it's just code, so of course we can just go on GitHub and find it, check what people are contributing and the latest versions of the code. The Bitcoin Core repo has the installation instructions for all different OSs. First, as always, we want to install the dependencies. Linux is a Unix-like operating system, so we'll follow that. They tell us what dependencies are required to run Bitcoin Core and give us the commands to install these packages. For example, one of the dependencies is either one of these compilers, responsible for parsing the source code, processing the files, and analyzing its semantics and generating the binary code for the CPU to execute. We'll look at this process step by step in another project. So let's run the code to install these dependencies. And here's a quick overview of what everything does for those of you who are curious. By the way, you can use apt-get or apt-install on Linux. It doesn't really matter, just whatever you're used to. Cool, so after that, we want a new folder, mkdir, make directory, and we'll cd in, change directory, and clone the Bitcoin Core repo. This repo contains all the source code for the protocol, from peer-to-peer communication logic to transaction validation, block mining, and address generation. As we can see inside the source folder, inside consensus, there's a file named tx_check.cpp. CPP is the file extension for C++ code files, and here's the function named checkTransaction, which returns a boolean, where the code begins by making sure the transaction has at least one input and one output. vin being the UTXOs the spender is spending, and vout referring to the new UTXOs to be created and locked to the recipient's address. And as we mentioned, this code will be compiled to binary and executed by the node. So let's navigate into the Bitcoin repo we just cloned, and from here we can start the build process, source code to object files to executable. First, we run cmake bbuild, and we'll add these flags since we're just building without the wallet or GUI in the video today. Cmake is just a tool to help manage the build process of software. Here we're telling it to generate the build system files in a folder called build, and we can see this successfully at the end of the output. The build system files it generates are just instructions that tell a build tool how to compile. For example, which files to compile and which compiler to use. Follow that up with cmake build, and we can add this extra jnproc flag to speed things up. The command reads those build system instructions and performs the actual compilation of Bitcoin Core source code into a binary executable program. And finally, we can run sudo cmake install build, which installs the compiled Bitcoin Core program onto the system, copying the executable and any necessary files into standard system directories like user local bin, so the program can be called and run from anywhere on the system. As we can see by the purpose of this bin folder in the table showing some standard Linux directories, and that's all it means to install something. After compilation, to take those binaries and place them in the right directories, and maybe setting up some config, like environment variables we saw in the last project. And note, we will have to use sudo at the start of the command to gain the necessary permissions when installing in a system-wide directory like user local bin. Sudo is super user do, giving us the highest level of privileges on Linux. At this point, we can check the Bitcoin Core program program has built and installed successfully by running bitcoind-version. Bitcoind is the actual program that will run the full node and interact with the network to sync with the blockchain. Bitcoin CLI is the command line tool we use to interact with a running Bitcoind program, another client and server model, sending commands and receiving responses. And we'll check these out in a second, but first, quick recap before we begin configuring the program on our node. 3 commands. First, we ran cmake bbuild, which generates the build instruction files in the build directory depending on your machine's environment, like which compiler you're using. Then we ran cmake build, which reads the instructions and compiles the source code, like the transaction check C++ file we just saw, into an executable binary. And finally, sudo cmake install build, which copies those binaries into standard system directories, making the programs easily callable from anywhere on the computer. Like we showed when checking the version of Bitcoind, we don't have to be in the same folder as the program binaries. Before running anything, a couple of settings to tweak. And by the way, if you shut down your instance for the night and come back later, the public IP can change. So there's another hour or 2 of debugging for you. There's a configuration file called bitcoin.conf, where there's a lot of different things we can do to change the node's behavior. We'll use this nano command with the file path to open the file inside the terminal. Here we can set up a remote procedure call interface for easy access. We can enable pruning for a pruned node, enable transaction indexing, and the list goes on. Let's just slap daemon equals 1 in there. Bitcoind means Bitcoin daemon. A daemon is just a computer program that runs as a background process. Here's a few other examples. Running things in background mode is a big help when it comes to developing software and working with remote servers. This means the program is not tied to the session in the terminal, where quitting or temporarily losing connection would end the program. Session managers like tmux or screen are also pretty useful tools too, letting us run sessions we can attach, detach, and reattach to. We cover more config options in the Patreon tutorial, but daemon 1 is enough to get us started, so we'll write out and exit. Finally, last bit of config is we want to make sure our node is accepting incoming connections at the operating system level, as well as the EC2 network level we configured in the security group. And Linux makes this real easy for us. We can just run sudo ufw allow 8333/tcp, adding a firewall rule to open up the port. So at last, this young EC2 machine has graduated into the field of Bitcoin. He has all the knowledge ready to get out into the real world, enter his network, and start talking to his colleagues. Blockchain synchronization. To run a full node, by definition, we of course need to download the full entire history of the blockchain, a timely, resource-intensive process that also includes validating each block according to the consensus rules, of which there are over 900,000 blocks. To kick the process off, let's run Bitcoind, which will do its stuff in the background. The node begins by connecting to peers on the network. Bitcoin Core randomly selects peers from a diverse global pool of decentralized nodes, discovered in different ways. DNS seeds hard-coded into Bitcoin Core, previously known peers, or even manual adds. This global selection ensures your node isn't isolated to nearby potentially evil peers, protecting against geographical attacks. The first step, which we saw running, is to download and verify all the block headers. This is the first part of the initial block download. Since headers are only 80 bytes each, it's a lightweight approach for our node to identify the best chain before downloading the block data, which is up to 4 megabytes each. After the headers are mapped out, our node begins downloading the block data, the transactions, verifying the signatures, and updating the tip of our blockchain. But how does the node know the right chain? There very well could be some evil nodes propagating a fraudulent chain where their address has 500 Bitcoin, but in reality they very well don't. Or nodes may have naturally misaligned at some point, causing a fork in the blockchain, and it would be too much to ask our node to talk to all 20-something thousand other nodes in real time to check the most common chain. So this is where consensus kicks in. Remember, Bitcoin is designed for a world where anyone can run a node, and anyone includes bad actors. So the system needs a way for honest nodes to agree on the correct chain. The rule is, the correct chain is the valid chain with the most cumulative proof of work. What does this mean? Well, each block contains a proof of work, a cryptographic receipt proving that real computational effort was spent to create this block. Remember, this is a job for the miners mining new blocks. They agreed to trade computation for Bitcoin rewards. To add new blocks to the chain, miners collect a bunch of pending transactions from a local pool called the mempool, a node's holding area for valid and pending transactions. They can check which ones offer the best fees, package them up into a new block we call the candidate block, and get to work on a mathematical puzzle puzzle that looks like this. It's a calculation where we're hashing a bunch of data. Remember, anything can be hashed. In this case, the input data is everything the new candidate block will have in the header. A bunch of metadata like the current timestamp, the version number of the current set of the consensus rules, and the hash of the entire previous block header. We also have the hash of all the new transactions, called the Merkle root. And the last two, which we'll explain now, are the n bits, which encodes the current difficulty target, and the nonce, a random number short for number used once. You see, the goal of the puzzle is to find an output hash value that is less than or equal to the target. This difficulty target is a 256-bit value set by the Bitcoin protocol, or 64 hex values as we're showing, since each hex value is 4 bits. So with all these inputs, miners repeatedly change the nonce and rehash the block header, trying to find an output hash value that is less than the current difficulty target by changing the nonce. We know SHA-256 outputs a 256-bit value, and of course, based on the nature of hashing algorithms, there is no way to predict or find a pattern in the nonce that gets us closer to the target. Even if we were to try and reverse engineer the algorithm, sorry, there's just no chance. Essentially, that makes this a trial and error process, an insanely fast brute force one. The number of attempts we can make per second is called the hash rate. More computing power, higher hash rate, greater chances, more rewards, more money, more Lamborghinis. Things started off with a relative difficulty score of 1, now in the hundreds of trillions. So you can see just how much more computational power is needed today to mine a single block, and why we've moved from homemade CPU setups to farms with dedicated ASIC mining machines. And final comment on the puzzle is what causes the difficulty to change. It adjusts roughly every 2 weeks to ensure that new blocks are mined around every 10 minutes. Naturally, as more miners enter the network, the difficulty goes up. The first to get a hash less than or equal to the target broadcasts their new block to the network, and other nodes verify its validity by checking both the puzzle solution and all transactions inside. This is one type of consensus mechanism, a way to agree and update the state of the blockchain ledger without a central authority. Another popular example is proof of stake, used in Ethereum, where the more currency you stake, the greater your chance of being selected to add the next block and gain a reward. Again, we're not doing this for fun. It takes real electricity and hardware to solve this puzzle, and this makes it costly to cheat. We're not just spinning up bot accounts to lowball on Facebook Marketplace. And this takes us back to the point of attackers. To propagate a fake chain where, for example, I did not send you coins in the past, as an attacker, I would have to outpace the honest network, creating a chain with more cumulative proof of work without my transaction in order for it to be accepted. Because remember our golden rule, the correct chain is the valid chain with the most cumulative proof of work. And to outpace the honest chain with fake blocks, I'd need to mine and add them faster than the rest of the network combined, which means at least 50% of the total mining power. This is an insane amount of compute, infeasible for any attacker or even world power to begin to attempt, as we can see in this table where the total network is around 900 exahashes per second. And so that's why there's this trade between computational power and rewards, enabling proof of work and securing the blockchain. So now we know why when our node first connects to peers, it asks around for the block headers and then follows the longest chain with the most proof of work, downloading each block following the consensus rules to ensure its validity. And we also know this works because rules are hard-coded into Bitcoin Core, giving us an objective truth. No voting, overruling authority, or subjectively interpretable rules like governmental laws. And that's all the logic behind what our node is getting up to right now. We can check the current synchronization status by running Bitcoin CLI get blockchain info, showing us the number of blocks we've validated so far, the hash of the most recent validated block, the compact encoding of the difficulty target of that block, this was our n bits input in the proof of work challenge, as well as the actual difficulty target in hex and the relative score. And we can continue to watch the logs in real time by tailing bitcoin.debug.log. So we give it some time to synchronize, our node will go through the initial block download process and check headers, move on to the blocks and verify transactions before finally reaching the tip where it becomes a full node. At that point, our node will continue to validate new blocks, looking at the UTXO set, adding to this pool of pending transactions, sharing the blockchain with peers, propagating new blocks, and all the rest of that good stuff. We could also transition into mining or using our node to set up our own wallet where we can start transacting ourselves, both of which we cover in the Patreon tutorial. For now, however, I think this is a good ending point. We've covered each step of the Bitcoin transaction transaction lifecycle, the consensus mechanisms that power this, and the core computing principles of cryptography enabling integrity in the system, as well as getting our hands dirty, setting up a virtual machine in the cloud, building Bitcoin Core from source, and running the program. So that's the project. Running a node isn't just technical, it's philosophical, a modern forefront of tech, finance, and freedom, all packed into a few lines of open source code.
We're now going to switch up the vibe and focus on media streaming platforms. We'll continue looking at core ideas in computing while also diving deeper into more practical software engineering, working with video and audio, looking at how they are contained and transported over HTTP in bytes, and on the reverse, how to decode these bytes into a playable video on your computer. We'll be working with APIs, web scraping, and mainly focusing on the infrastructure of modern streaming platforms. So full video on the Patreon, including the code and written tutorial.
Project 5. The lore of Project 5 stems from a love of music and tech. Ever since Apple's AirPods released, and my first pair in 2018, I'm usually walking around with a single bud-in to set the mood, whether it's lo-fi beats at my desk or medieval tavern music at the coffee house. And also because I have a pretty bad pet peeve for people who play stuff out loud in public. I've had enough of my own brain rot, I could do without yours too. That's when the second bud goes in. So naturally, the idea came for some kind of tone setting or music playing ambience app. Something that takes in your surroundings, maybe your heart rate too, and plays the best suited tune, like a background score in a movie. This is obviously quite a big project. We need a 24/7 camera to collect all the context, hook it up to some AI video processing model in the cloud, not cheap, info from any other wearables like a watch or smart ring that might help determine the mood, connect that to a music streaming platform, maybe decide the best song based on the user's likes or playlists. There's also the option to generate something on the fly and play that music. As you do, I added it to my notes page with the rest of my trillion-dollar app ideas and kind of forgot about it. In the midst of working on this video though, the idea came back to me. A much smaller implementation of the idea, but something fun that keeps the heart of the project alive. We'll be building this desktop app, a cross-platform text editor all about music and vibe. As you start to type faster and your ideas are flowing, the lo-fi music in the background picks up the beats per minute, helping fuel the inspired tone. Eventually, maybe you run out of ideas and get writer's block. Your typing slows down and the BPM drops alongside that. Or maybe you just want the classic lo-fi girl live stream in the background. Switch to dark mode, and maybe you want to save the file too. That's the project. Definitely a lot simpler than the original grand vision, but still covers a heap of programming and computing concepts. We'll be looking at how programs execute on a machine, the stuff that turns this scrap of metal into a coordinated, Turing-complete machine capable of anything. We'll also take a look at the full stack code that goes into building a product like this, front and back end, as well as the framework we are building on called Electron, comprised of Chromium and Node.js, which enable the project to be cross-platform. A good comparison point for when we later look at building native apps on mobile. To understand how we'll be building this project, let's start as always with the bottom layer, the trunk of our learning tree, and work our way out to the branches. Remember, we mentioned in the web server project that Apache, our web server, is just a process, some code being executed on the computer to achieve some specific task, like running a calculator, or it could also be a system process, run in the background to handle something under the hood like Wi-Fi connections. In fact, there's many different types of processes running on your computer, each with its own role. And it's worth mentioning there are many different ways to categorize processes, not only by their function, their state, their lifespan, the threading type, which we'll see, or their origin. And so now would be the perfect time to discuss how programs are actually executed on computers in a bit more detail. We know that programming languages are just high-level, human-readable instructions, and a compiler or interpreter is just another program, one that translates source code into machine code, human-readable code to a sequence of binary instructions, ones and zeros, which we can also represent using hexadecimal, for example. And we also know the difference between the two types of translations. Either way, the resulting binary instructions or machine code are still doing the exact same thing your original source code described, just in a much more detailed and explicit format. For example, x equals 5 in Python might translate to something like this set of bytes. This would be an instruction to move the 5 value into some register in our CPU here. So it's an instruction specific to the CPU. It's telling the processor exactly what to do at the hardware level, storing the value 5 in this AL register, basically just a place to store temporary data during operations. But the main point here is the binary instruction. And good news is, we're also well aware of how this data will be stored at the hardware level using devices like transistors. Okay, so what is the CPU? Why can we just give it these instructions? The CPU is the hardware component in a computer that usually sits under a fan to keep it cool. It fetches, decodes, and executes the instructions to perform all the operations on a machine, from playing music out the speakers to managing Wi-Fi connections. Physically, it's made of a material called silicon. This is taken and shaped into a very thin wafer, upon which billions of transistors are etched onto the surface using light, making multiple CPUs. These are then cut out and packaged into individual CPUs ready for sale. Like we said, transistors are basically tiny switches which control the flow of electrons to represent ones and zeros. And we also discussed how combined together transistors can create logic gates, like AND, OR, and NOT. Combine the gates together and we can create even more complex circuits that can perform arithmetic operations called adders, a flip-flop circuit capable of storing ones and zeros for building memory, and ultimately all types of circuits for full instruction processing, powerful and capable enough to build a Turing-complete machine. But to be clear, all these CPU components lose state when power is lost. We say this is volatile. To maintain long-term offline data storage, like with SSDs for example, we use special transistor designs like with floating gate cells which trap charge and represent data persistently without any power, or with RAM where we combine transistors with capacitors, which enables for faster reading and writing of memory, but again volatile, losing state without power. That's about all we need to know for now without becoming full-fledged electrical engineers. So these circuits are once more combined and organized into functional units within the CPU, like the arithmetic logic unit for performing all types of calculations on binary data, the control unit for directing operations, registers for temporary fast access storage, and the cache for quick data retrieval. Together, these functional units make up what we call the CPU, forming the foundation of everything from adding two numbers to running an entire operating system. And we should also make it clear that the binary instructions, or the machine code we give the CPU, are specifically tailored to the architecture of that CPU. It's why code compiled for one processor, say x64, won't run on another like ARM. So the machine code, the actual binary rules for execution, follow the instruction set architecture of the specific processor, telling us our rule set, which instructions we can call. It's also why when installing software like games or apps, we need to choose the version built for our processor. And that leads us nicely into the next part of code execution. So to recap, machine code is specific to the CPU architecture and it must follow the instruction set architecture, the native language of the CPU, defining exactly what instructions the CPU can perform, how those instructions are organized, and how they interact with memory and hardware. So as we see once more, it's all protocols, stacked layers of interpretation, whether we're building networks to transport data, building apps and games, or to execute low-level instructions on a CPU. Same principles. For example, there's the x86 ISA in front of you, used in a lot of desktops and laptops for Intel and AMD chips. Another ISA example is ARM, common in smartphones and tablets like the Apple M chips. Even though the details may differ, these architectures have similar building blocks when it comes to how instructions are organized, the same way different programming languages share the same building blocks. Each instruction, a set of bits, usually includes an opcode, short for operation code. This tells the CPU what to do. For example, add two values, move some data, or compare some values. Then maybe change the flow of execution by jumping based on that comparison. We also have operands. This specifies what data the operation should act on. This can include data in some memory address in RAM, registers, tiny temporary storage areas in the CPU, or immediate values passed in, fixed numbers written directly into the instruction itself. And so the operand opcode approach is just an implementation of the core mathematical expression model we've seen before in this video, showing us how math and computers are tightly related. And if you've read through the All of Software and Computing Concepts learning doc on the Patreon, you'll already be familiar with these ideas at the core of computing. Finally, we have addressing mode. Depending on the ISA, this is sometimes baked into the opcode, so you might see diagrams like this. In other ISAs, it's a separate field. The addressing mode basically tells the CPU how to interpret the operand, whether it's a direct value, a memory address, or a register, just a reference to where the data can actually be found. And as you can see, even though this is a machine code instruction, we have this assembly tag in the corner. This means assembly language, basically a human-readable textual actual representation of machine code instructions, since writing raw binary is pretty painful. So remember our compilation process. That's why it emits assembly and the assembler, just another program, turns it into machine code. Cool, so that's how we arrive at the instructions. Now how are they executed? What's the process after compilation or interpreting to machine code? It's not just run immediately like pressing play on a video. There's a specific cycle the CPU follows to process each instruction one at a time. We call it the instruction cycle, which at a high level looks like fetch, decode, execute, and loop. So let's see these 3 steps. But first, a kind of step 0 just before the instruction cycle. We said source code is translated to machine code, but we did not mention that this resulting machine code is loaded into the RAM by the OS. And of course, we know the OS can do this because we've already seen how the OS sits between the hardware and the user/applications. The reason the instructions are loaded into RAM is because the CPU only interacts with the RAM, not the main disk like your SSD. This is because CPUs operate at billions of cycles per second, and they need data at that same pace, each cycle executing a process instruction before switching to another process. More on this soon. So for this fast pace, CPUs interact with the RAM, which we explained earlier at the hardware level why it's so fast, able to respond in nanoseconds, hundreds of times faster than the SSD. An easy analogy is to think of a workplace. Our hard disk is the filing cabinet, our permanent storage, the RAM is our desk space, fast and temporary access to items, and the CPU is the worker at the desk. The CPU can work quickly with the RAM on the desk, but the CPU can't reach the filing cabinet, so the OS pulls it over. Remember, the OS exists to manage hardware resources, abstract physical hardware interaction for us, and maybe provide a GUI. It's like the intern in our analogy, running back and forth, fetching files, grabbing coffee, and pretending it's not underpaid. So here, after loading the machine code into the RAM, the OS is also then responsible for setting up the program as a process, a running instance of our program with its own execution environment. This includes its own memory state, CPU state, and identity. So it's one piece of hardware and multiple processes, although each process acts as though it has its own private computer and resources, like guests in a hotel, each with their own room, keycard, and personal space,
but all sharing the same building, elevators, and infrastructure behind the scenes. This is called process isolation. The operating system uses separate virtual address spaces, each process's individual view of memory, and process privilege boundaries to give each process a private execution environment, preventing them from interfering with each other. A related but different concept is called virtualization, which goes a step further and creates the illusion of entirely separate machines or operating systems running on the same hardware, enabling efficient sharing of the system's resources.
Okay, so let's see what setting up this operation looks like under the hood before we continue with the instruction cycle. We start by allocating memory in the RAM for the process. Within that allocation, each process gets 2 key regions of memory, a stack and a heap. The stack is a structured, fast-growing region divided into stack frames. Each time a function is called, a new frame is pushed onto the stack to hold the function's local variables, parameters, and return address. And flashback to our data structures practice, you'll recognize the last in, first out nature of the stack, perfect for tracking functional calls and returns. Memory here is automatically managed and short-lived, freed as soon as the function exits, like some incremental counter variable in a loop. For example, our download variable from the last project, or this message variable in front of you. The heap is a more flexible, unstructured region used for dynamic memory allocation. Programs request space here at runtime, and the data here is not tied to a single stack frame, so it can outlive the function that created it. For example, ideal for creating a new mutable object. The variable name reference lives in the stack frame, and when the function ends, the reference on the stack is popped, but the object on the heap can still live on if another reference exists elsewhere. So memory on the heap lives as long as the program needs it, and must be manually or automatically freed depending on the language, making it ideal for data that lives beyond a single function, like a list of user profiles used across multiple steps in a program.
Where values live depends on the language and runtime. But here's another example in Python specifically to really drill it home. In Python, everything is an object and lives on the heap. The stack just stores references to those objects. This supports the dynamic nature of the language. In lower level languages like C and C++, we must explicitly control whether data goes on the stack or the heap, as well as removing the data off the heap. These statically typed languages may store variables on the stack when their memory usage and lifetime are known at compile time, safely managed in the limited scope of a function or block, freed when the function returns. Also better since stack allocation is simpler, cheaper, and usually faster due to its last in, first out nature, meaning overall better fine-tuning and performance control with these languages, but riskier and more manual. Aside from allocating memory, the OS also assigns a unique process ID, and you can see these listed when you check all the running processes in the terminal. The OS also then initializes registers, small, super fast storage areas inside the CPU, faster than RAM, that hold data for the processor. Remember, the same physical registers but shared by all the processes. So when preparing a process for execution, the OS loads the registers with the initial values relevant to the process. For example, one key register is the program counter, which holds the RAM address of the next instruction to execute. Remember, the OS loaded the RAM with the executable machine instructions after compilation. And also remember that each process is isolated, so each has its own section in the RAM and its own program counter keeping track of the next instruction. When the CPU switches to execute a different process, the OS saves the value in the RAM and reinitializes the register when it's time to execute again. Another example is the stack pointer. Like we said, the OS allocates each process its own stack in the RAM, and so there's also a stack pointer register living in the CPU. It's the memory address value at the top of that stack for the current process. This way the CPU knows where to push and pop data, like our local variables or variables which reference larger items in the heap. For example, we might write code like x equals 5, which might compile down into an instruction like move R1 5, meaning move this value 5 into a register, since the CPU works through these registers first like an interface, and then another compiled instruction like push R1. So finally, the CPU will look at the stack pointer and see where in the RAM to store the value 5, in bytes of course, and yes, to complete our picture, the RAM address will ultimately translate to a physical location on the hardware. There's also more general purpose registers which hold the data the CPU is currently working on for fast access, like numbers to be added or a result from a previous calculation, and other registers with more specific purposes like we've already seen. And remember, they are shared, so no need for millions of registers, just a few purpose-built ones. So with all that in place, the CPU is ready to start the instruction cycle, and I promise you we're near the end of the background knowledge and will lead into the project soon, but trust me, this is good stuff. As for this instruction cycle, remember that this happens fast, billions of times per second, and covers everything being executed from rendering pixels on the screen to handling keyboard input and running applications. It's all broken down into countless low-level instructions, each executed in these fast, tiny cycles. Step 1 is to fetch the next instruction from the RAM. The CPU uses the program counter register to check the memory address of that next instruction where the OS loaded the machine code in. The address is copied to the memory address register, which tells the CPU where to look in the RAM. Meanwhile, the program counter is incremented so it's ready to tell the CPU where the next instruction is. The CPU then sees the address in the memory address register and copies the data, our machine code instruction, into the memory data register, and from there into the current instruction register, ready for stage 2. Long story short, a lot of registers doing their part. Step 2, decode. Now the instruction is ready to be understood. We don't need to memorize every detail on screen, but it's there for completeness. The control unit takes over, reading the binary instruction in the current instruction register and splitting it into parts: the opcode, what action to do, and operands, which data or locations to perform the action on. And the control unit isn't programmed like software. It doesn't pass the instruction. It's hardwired circuits that interpret machine code based on fixed bit fields according to the CPU's instruction set architecture, similar to Project 1 and the card reading protocol on the bit level. So the input is a binary instruction, the logic is fixed circuits, logic gates, decoders, multiplexers, and the output are control signals, streams of ones and zeros sent through wires that switch transistors in different CPU components, triggering the correct operations. Basically, the CPU's own built-in binary language. And this will make more sense in the final stage, step 3, execution. So we kind of mentioned this already, but depending on the instruction, this might mean the control signals will tell the arithmetic logic unit to perform a calculation. For example, writing the result in the accumulator register, or it might trigger some data to be moved between registers, fetched from memory, written to memory, or even cause a jump to another instruction in the program. And that's the cycle. Immediately after, the CPU goes straight back to the top of the cycle, fetching the next instruction from the register in the program counter we incremented to. And unless we have multiple cores for parallel execution, the OS and the CPU are working together to execute one thing at a time using the CPU scheduler to rapidly switch between all the processes, meaning you can rebase
and revise your code review at 5 PM because senior engineer Douglas dropped you a message on Slack letting you know you forgot a semicolon, all while you're stuck in a Teams meeting about the 50-year vision for the organization, but you're more interested in watching last night's curling highlights in the background. So to recap, we have our CPU made of a bunch of useful functional components. We have our source code compiled by the compiler, which is just another program, into assembly and then executable machine code, which follows the instruction set architecture of the CPU. The machine code is loaded into the RAM by the OS, and really and truly, everything running on a machine is code, whether it's a game or the browser, and all code can be translated to executable binary. Then it's CPU time, going through the fetch, decode, and execute cycle to shift around electrons through transistors and logic gates, and by doing so, it can add numbers, move data, compare values, or jump to a different instruction, allowing us to perform any type of computation possible. Okay, so let's take a look at these ideas in action, particularly at the process level with Google Chrome, the perfect bridge to then see how we'll use Chromium to build our app as part of Electron, the cross-platform desktop application framework. So we have a process, the program currently being executed. A thread is the smallest unit of execution within a process. The process is the full program in memory with its own isolated execution environment, which we've seen. The simplest process will have one thread, and each thread gets its own register state, like its own program counter and its own stack in memory. More complicated processes can have multiple threads, each a small sequence of instructions the CPU scheduler can handle independently. So some key points are on screen here. For example, processes get their own isolated space in the RAM. They don't share, but the threads inside, they share that space and can access each other's memory. They are a subset of the same process. A single-threaded process would be something like a simple command line calculator or some basic Python script with one thread doing all the work, and multi-threaded processes, something like our trusty Apache web server, using one thread to handle each incoming request. Cool, so back to Chrome. Opening the application, which is just a binary executable, like Chrome EXE on Windows, runs the main browser process responsible for managing the overall application across all windows and tabs. It's like the coordinator of the app, spawning multiple child processes, each with a dedicated responsibility. For example, a renderer process, which takes the HTML, CSS, and JavaScript of a web page and interfaces via the OS with the machine's graphics processor to render that into the pixels you see on your screen. More on this later. Or the browser process might spawn a network process, which handles all network communication, like fetching web resources by interacting with the OS's network stack, like the network interface card, which we know all about from Project 2. Once more, this isolated design for the processes helps for security, sandboxing each process with its own privileges and improving stability. For example, one tab crashing will not tactical nuke the entire app, plus the added benefit of per tab resource management for better efficiency. Although now we reach a problem. We have all these isolated processes which we want to keep separate, but yet somehow we need them to communicate with each other to bring the total functionality of the browser together. This is where inter-process communication enters the scene, a mechanism that enables different processes to, yes, you guessed it, communicate, share data, and sync up their activities. When it comes to the practicality of this, how the OS and app come together to implement IPC, well, it depends on the type of communication channel we are trying to open. The OS, as always, handles the lower level plumbing, and the app or the framework will handle the logic of initiating this communication through whatever abstraction or API it provides. Let's take a look at IPC methods in practice at the OS level before finally diving into Electron. So a pretty easy to understand example you may have used before is piping, where the output of one process is directly passed as input to another. For example, ls pipe grep my file, where the ls command outputs a list of files and folders, and the grep command filters that list to only those containing the given string. This is a unidirectional communication channel, meaning one way, great for linear data processing, but not so much for when processes need to share and manipulate more complex or persistent data. For example, when two processes are working on the same file. Let's say process A is writing data and process B wants to read the data. Traditionally, process A opens the file, writes the data, and closes the file. Then process B opens the file, reads the data, and closes the file. Working with files in this way involves going through the file system and OS level file input/output, involving system calls, permission checks, and a lot of slow overhead instead, that also requires ensuring process B reads after A has written and not before. There's just a fair amount of latency and complexity. Instead, with memory sharing, another IPC method, processes can share a chunk of RAM using a memory mapped file. Okay, what does that mean? Well, this means by using OS level features like mmap on Unix machines like macOS or Linux, we can map a file's contents directly to memory as if it were an array in RAM. And this memory mapped file region is then made accessible to both processes, allowing one process to read and the other to write simultaneously at much faster speeds without having to go through the file system. Although this doesn't fix the issue of coordination, but don't worry, there's tools for that too, although that's for another time. For now, let's just be aware they exist. Back to our Chrome example now, and we should be able to understand how the different isolated processes come together under the hood. For example, clicking download file on a web page may trigger the renderer process, responsible for everything on the web page inside the tab to send an IPC message to the main browser process. The browser process might then communicate with the network process, which will fetch the file over the internet. Once the data starts streaming in, the browser process, which has the necessary file system permissions, can handle writing the file to disk. So that's how it's done. But it's worth mentioning there is no one way to make a browser. It could be one process with many threads or many single-threaded processes. Chrome, however, uses a mix of both, and you'll be pleased to hear that's our background complete. Programs, the CPU, the operating system, processes, threads, IPC, and Chrome. And now we should be able to understand every component and step of source code execution on a machine. Let's now shift over to the project at hand. We'll be using Electron. Electron is an open source framework that allows us to build desktop applications using web tech like HTML, CSS, and JavaScript. It does this by bundling together Chromium and Node.js. Let's make sure we understand all parts of the framework, which will make building the app 10 times easier. And we'll start with Chromium. Chromium is an open source web browser. You can literally just go and download it, build from source, which we know all about from the full Node project, and you get a fully working browser, different from Google Chrome as we can see in the applications menu. It includes all the core components of a browser: the HTML/CSS rendering engine, Blink, the JavaScript execution engine, V8, the networking stack, sandboxing and security layers, and the basic front-end interface with things like tabs, an address bar, and settings. All the stuff that makes a browser run without the bulk. In fact, Chromium is the foundation that many browsers use, like Google Chrome, Opera, and Edge, and even non-browser tools like Electron. These apps and tools build on Chromium by layering on custom branding and features to build new things. For example, the browsers will add their account services and some UI customization. Chromium looks like this. There's a lot going on here, so let's focus on a couple of the main things. First of all, it's a multi-process architecture. We have the browser process, also called the main process sometimes. Each browser process, like we saw in the Chrome example, controls the lifecycle of the app, managing tabs and windows, network requests, and other coordination type responsibilities. And when a new tab is created, the browser process will spawn a renderer process. Quick look under the hood.
Each renderer process has a render process object, literally just a C++ class, responsible for participation in inter-process communication with the browser process.
Working together, for example, user input is captured by the OS and relayed to the browser process. The browser process determines which renderer process should receive the input and forwards it via IPC. The renderer process then handles that input, like say a click opening a menu, triggering some JavaScript that updates the page. The renderer then sends a message back to the browser process with the updated portion of the screen, which will then talk to the GPU process to perform the on-screen repaint. So on the browser side, there's a corresponding render process host object. This is essentially the browser process's handle to a specific renderer process, and it's a one-to-one mapping between each render process host and the associated renderer process managing the IPC communication bridge. Back on the other end, like we've said, each renderer process is responsible for rendering web content for one or more tabs. It includes key components like the render view, which handles things for the whole page like layout and zooming, or the render frame object, which handles the content inside each part of the page or frame, like running JavaScript, working with user input, and updating the DOM. We're not really worried about these objects in detail. The main point here is that we take a clean programming approach of dividing responsibilities into manageable units. We call this modularization, and we'll see a lot more of this and clean software engineering design in the rest of the video. And there's also the point that since Chromium is open source, we can just open up the code package and have a look inside at the objects and their functions. For example, how they handle IPC. We also see this WebKit thing here. This is the original browser engine, later forked by Google to create Blink, a more evolved engine. This engine is responsible for parsing the HTML to build the DOM, styling it with CSS, and executing JavaScript code using a separate JS engine called V8. More on that in a second. So the rendering and JavaScript engine work together inside the renderer process. And again, Blink/WebKit handles structuring the layout of the page, parsing HTML, styling and paint logic, while V8 executes the JavaScript that drives interactivity like any click listeners or animations. And specifically in terms of screen rendering, the rendering engine calculates the pixels on the screen and sends paint commands to the GPU, like we said, via the browser process using IPC for you to enjoy all these beautiful colors on your screen. So that's Chromium.
Node.js is another open source project, a runtime environment that lets you run JavaScript outside the browser.
What does that mean?
Well, originally, JavaScript was designed to run only inside web browsers. Gather around the campfire again, it's time for a bit of JavaScript lore. You see, originally, the internet, as we discussed, was this network named ARPANET, created by the US Defense Department as a research project in 1969. Eventually, it was adopted by more official bodies, including universities and government agencies, as the network grew. It was used for tools like Telnet, a kind of older SSH for remote computer access, and the very first emailing system, all text-based and in the command line. A major turning point came in the early 1980s, considered as the moment ARPANET transitioned to the internet, moving from the original NCP protocol to TCP/IP. Eventually, in 1989 at CERN, a European organization for nuclear research, also known as those guys with the massive super collider machine underground, an employee there by the name of Tim Berners-Lee came up with the idea of a system to link and access documents over the internet using hypertext. And when we say hypertext, we mean the cross-referencing kind, like hyperlinks. That was the idea, a worldwide web of links and documents over the internet network. So in 1990, he developed the first version of HTML. He built the HTTP protocol, the URL address system, along with the very first browser, the very first web server, and hosted the very first website ever, which went live in 91, still up and running today at info.cern.ch. That was all a big leap, but still lots to do. For example, Tim's web browser was cool, but it could only run on Next computers. You know, the ones Steve Jobs created after he got kicked out of Apple in 1985. These were expensive PCs, and the web Tim created was still mainly for plain text. The first version of HTML didn't even have support for images. But eventually, as computers became more affordable and web technology evolved, ISPs began offering dial-up internet access to homes. On top of that, cross-platform, user-friendly browsers like Mosaic and Netscape were also developed, with more features and ease of use, increasing adoption by the regular, non-technical person, helping the World Wide Web grow ever larger. And here's the important point. When creating Netscape, the developers behind it wanted to remove the static limitation that pure HTML provided. They explored different ways to introduce interactivity and landed on lightweight scripting in the browser on top of HTML's structured content. And eventually, they decided the best thing to do is to create their own programming language.
I had been at Silicon Graphics, and Netscape was founded by Jim Clark, the founder of SGI, and Mark Andreessen from the National Center for Supercomputer Applications. And Andreessen had done the Mosaic browser, and he and Clark got together to do Netscape. Really tried to recruit me by saying, come and do a programming language in the browser. When I got to Netscape, they already said, oh, we're looking at this language from Sun called Java, so maybe never mind. And the only way that Mark Andreessen, who really still believed in the idea of JavaScript, which we called Mocha at the time, making it a sort of a sidekick language or a little brother language, was for me to build a demo in 10 days to show at an all-hands meeting that there could be a language in the browser that loaded quickly and you could instantly use to compute HTML or, you know, validate the field, the data in a form field. And that I did. I did that in 10 days. Mark Andreessen was very clear that you should just be able to write the code in your page, right? And you know, this is easier said than done, but what he meant was it should be interpreted, as was pointed out earlier, it should be very fast to load, it should be accessible to beginners, amateur programmers, graphic designers who know a little BASIC from their Apple II, 15 years earlier. It should be a language for the masses as opposed to Java, which you have to write, a class that wraps the main program. You have to run a compiler. You have to know what types are. And unlike, TypeScript and Float, at that point, Java did not even have decent local type inference. So you had to write types everywhere. It was like painful. Java was not going to be for the masses ever, and we knew this, and that's why Mark and I and Bill Joy supported JavaScript.
So JavaScript was created, an interpreted language that would be executed in the browser using a JavaScript engine, responsible for parsing the code and translating it to machine code to be executed on the machine's CPU. And this may be a level of detail too far, but it's a good knowledge check to mention how an interpreter works. The interpreter itself is just a compiled program that the CPU executes, compiled into machine code and loaded into the RAM. So strictly speaking, the CPU executes the interpreter program and not the source code directly. The original source code is also compiled and stored in memory, but in bytecode. Bytecode is platform independent, unlike our compiled machine code, dependent on the instruction set architecture. And when we see VM here in the table or in our diagram, it refers to our actual interpreter program. Since the interpreter, the program being executed, runs its own fetch, decode, and execute loop with its own program counter, reading the next bytecode instruction just like a real machine would process things. And for any instruction possible, like add or print, the interpreter has machine code built into the compiled binary to handle that operation, which it will give to the CPU to execute before continuing to the next instruction. So back to our browser. HTML is still the entry point to a web page. Think of it like the main function, the first thing the browser engine executes. It defines the structure, our document object model, and now also defines the JavaScript code to load. Then JS can start moving stuff around in the DOM, we can attach event listeners for clicks and key presses, and make network requests, all via a neatly coupled browser API in the JavaScript engine, including easy-to-use objects like window and fetch, which provide a connection between the JavaScript and the HTML. Then years later, in 2008, Google released V8, an evolved JavaScript engine with just-in-time compilation, addressing a lot of issues in the past with previous JavaScript engines. So finally, this is where Node.js comes into the picture. This guy, Ryan Dahl, saw what V8 could do and worked on the idea to take this JS engine from Chrome so we can run JavaScript code outside the browser. You see, by itself, JavaScript is single-threaded, meaning code runs synchronously using a single call stack. One big while loop could stop execution. Sure, inside the browser, JS can hand off tasks to the browser to run asynchronously in the background, like some network request using the fetch web API, which the browser schedules a callback into the JS event loop when ready. But this asynchronous stuff is running outside the JS engine, powered by your OS via the browser. So your browser is handling the binding to the OS for these extra features. To take JS out of the browser and make it a true programming language, and not just a browser scripting tool, Ryan combined the JS execution engine with libuv, a cross-platform C library that provides an event loop for asynchronous code running like the browser was handling previously, as well as other bindings for things libuv does not cover or are indeed platform specific. Things like bindings to the OS file system and cryptography and compression using cross-platform libraries like OpenSSL and zlib, all exposed to the user as easy-to-use Node.js APIs. So what does this mean for you? Well, you can literally install this Node runtime environment on any platform, write a JavaScript file and run it inside Node on your PC. So Node brings JS into the world of general-purpose programming, giving it powers it did not have before. We can now read and write files using built-in APIs like FS, run shell commands, create web servers, and a lot more outside the browser. A true backend language. Okay, so we know Chromium is a working browser with a multi-process architecture, and Node.js is our backend runtime environment for JavaScript. But where do the two worlds meet? Chromium is great, but you can't just write a JavaScript file and start calling methods. Sure, Chromium has platform-specific code to work with different operating systems, but it's buried under the browser. It's not for developers. And Node is great too. We can build all sorts of apps, but it doesn't come with any out-of-the-box UI or framework, especially if we want to build desktop applications. This is where Electron enters the scene. It's a framework that merges Chromium and Node into a single runtime, giving us the best of both worlds. A Chromium renderer process to build beautiful UIs with HTML, CSS, and JavaScript, and a main process to manage the app. A Node.js runtime extended with Chromium integrations so it can act like the browser process, also giving us easy OS interaction using Node APIs. So Electron takes Chromium's renderer process, responsible for creating browser windows, and strips out all the browser-specific features like the address bar and tabs, since we're building desktop apps and not a web browser. And of course, we can write HTML
HTML, CSS, and JavaScript in the renderer since we have all the necessary parts, particularly the Chromium rendering engine and the V8 JavaScript engine. So that's one half. Alongside it, Electron embeds a Node.js runtime as the main process, extended with Electron's own bindings to Chromium. This is our backend. This allows Node to act as the main browser process did in Chromium, spawning and managing renderer windows. How they wire together is for another time. Instead, the key thing is, in our Node environment, we have all the great stuff Node gives us, like easy-to-use built-in libraries for OS access, all while writing sweet JavaScript and not evil C++. Within that wiring though, Electron also provides us easy-to-use custom APIs, like IPC to communicate with the renderer process and back again. We also have browser window to launch and manage renderer processes, and app to handle the lifecycle, like when to start and when to quit and close things. Again, all available to us in JavaScript, executed in the embedded main process, our Node.js runtime. And this is of course useful since Node doesn't have built-in APIs to create browser windows. It was never designed for that. It has no understanding of what a renderer is. It's like asking a biology major to reverse a linked list. So Electron takes on the responsibility. Where before the renderer process would usually communicate with the Chromium browser process via IPC, it now communicates with Electron's Node.js main process managed by Electron's IPC bridge. And we'll see this in action real soon, I promise. So all in all, this means me and you can now write JavaScript in the main process and access the OS, while Node and Electron handle the C++ bindings to each platform's OS for us, whether it's for file system access or networking in Node, or desktop features not covered by Node like calling Chromium internals to create browser windows, or using app to launch the application with Electron. And again, on the other side, we can use HTML, CSS, and JavaScript to write the front-end code in the renderer process, which Chromium have built with all the components needed to build dynamic web pages, style them, and render them on screen. Cross-platform OS-level access using a simple web technology stack across the board to build whatever desktop applications our hearts desire. So I don't want to get into every detail of the code, like the config, the libraries we use, the music features, although it's all cool stuff, especially how we tie the keystrokes to the beats per minute using data structures we know and love combined with some math. The code's there for you to play with on the Patreon, and the tutorial explains everything. The projects coming up will also cover a lot of app infrastructure stuff and how to write good clean code, you know, software engineering things. Instead, I want to focus on the coded implementations of the computing concepts we discussed, giving us the understanding and toolset to use Electron and JavaScript to build any kind of cross-platform desktop app we want, from Discord to Desktop Goose. So first, we'll speedrun the app infrastructure, how we build and run the project, and then go deep on how we use IPC in our Electron app to implement two features, light and dark mode and saving files. So let's start with the larger skeleton of the project. We kick things off by creating a Node.js project. This might seem strange at first. Why a Node.js project and not an Electron project? Well, the Node project on our machine is not the node that Electron runs. Our Node package is just the scaffolding for running Electron. It's our system for building the project. Electron itself is just an executable binary with its own Node.js runtime embedded inside. When we run our top-level Node.js project, we are executing Electron, which loads in our main.js file defined in our project's manifest file, which we'll see in a second. We could directly work with the Electron binary, but this approach provides a better workflow for development. So to be really clear, Electron is a framework that ships as an executable binary, our Chromium plus Node.js bundle, and it's distributed as a package via NPM. NPM is the default package manager that ships with the Node.js runtime. Firstly, NPM is a command line tool where we can run commands to install third-party libraries like Electron. This hooks into the NPM registry, basically a massive online database of all the JavaScript packages you can install, which are almost all open source and free to use. Package.json is the configuration file that NPM reads and writes to. In this file, we can define those dependency packages and metadata, scripts, and more. For example, we define Electron and the specific version of it as a dependency. So that's our main build structure. We also use TypeScript, a programming language built on top of JavaScript that gives us type safety. It needs to be compiled to JS before execution. We cover this in the tutorial and also in the next project. And here's a quick example of the benefits of type safety. Of course, we also have Electron, our framework bundling Chromium and Node.js to provide the execution environment to run our desktop app. And it's a good time to mention the two slightly different meanings of the word runtime. So firstly, at runtime, meaning the moment of execution, and secondly, Electron being the runtime, meaning the process that launches and executes starting from the main file and following the code execution flow from there. We also have Electron Forge, a useful tool to help us package up the app for distributing it on multiple platforms. It's a bundling tool, taking our source code and including the correct Electron binary for each platform, Windows, macOS and Linux, and generating the correct installers, .exe, .dmg or .deb for installing the app on your desktop. The maker is an Electron Forge plugin responsible for this operation of creating the platform-specific installers from the packaged app. Each maker is specific to each format on each operating system. We have Webpack, another JavaScript library that is a module bundler. You see, modern apps are made of a lot of different modules: TypeScript, React, other third-party library imports, CSS, images, audio, and more. Webpack bundles these all together, which just means transforming these assets and their dependencies into optimized static files so they can be loaded in the browser efficiently, or in our case, the Electron renderer process. For example, all these files get compiled down into one JavaScript bundle file containing everything, including our CSS and our HTML, or our React JSX to be precise, but more on that in a second. So anyway, we set this up in a webpack.config.js file in the root of the project, defining all the bundling rules, and we'll cover this awesome tool in depth in the next project. Finally, we have React, a JavaScript library that makes building user interfaces a more developer-friendly experience. It comes in two flavors, React DOM for building web UIs and React Native for mobile apps. As for the working details of React, again, we'll wait for the next project. But just like Webpack and TypeScript, since it's distributed as a JS library, we can of course install it, defined in our package.json. And here it's worth mentioning the difference between the two dependency types in our package.json file. Simply put, dev dependencies are only needed while developing our project. For example, TypeScript or some testing library, and our dependencies are required for runtime, like React, which works real-time to dynamically update the DOM, and this will make more sense later. And so that's the infrastructure and folder layout of our app. Now the logic. Here's a quick summary of the execution flow. Let's go step by step. First, Webpack compiles index.tsx and any transitive dependencies in the file into bundle.js. Transitive meaning any other files / modules we import into the index.tsx file. Index.tsx contains React UI code and is the entry point of our app on the renderer side, the code that will be executed once the browser window is launched from the main process, creating our beautiful text editor instead of this empty window. We define the entry point for the renderer inside the main process, since here is where we spawn renderer processes which display the views of our app, as we know well enough by now. And we also know the reason we bundle the React TSX/JSX into JS is because at the core JavaScript is the only format the browser and thus the renderer process can execute. Not TSX React code or TypeScript, but JavaScript. And since our entire front end of the app is in React, which we'll learn more about later, and React TSX compiles to JavaScript, not HTML, then we need some basic HTML to link this JavaScript to, so our React code has somewhere to hook into and start playing around with the DOM. So we write a basic index.html in our source code, for which Webpack will generate an identical index.html in the dist output folder, since of course HTML doesn't need any compilation. So in the next step, we tell Webpack to add the link to the bundle.js in the output index.html. This allows our React code in the JS bundle to hook into the HTML, using this root element as the binding point. Now when the renderer process loads, the React UI code from index.tsx can render in the text editor and all the good stuff inside it, like our lo-fi girl. And that's the hardest of it. If you understand that first time, you're in a pretty good spot. If not, don't worry, we have another project coming up with the exact same flow. And finally, it's worth mentioning, step 1 is run with this webpack watch command, which checks our webpack config file, telling it to run all the steps we just mentioned and rebuild anytime we save a file, making developing the project a lot easier. By defining it as a script in our package.json, we can run it with npm run build and leave it there in the background while we make changes to our files. In step 2, we run Electron with the very creatively named Electron script. So npm run Electron will launch the app and starts, as we said, by reading the package.json file for the entry point, main.js, our main process. It will take this file and begin executing it in the Node.js runtime embedded inside Electron. Step 3 refers to our main.js file launching the browser window, which as we've seen loads in the index.html from our dist folder. And finally, in step 4, Chromium loads that HTML into its rendering engine so it can be parsed and rendered onto the screen, also executing the linked bundle.js inside its JavaScript engine. engine. So that's how everything runs. When we want to create the window for our user to interact with, we could just add a plain text area tag to our HTML file. But since we're using React, we'll put our text area in our React code and beef it up with some CSS styling. This will eventually be injected into the HTML using JavaScript from our bundle.js. Either way, the point is, our app is nothing more than a glorified text area tag. Great stuff. And as we've said before, back in our main process, we use the browser window object from the Electron API and choose the HTML file to load, which will be the one from the output folder where Webpack linked the bundle file. Behind the scenes, Electron will start a Chromium renderer process, and the Blink rendering engine begins parsing the HTML. Whenever it hits a script tag, like the one pointing to our bundled React app, it will start executing the JavaScript using the V8 engine. After parsing an execution and layout and painting on the screen, we'll get this empty window where we can start typing stuff. And pro tip, since it's Chromium under the hood, you can literally pull up the DevTools as you would in Chrome or any other browser. This runs a separate process which we can use for things like debugging, logging things out in the console, and tracking network requests. Okay, so we've got the Node.js main process with full access to the OS, and we've got the renderer process rendering our UI. We know the two talk to each other, just like they would in the Chrome examples we covered. So let's see how Electron exposes this communication channel for us. Built on top of Chromium's existing IPC mechanism called Mojo, we can work with IPC channels in Electron through the form of a script, injected into the renderer process before the HTML is even loaded, hence the name preload. We use the preload script to define APIs of our choosing using the IPC renderer object, which has a bunch of methods we can use, and we'll see this in action very shortly. Generally speaking, an API is some interface that allows different software applications to communicate with each other, a kind of bridge per se. There's a brief example on screen and we'll see more later. For us, the API we create in the preload exists in order to enable communication between the main and renderer processes. Obviously, inside the preload script, we can work with the IPC renderer object since it runs inside the renderer process, and in the main process, inside main.js, we'll use IPC main. So, quick simple example. We define the download file API in the preload script, and don't worry about any words or syntax we haven't explained yet, all in due time,
my young Padawan learner.
So this code tells the renderer process to send a message with the string download file and some URL object that gets passed in. And side note, this example is JavaScript. You can easily tell how beneficial it would be to add a type and make sure the URL is a string and not, say, an integer, which is why we use TypeScript in the project. Then inside our renderer process HTML, no React, we can add a button which through the power of JavaScript will call the preload API. When clicked, Electron will trigger the API code, sending the download file message to the main process with the URL argument passed in. Then back in our main process, outside the browser sandbox, we can define a listener specifically for that message. Now over here, we have the necessary Node.js bindings to interact with the OS, like file system access to help us download the file. So it's a pretty basic communication format with senders, messages, and listeners at its core. We can take a quick look at a level deeper to see how this works. When we create our browser window with context isolation set to true, which is the default, Electron runs the preload script in a separate isolated JavaScript context, still inside the renderer process though.
An isolated JavaScript world to be precise, protecting the preload environment from the web page, but still allowing the preload to access Node APIs and allow us to choose which ones to expose to the renderer.
And of course, use of the Electron IPC renderer object. To safely expose the APIs we define to the web page, we use Context Bridge and Electron interface. Using these methods, we can securely pass the APIs from the preload context to the web page window object. This keeps the web page walled off and isolated from the privileged preload environment. Of course important because as we know, the browser window is exposed to running third-party code. For example, any network requests we make in the renderer. And this window is made globally available by Chromium, so we can call it in our code without an import, and the JS engine has no problem accessing it. So there's a few API examples to choose from in our app. Let's start with light and dark mode before moving on to saving files. So we have this empty text area and we're going to add light and dark mode so everyone can feel included. The first thing I decided to do is add a button to choose the theme. I want the button in this native menu bar for my MacBook, which appears inside the actual application window on Windows. Of course, this goes in the main process since Electron is handling the platform-specific code to access the OS, including things like native menu bars for applications, since of course Node does not understand desktop UI elements. We can simply use the menu menu object from the Electron API to access native application menus, abstracting the platform-specific code for us, adding a menu item called theme with light and dark mode options. Then, when a user clicks an option, it triggers our toggle theme function in the main process, which interacts with the main window. This is what we called our browser window when we created it earlier. And it's worth a mention, this browser window is a main process object because it's an OS native window, with native things just like the menu bar. The stuff inside is the renderer's window object we spoke of before. The web contents property of the main window object is a bridge to the renderer process. It's how we send IPC messages from main to renderer, and we'll see the reverse using preload in a second. Every browser window has an instance of this web contents class. It doesn't hold the DOM or anything allowing for direct manipulation, but it defines a bunch of things we can do, like send messages to the renderer's global window context, execute JavaScript inside that renderer window, and even take a screenshot of the rendered content. So with this built-in send method, we are required to define an identifier string. This is also called the IPC channel. We can also include any arguments we want. So we'll call the string theme change and pass in the mode, another string coming from the menu object. That's everything done on the main process side of things. And now will be a good time to mention the different approach for each IPC action and process. We've briefly mentioned the IPC objects coming from Electron, and we'll see these next, and also now web contents. And of course, we don't need context bridge or any of that preload fluff for sending messages from main, since it's our code and we can rely on it, unlike the renderer exposed to all kinds of web traffic. Also, we just mentioned web contents is tied to each browser window instance, whereas IPC main is the global listener for all windows in the main process, so that's why we have that separation. So anyway, that's the table, and we'll see all four ways we can send messages or listen on either side. Speaking of which, let's now head over to our renderer where we can listen to that message coming from the main process. First though, in the preload script, we need to expose a way to listen to those messages, since the renderer does not have access to Electron APIs by default. We create a wrapper around Electron's pre-existing IPC renderer on method. This is a general purpose listener, allowing the renderer to register a listener for any specific channel by using the channel string name. When it receives the message, it automatically triggers whatever listener function is passed in. So when the main process sends the theme change message, the IPC listener in the renderer for that channel receives the data and calls our handle theme change function. And we already mentioned the preload via context bridge expose in main world attaches the APIs onto the global window object, hence why we use window.electronapi.on. On the renderer side of things, our code has access to the DOM, so this function uses JS to manipulate our HTML elements. We use the document object representing the DOM, an interface to the web page, where we go inside the HTML, grab the body tag, and either add or remove the dark class depending on the mode that was selected. So handle theme change is our listener function automatically receiving any parameters passed in from main and triggered when the theme change message is received. So this function will attach the dark class to the HTML in dist. This is the HTML used at runtime, since remember that's what the bundle.js linked to after compilation from our index.tsx, which is our renderer. Anyway, this will trigger a bunch of conditional styling rules to apply to all the elements nested inside the body, which is our entire app. For example, making the background of the text area window a dark grey color instead of the default white during light mode, as well as making the text a very light grey to go with the dark background. And that's practical example 1 of how we can add a new feature to our desktop app. It's a good first example since the communication channel is one directional coming from our trusted main process. I hope you liked it, because next, a more complicated one, a feature old as time itself, saving files. So let's say I've written my amazing 3-part series on why octopuses are the Mike Tyson of the aquatic world. Well, now I want to save my file and submit it for peer review. The high-level execution flow is as follows. User clicks the native menu Save File button, then the main process requests the content from the renderer hears this message and sends the content back. Main process with OS access saves the file and sends a success message back. And finally, the renderer shows the successful result to the user. So, same as before, we create a Save File menu item button in the native menu bar. And then when a user clicks Save, we trigger trigger an on-screen save dialog box, again provided for us by Electron, who take on the work of hooking up to each specific OS. When the user saves the file with a name, they basically specify the file path in the file system. We can take that file path and send a message to the renderer requesting the content of the file, using the window.webcontents object again. We send this using the request file content IPC channel, passing in the file path as an argument. The renderer doesn't need the file path argument, it's just so that we can send it back later to main after we get the content. It's a design choice. We could just as easily have stored the file path as a variable in main, which will be more secure but less stateless. So as you might have guessed by now, the renderer will need a listener for that request content message. We'll use the IPC renderer module in the preload script and attach the listener with the on method again, except this time we'll wrap the listener in a custom API named onRequestFileContent. We could have used the general purpose on API again, but this is a chance to show how the preload script lets us design our API freely. It looks messy at first, and I wouldn't worry about understanding the specifics of the syntax too much. But in this case, our API call does two things. First, it filters out the IPC channel name, since it's obvious in the custom API name which channel we're using. And secondly, it automatically removes the listener, whereas before we manually had to call IPC renderer off. A bit more of a tailored experience than simply exposing the IPC renderer methods directly. Anyway, as you can see, once the request message hits our renderer's listener, we call the handleRequestFileContent function. This function grabs whatever's in the HTML text area, that's this text variable here, easy to grab since we're inside the text editor, and it sends it back along with the file path using another API we defined in the preload named SaveFile. So you may not have noticed it, but we've upped the difficulty just now. We're not solely using the renderer to listen anymore, we're now sending messages back. So finally, back in the main process, we can listen for the message with the file path and the content. My 3-part series on octopuses hitting uppercuts. We'll use IPC main on to listen to the SaveFile channel, and use Node.js's built-in file system module fs to write the file to disk. The write file function takes 3 arguments, the file path, the content, and the encoding. And this is a nice reminder of encodings in practice once more, which popped up in our HTTP messages in the Raspberry Pi project,
and that we also looked at in depth in Project 4.
So nothing new, we're instructing the function to use the UTF-8 encoding, the standard or rule set for taking these Unicode characters about octopuses and turning them into bytes on our SSD. Finally, we also send a message back to the renderer that we saved successfully, and we use event.sender, allowing us to reply directly back to the same renderer that sent us the save file request message. The renderer registers a listener using another preload API for the save result message, and then we can call handle save file result. This will update the UI with this beautiful green box. Nothing too crazy, just more IPC messaging and style changes, which I'm sure you get the hang of and have definitely had enough of by now. And that's it. We could talk about the music features, late nights mixing math and stone code, but I think we've achieved our goal. We hit a lot of the core mechanisms in computer science, like systems programming, processes, CPU execution, and all of this in real-world action with Google Chrome, then a bit of history looking at the browser, Berners-Lee, JavaScript, V8, and Node.js, followed with hands-on experience using the Electron framework to actually build something real. So the next time you go to save a file in VSC or send a message on WhatsApp, you know all that goes on under the hood technically and all the history that made it possible.
Okay, so we've reached Project 6, and this is one that I just had to build for myself. I use YouTube a lot, whether it's tutorials, interviews, music, or the algorithm's fringe rabbit hole of the day. And over the years, I've seen the platform grow and change. And at some point, the clickbait and filler virus began, infecting creators left, right, and center. Honestly, it's gone too far. So I decided to do what any programmer with common sense would do, and let an AI endure all the suffering for me, leaving me to suffer in other ways. To put it simply, we're building a Chrome extension which can summarize YouTube videos in one click. And so far in the context of the internet and networks, we've seen everything from wires in the ground to the browser running on the machine, inside and out. Now we're building something on top of that existing platform with a Chrome extension, something on the application layer. In that case, we can take a much more practical approach and dive more into the real programming side of things, all while building something people might actually want. So first things first, what is a Chrome extension? Well, we know all about Chrome Chrome, it's Google's browser built on Chromium, a multi-process application running on your computer just like any other program being executed by the CPU. Well, this browser also enables extensions, a set of scripts and maybe some resources that add custom functionality to the browser by interacting with the web page and the browser itself. There are several components of an extension, each plugging into the browser in different ways depending on their responsibilities. And if this table is overwhelming, as always, don't worry,
Young Padawan.
We will go through all these concepts one by one. First, we'll understand the architectural framework we're required to follow when building a Chrome extension, and then straight after, we'll go into the specific code of our YouTube Summariser. Let's start with the manifest.json file. Like the package.json file in our Electron project, the manifest file defines everything about the extension as a project whole. It defines the file path entry points for different parts of our extension, our app's icon, the permissions our app has, which websites our extension will be allowed to run on, and which internal files can be exposed to web pages. And this manifest file isn't executed anywhere, it's just read by the browser process to understand what to do next, like which scripts to load and in which execution context. And side note, we also define the manifest version here. We will be using 3, which includes updates like moving from background scripts to service workers.
So if you have any problems, make sure you're using the latest version since Chrome have killed off MV2.
As we can see, the service worker is also defined in the manifest. It's the extension's event-driven controller, a listener for events, a script that is terminated when idle, then restarted up to handle browser events. This includes things like a new tab open event, network requests, download events, or messages from other parts of the extension. Service workers run in a separate process from both the browser and the web page renderers, a dedicated extension process. And when we say it's the controller of the extension, that's because it's right at the center. As 2 quick examples, in the service worker, we can use Chrome.tabs and Chrome.alarms to interact with those browser features. The service worker can also communicate with the renderer via these APIs using Chrome.tabs.sendMessage, for example. So in summary, the service worker doesn't have direct access to the OS or DOM, but does have a bunch of functionality through these Chrome extension APIs. Since our project doesn't actually need a service worker, we'll show a quick example here where the service worker registers a listener for file downloads and automatically saves the file in one of your cloud folders with an API call, a post request with the file in the HTTP body. In our example, the service worker is listening for events on the browser side of things, but like we said, it can also communicate with other parts of the extension, like those running in the tab's renderer process on the web page side of things. This leads us onto the content script. The content script is a JavaScript file that gets injected into web pages the user visits, given of course those web pages have been declared in the manifest. The content script is executed inside the renderer process on the main thread where all the action happens, the same thread that the web page uses, executing on the same JS engine, but running in a separate JavaScript execution context. As we've seen in the previous project, this means content scripts cannot directly access variables or functions defined by the page, and vice versa, stopping malicious web page content from confusing our content script, and also in reverse, stopping third-party content scripts from doing something mean and evil to the web page. But the content script does have access to the DOM. It's kind of why we put it down here in the first place. This is done by V8 context bridging in Chromium. Basically, the renderer safely injects a reference to the live DOM into the content script's sandboxed execution environment. This is so the script can interact with the DOM without gaining access to the page's JS environment. Think of it like 2 people, the web page and one content script, although we can have multiple content scripts, both writing on the same whiteboard, which is our DOM. And it's Blink, our rendering engine, which provides the underlying C++ DOM object that acts as this shared whiteboard. Each person uses their own isolated notebook or toolbox. This is their execution context. They can both write, read, and change what's on the whiteboard, but not at the exact same moment. Since remember, the content script and the web page script execute on the same thread that runs the V8 JavaScript engine, which uses a single event loop to run one task at a time. Remember, WebKit/Blink is the rendering engine that embeds our JS engine. The scripts cannot see what's written in each other's notebooks or the tools the other has, unless they pass messages. Kind of like IPC, it's the same mechanism with listeners and messages. Ultimately, just 2 isolated execution contexts, or as Chrome calls them, isolated worlds. But since the web page and the content script are in the same thread, they can communicate. Cross-context communication using DOM events. It's a bit of a headache to understand, but here's another analogy. Think of our renderer process like a house, Blink as the infrastructure for a kitchen, V8 as an oven where we can execute/cook things, and our web page and content scripts as different cooks. Each has their own work area and can grab items from the DOM, our fridge. The scripts can use the oven, but not at the same time. They have to wait their turn on the thread. A couple practical examples might help draw this in. For instance, we might use the content script to detect and autofill login forms on websites. Or going back to our previous service worker example, the content script might inject a button to the page, a save locally and to the cloud button, which sends a message over to the service worker, letting it know to save locally and to the cloud. This leads us perfectly into the next part, all about this communication between the components. Since the content script is way down here in the renderer process, it has no direct access to sensitive Chrome APIs like tab management, Windows, history, downloads, or the system. These high privilege operations must be communicated and carried out by the service worker via Chrome's IPC messaging system, which, just like Electron, Chrome provides us the easy to use APIs. And it's worth noting, while we do put the content script in an isolated world, it's still sharing the same thread as the untrusted web page, and so a sophisticated attack could exploit this context isolation. So having the service worker be the authorized component reduces the surface for attack. The service worker can ask questions like, is this requested action allowed by my logic, and is the data being given to me both valid and safe? The pop-up is what we call this small window that appears when you click the extension icon in the Chrome toolbar. We define the pop-up HTML in the manifest, which can link to a pop-up JavaScript file inside. It runs in the extension process, but while the service worker gets a background worker thread, the pop-up runs on the main thread, of course also separate from the content script over in the renderer process. It exists as a user interface for our extension, where we might expose options for the user to configure, like choosing your preferred region in a VPN, or telling the extension when to act or on which sites. Since the pop-up is running its own process, isolated from the web, it's considered a trusted context, inaccessible by external entities, so we have no issue giving the pop-up full access to Chrome extension APIs, which go through Chrome's IPC channels to the browser process when we call something like chrome.tabs.create. So let's build and run a test extension. This is a practical video, so let's get practical. Remember, we said the one file we must have is our manifest.json, so let's add that inside a test folder, and we can grab a manifest template from the Chrome extension docs and paste it into our manifest. Next, let's add a popup.html, a simple h1 heading and a button. And as you can tell, our extension will be saving the current web page that we're on. Simple, but demonstrates a lot of the components we just went through. You may notice we also linked a pop-up JavaScript file, but first, let's not forget to add this as an entry point in our manifest. We're going to add the popup.js file and make it send a message to the service worker, the controller of our extension, which we've not yet added. Remember, the pop-up does have access to Chrome extension APIs like download, but it's a good design approach to centralize the logic in the service worker, especially due to the fact the pop-up is short-lived, meaning the process, including the popup.js, is killed as soon as the user clicks away. So in this event-driven setup, we'll use the API to send a message like download HTML from our pop-up to the service worker. That's what this chrome.runtime.send message is doing. You know the drill now. Add a service worker JS file, and in our service worker, we'll add a listener for that message using the same messaging API. Then we'll forward it on to the content script who has access to the web page. That's what this chrome.tabs.send message does. And instead of download HTML, our message will be get HTML, and we'll add this service worker entry point to the manifest file, new content script JS file, and this will listen for the get HTML message from the service worker and send the entire page's HTML back as a string with the message send HTML. And yes, you guessed it, we're gonna plug this into our manifest file and let it run on all web pages. From there, in the service worker's same listener, we check for the send HTML message, which will extract the HTML from the message and trigger the download. We use the chrome.downloads API, which uses the machine's file system underneath to save the file locally. And this is fun. Remember the blob stuff from Project 4? Well, here it is again. The blob wraps our HTML string into a file-like object with a URL. Since the Chrome extension API explicitly tells us the download function needs a URL, it doesn't do HTML strings. So that's all the code. Last thing is to give the extension the correct permissions. So back to the manifest one last time. We'll also update the name and description for good measure too, and remove the icons since it's just a quick test app and pointing to files that don't exist usually breaks things. Developing done, it's time to test our extension. We head over to the Chrome extensions page, enable dev mode, hit load unpacked, and select our folder. And by the way, I'm receiving a message from future you. They said if you get any errors, you're debugging, or anything doesn't work as expected, refresh the extension, refresh the tab, or restart Chrome. You'll be surprised at how often that fixes the problem. You can also check out out errors in the extension page, and open up logs from the service worker, logs from the pop-up, and find logs from the content script in the regular DevTools console of the tab, since of course the content script is running in the same renderer process as the web page. Finally, go to any web page. Since we're not downloading the JS or CSS, a pure HTML site will be a good example, like the first ever website created, which we saw in Project 5. Hit download and be amazed at something we could have accomplished in just 1% of the time by pressing Command S. And now you know how to make a Chrome extension. So lower level stuff done and Chrome extension architecture understood with a real example. Let's now intro our app, a great opportunity to dive into the programming side of things, because instead of music features in a text editor, we're doing something more universal like web scraping and using APIs. We'll break down the app into 3 main steps. Step 1 is to insert our button into the YouTube webpage. Step 2 is to fetch the video transcript when a user clicks the button, and step 3 is to pass this transcript to our good old GPT worker droid, get our summary, and print out the result in our little sidebar button thingy here. There's a few more technical aspects, like watching for users navigating between videos to handle the state of our button, different browser layouts, error handling, and all that good stuff. But that's a pretty accurate overall flow for now. First though, a bit of the infrastructure and code design stuff.
Hello, Webpack, my old friend.
Webpack, our module bundler. We're again using Node.js for development, our project scaffolding, to manage dependencies and run our build tools like Webpack and Tailwind that rely on the Node runtime, and more on these tools in a second. So we use Node for the development, but the output is just plain JavaScript, HTML, and CSS that runs directly in Chrome's extension environment in the browser. So we'll tell Webpack to put our bundled output in the public folder, similar to our dist folder in the last project, separating our source code from the build output, a common engineering practice that keeps the project organized and avoids cross-contamination of source code and build code, making deployments easier and safer. So when we test the extension, of course we'll be loading the public folder, whereas in the test example earlier, we developed and loaded the public build code directly. And before we take a look at the actual Webpack file and the rest of the configuration, it's worth pointing out this term module, which ties into a larger concept called modular programming. We mentioned modularization in the last project while looking at the Chromium code package. To be clear, modular programming is a software design approach that basically focuses on separating different functionality into independent code modules, each with distinct responsibilities. For example, in Amazon, a modular approach would separate features like the shopping cart, payment processing, and user reviews. Then we can reuse those modules in other Amazon services like Prime Video or Amazon Luna. Here's another example that includes hardware to better demonstrate the value in modularization. Parmalucky is the creator of the Oculus headset, coming up in Project 9, and now working on military tech.
For example, imagine we deployed a bunch of these glasses and they had the laser filters built in from the start. Now imagine that China shifts their laser frequencies 10 nanometers so that it bypasses that filter. Imagine if I had to just replace all my AR glasses. That's not acceptable, right?
Right.
So everything on this system is totally modular. So what would happen is if they shifted their laser weapons, we would just give people a new mission shield. Now they're all set. And notice how that's a replaceable module there?
Mm-hmm.
I could just unscrew this and replace it with a new part. Everything on here, I can repair in the field with a field repair kit.
And at a lower level, this modular approach manifests in different folders like we have for our build output and source code. Within our source code, we have a components folder for all the UI related elements, a separate file or module for working with the video transcript, and another for interacting with OpenAI, all with clear defined responsibilities, an important factor in writing clean code. Diving even deeper, this code approach helps with writing tests. When each module has a clear, well-defined responsibility, it's much easier to write focused, meaningful tests, while removing other modules that are not the focus of the unit under test, rather than having one big jumbled mess. Better codebase readability, product reliability, faster shipping, and more stakeholder value.
What's your biggest regret in life?
Not providing enough shareholder value.
Here's an example of unit testing I put together, the kind we do in Fang and other software companies. Writing code is fun, but just know, for every line you write, there's a corresponding test waiting for you around the corner. Traditionally, there are 3 levels of testing. Unit tests that check one function in isolation, integration tests that check how multiple modules work together, and end-to-end tests that simulate the whole system the way a real user would. Here, we're seeing an example of a unit test where our one file has one responsibility, and in the same
same code package, we can easily add a corresponding test file with test cases for every possible outcome, good and bad. Modular programming also goes hand in hand with object-oriented programming, another foundational concept in software design. I assume most of you watching may be familiar with OOP, but a quick mention and refresher regardless. OOP is a programming model that structures code as objects which can contain data and actions. Basic example, an animal parent class with dog and cat child classes. Okay, pretty easy. That was one type of inheritance, a cool feature of writing code in an object-oriented manner. More practical example, a user class will store profile data like name and email with methods or actions like login and logout. And in our modular app, another object like the user factory will be responsible for creating instances of this class, pulling data from the database to populate it, a common type of design pattern. And so that's a brief introduction into two design paradigms at the core of writing and organizing clean code, not to be confused with architectural design patterns which focus more on organizing the application as a whole and the larger technical components inside. And we'll see a lot more of this in the mobile application project coming up next. So let's make sure we design our code in an object-oriented manner, keeping things modular, making our code base easy to extend, easy to test, and easy to maintain as the system grows. In Node.js, every file is a module. Whenever we export a module, another file can import it. So in our Webpack file, we export a module containing all of our bundling instructions. Then when we run Webpack, using the command line for example, the Webpack library pulls in our exported module and gets to work. Let's check out some of the instructions we put inside. Let's start with the entry points. This tells Webpack where to begin building our dependency graph. Webpack starts at these entry files and follows every import, mapping out every dependency to include in our final bundle. This can be other modules or files, as well as third-party libraries. In our case, we have two entry points to our app, the content script and our pop-up. A rule of thumb that can help is to think of all the separate contexts in your extension. They're unconnected modularly, not sharing any imports, so each will need its own bundling or its own output file. And the output field in our config defines how and where those bundles are written. As you may have guessed by now, I'm a big fan of TypeScript. Unfortunately, that means an extra step when building our application. Regardless, Webpack always runs our module.rules on every file it encounters. So when it sees the TS extension, it checks the loaders for how to handle this file, as well as React TSX files. So a loader in Webpack is a transformer, some tool that pre-processes these files like TypeScript, CSS, and images into plain JavaScript modules so they can be bundled. Let's now take a second to understand how React works. TSX is just the TypeScript version of JSX. JSX stands for JavaScript XML. It's an extension of JavaScript that lets you write HTML-like code directly inside JavaScript to build UI components in the React framework. It's basically just an easier way to do everything in one place, rather than writing HTML and adding a JS script tag pointing to another file. Although don't be mistaken, that's still the fundamental structure it will take when compiled by the loader. But using React and writing in JSX is just a smoother developer experience once you learn how. Plus, React provides a bunch of useful APIs and things called hooks that make life a lot easier too. So to handle these files, we use the TS loader, which compiles both file types to JS. And we also define loaders to handle our CSS files. Fairly straightforward, so I won't bore you with the details on screen for that one. The resolve section tells Webpack which file extensions to look for when automatically importing modules. Just to make life a little more bearable, nothing too crazy. Next, this plugin section. Plugins are different from loaders in that loaders transform files during the build process, whereas plugins extend Webpack's functionality to perform some task. For example, this HTML Webpack plugin. It runs after the loaders have processed the files before the final output. So at this point in the build, our popup.tsx has been processed into JS along with all its React dependencies. But since TSX and JSX get compiled to JavaScript, we need a way to inject this popup JavaScript file into the popup HTML file to create our extension's popup menu. So we provide a bare bones HTML file called index.html in the source code folder. The plugin takes that template, sees the output path as the public folder, and proceeds to put the processed file in that folder with the name popup.html. But before outputting the file, Webpack injects a popup.js script tag based on our chunks field in the plugin. This field refers to one of our entry points from earlier, making the config more automated than entering popup.js in the chunks field, since based on the output, Webpack knows it will be linking a popup.js. Altogether, this means we don't have to manually update script tags in our HTML to match the bundles. Webpack makes sure the correct scripts are always injected automatically, even if file names, extensions, or chunk configurations change. And finally, we have one more plugin, and this one brings up some interesting points on the security of our extension, an important factor in any piece of software. First, let's explain how and why we use the define plugin, and then some potentially more secure approaches. The define plugin runs after the loaders as Webpack passes through our JS code. The plugin hooks in at this step to replace any identifiers with the actual values defined in the config. A simple find and replace. The good side of this approach is we do not hardcode our open API key or any other sensitive information in the codebase, and instead we use a .env file. This is a simple text file where we can store variables that should be kept secret, separate from our source code. Then we can load them into the Webpack config file using the .env package, which makes those variables accessible in Node's global process.env object. The reason we do this roundabout effort is because when we said all files are modules in Node, more accurately, all JS files and a few others like JSON are modules by default since Node has the built-in loaders to process them as code. .env is just a text file, so this env file we keep separate. We don't upload to our codebase like our GitHub repo, and instead load it only at build or runtime on our machine or cloud platform. This prevents us from any issues such as committing our keys to our repo, which even if the repo is private can still result in disasters. However, on the negative side, this doesn't conclusively prevent the client from seeing our key. Think about it. Our current approach will replace the string identifiers with our key, which will be included into the JS bundle that will go into our output folder, and this will be loaded into Chrome. This means anyone using our extension will be able to find our key, even if everything else has been minified and obfuscated. We could get around this with a bit more work, setting up a backend server so our server has the key and we the client and our extension make the call to the server. The server forwards the call to OpenAI and returns the response to us. But as you can see, there's no way to truly make it impossible to access, just increasing levels of security. But since this is just a prototype project for individual use, I'm not uploading this to the Chrome store just yet. It's for our learning and the love of building cool stuff. We don't need to worry about making this app a black hole event horizon right now, but at least we're aware of the situation. And so that's our Webpack config. We're bundling code, structuring our app, and putting together all the dirty nuts and bolts that keeps things ticking. And if you manage to follow all that, even at a high level, then you're in a pretty good spot, I'd say. Next up is the feature logic. Time to make our extension actually do something useful. Let's start with manipulating the DOM to insert our sidebar button thing. And since the content script runs with access to the DOM in the web page context, it will be the perfect place to do all things user-facing. At the heart of our content script is the observer video changes function. It's like our main function where code execution begins. A bit of background: YouTube is a single page application, meaning it dynamically updates content, replacing only parts of the DOM it needs to without reloading the whole page and updating the URL with JS. Great for users, a much faster experience, but tough for developers to detect new video loads. Our approach is to add a mutation observer object, basically just a listener for changes in the DOM, detecting when a user navigates between videos by watching for updates to specific elements, and as we define, their children too. We're taking a bit of an inefficient brute force approach by watching for changes in the entire HTML body, but it works fine because of our handle video change function that gets triggered. So let's see what this function does. First thing to mention, in our manifest, we define that the content script should only run on the YouTube domain. So in our actual content script file, we can go one level deeper and check that it's a YouTube video page. To do this, we use the window object, which we're pretty familiar with by now, part of the browser's web API, a set of interfaces allowing us to use JavaScript to interact with the web page environment. So we use the window API in the isYouTubeVideoPage function to check the query string of the URL for the letter V, followed by an equals sign, indicating a video page. If it is indeed a video page, we make sure the unique video ID is a new one, avoiding the issue we mentioned earlier where the DOM may change for some small page update, but the video stays the same. Great, so at this point, where our red arrow is, we know for certain we have a new video to handle. In that case, we can simultaneously fetch the video transcript and video title, both functions from our transcript service, which we'll look at next. Finally, in our content script, if we manage to get these two items successfully, we have everything we need for our summarizer to work, so we can be confident that it's okay to inject our sidebar element into the page. We could put this button wherever we like, make it as big as we want, and give it the most abominable design you've ever seen. Instead, let's keep our sanity and put it here on the right side of the screen above the related videos. If we inspect the element on the page, we'll find the parent element of this sidebar of related videos is conveniently called related. We'll wait for for that element to appear using our custom waitForElement function, and once the related bar has been inserted into the DOM, we'll call injectSidebar. I'll skip over the waitForElement function, but essentially we use another mutation observer to watch the DOM for our related element with a timeout using TypeScript's promise-based system. And just a tip, waiting for the specific element this way will be a lot faster than waiting for the whole page to load with something like window.onload. So related element loaded, we call the injectSidebar function. First, similar to the video ID, let's check if we already have our Summariser sidebar. A YT Summariser sidebar container I've decided to name it. If the element does not exist, we're going to create it in this if block. We'll create an empty div DOM element for now and add it to the related content element in YouTube we passed into the function as the parent element, prepending our div to make sure it's right at the top. Then we do some React work, creating an entry point that connects our React component tree, which is just one, our Summariser button, to the real DOM in the browser. Let's break that down. In React, the component tree is the hierarchy of components that make up our UI. At the top, you have the root component, and inside it are nested children, each responsible for a piece of the interface. Each component is like a small Lego piece. For example, a button can slot into the navbar, which slots into the header, and we can reuse this button piece elsewhere too. Instead of manipulating the browser DOM directly, React builds a virtual DOM, an in-memory representation of the UI. To be specific, in-memory as plain JavaScript objects in V8's heap memory. When something changes, React calculates the difference between the old virtual DOM and the new one and applies only the minimal updates to the real DOM. This makes updates more efficient and avoids unnecessary reflows/repaints of the whole DOM in the browser. So when we set up our entry point, we're telling React, here's the element in the real DOM, mount our component tree here, not necessarily the root of the HTML, and manage it through the virtual DOM, keeping everything in sync with the actual DOM. So after creating a React root with createRoot and attaching it to our empty Summariser div, our real DOM container, we then call render. The sidebar component we pass in becomes the root of the React virtual DOM tree, which React then mounts and updates inside that container. All that in simple English, pretty button gets injected into YouTube page. Now we're yet to cover building this button, and I'll avoid going into it too much. It's a lot of React, CSS, styling, and HTML. We do things like manage the state of our button, whether it's closed, open, or loading the AI summary. We also have code for calling our GPT worker droid to give us that summary, code for animating our button, code for showing a loader circle, and code for displaying the AI summary in a user-friendly way. As always, the entire code package is there on the Patreon, along with the tutorial and an example of the web scraping data, which we'll see in the next step, so you can play around with it and see how it works for real. Though I will mention one thing that could save some of you a lot of painful debugging hours when making Chrome extensions. In our extension, we use Tailwind CSS. It's a CSS framework that comes as an NPM library. Tailwind provides pre-designed style classes for direct use in HTML. We call these utility classes. For example, I can easily make a button in HTML and give it some Tailwind styling, a blue background color, directly in the button tag in the class attribute. Or we can do the same with the border or anything else you can imagine. I like this approach over the traditional workflow because it's easier to manage in my opinion. We don't need a separate CSS file and we can easily make edits on the go. As for the Webpack build process here on screen, I'll avoid going into detail on that. We've seen a lot of building and understand it quite well for different modules. It's there if you want to read into it, but it's not the point right now. Instead, I want to explain again how as engineers we face problems, suffer greatly, and find solutions. So I made my button and injected it into YouTube, but for some reason it was missing things, like this beautiful black border. After a bit of debugging, I became a DevTools power user and figured out the issue in this heap of colorful junk. Essentially, YouTube styling was overwriting my own, defaulting borders across the page to 0, as you can see across the whole platform with these borderless buttons for example. So this issue may seem obvious in hindsight, but figuring out why something isn't working isn't always easy. So practical software engineering tip from when I first started on the job, straight from my FANG tech lead, is to be able to reproduce the error. Then you can test your assumptions and play around with possible solutions. In this case, the issue was consistent on every button injection, so I only had to load my extension into the browser to reproduce the error. I tested my code outside the browser and it worked perfectly. So the assumption was that in the browser environment, something wasn't quite right. If I deleted this border 0 CSS rule, which we can do in DevTools since it's our browser running client-side code, then the border on our button would come back. Of course though, messing with YouTube CSS styling isn't a viable long-term solution. The actual solution was inline styling. It's another approach to CSS styling, similar to Tailwind, but built into HTML itself using standard CSS language. And more importantly, it has a higher specificity in the CSS cascade than our Tailwind or even YouTube's overriding styles. So we use inline and get back our beautiful black border. And quick mention, in reverse, we don't want our styling to infect the entire page. When using Tailwind, we add an entry CSS file with the directives we want. There are different directives for different purposes, but these @Tailwind directives tell our build pipeline from earlier which parts of Tailwind's full collection of styles to generate and include in our final CSS. Main point here is be careful with using the base rule when working on Chrome extensions or with the browser plugins in general, especially when the Tailwind docs might just blindly direct you to add all three directives. Anyway, first world front-end developer problems aside, we have this button ready to roll. Let's move on to step 2. Step 2 is the heart of our extension. If we lay the problem out in a first principles approach, we know a lot of YouTube videos are diluted, and our solution is to summarize them with an LLM. So of course, it only makes sense we need the content of the video to do just that. The most accurate approach would be to take the video, maybe we could download it, and code out a pipeline to pass the video frames as images to a model like GPT, as well as using an audio transcription model to extract the speech before combining both streams for a coherent summary. We'd also need to build out some frame sampling logic to avoid brutal fees, or use a model like Gemini Pro from Google who handle the logic internally. Either way, as powerful and accurate as these solutions may be, it's pretty costly and a lot more timely to build than our solution. And to be honest, less fun and less hands-on. The more pragmatic alternative is to grab the video transcript. YouTube provides it and it's surprisingly accurate. Unfortunately, we lose the visual element. However, it turns out from using the tool that pretty much no meaningful context is lost and the summaries are still perfectly accurate. What's even better is that we don't need to use any behind-the-scenes API since the captions are available right here on YouTube's front end. Although the same caveat still applies. YouTube will continue to put up protections and developers will have to continue to find workarounds. Continuing with our modular programming approach, we'll put all this logic in a file we can call transcript service. The file has two exported functions called getYouTubeTranscript and getVideoTitle, and we've actually already seen these in use in the content script before injecting our sidebar button. So first, let's quickly check out the getVideoTitle function, not strictly necessary for the summary, especially if there's clickbait, but it might add some useful context. Here we fetch the raw HTML of the entire video page using the fetch web API. Then we convert the HTTP response body into a plain text string where the text method automatically uses the encoding specified in the HTTP response headers. We then pass the string with regex to find the title tag. Regex, short for regular expression, is just a sequence of characters defining some search pattern. We go for the title tag. It's required by HTML law, there can only be one of them, and YouTube sets this page title to the video name. And so that's all the code to handle fetching the video title. Now for a bit more of the messy web scraping stuff. We'll go through each function in order, but for a quick overview, this getYouTubeTranscript function starts by pulling the HTML of the page like we just did with the video title. In the HTML, we find the captions as a key pair of language and URL. So we sort by language and fetch the captions which are in XML format. We parse, clean and format the captions before converting them into a readable string, which we'll eventually be able to pass to our AI for summary. First things first, we're going to pull the entire page HTML, convert it to a parsable string, again using the text method. Doing this in a node environment in my terminal, you'll see we get the entire page HTML and we can see the title tag we grabbed from the getVideoTitle function we just went through. Hopefully you will remember seeing this HTML response from project number 4, where we found the streaming data field inside, a property of the YTInitialPlayerResponse object. Well, as you can see, there's also a captions field, only one of these specifically in this style with the colon. Just like the streaming data field contained all the information about the streaming URLs, formats and encodings, the captions field contains all the data about the captions, all the available languages, the URLs of where to find the transcript texts, and other things too. And fun fact, to bring our knowledge together, we can actually test this code out right here in our DevTools console also, running the following line, fetching the page HTML. And you'll notice we don't need to enter the page URL manually like we did in the code. Since this DevTools JavaScript code is executing on the same JS engine and context as the web page with access to all the browser APIs, we can just use the window object to access the URL instead. And main point here is that no extra permissions are needed since the request is going to the same origin, meaning the same protocol, domain and port as the current page. You'll see if we fetch a different website, say google.com, the browser blocks JavaScript
JavaScript from accessing the response data.
That's due to CORS policy, cross-origin resource sharing, a browser security mechanism without which any site could maliciously run JS, fetch your data from other sites you're logged into using cookies or session tokens, and bankrupt you for all your V-Bucks. So side quest over, we'll take the string HTML and split it at this captions point. If the video has no transcript, this field will not exist, and the button would never inject. If the captions do exist, our new variable will be a list of strings which elementary math tells us should have a length of 2, everything before the captions and everything after. Focusing on the second string, usually the next item in this massive object is the video details, so let's chop that off the other end, leaving us with just the captions object. Using JSON parse to turn the string into a JavaScript object we can work more easily with. And one thing we need to know is the captions for each language are not part of the HTML. They are loaded from a separate URL. Why? Well, we write modular code and so do YouTube. Loading the transcripts in from another source keeps things clean and allows them to be loaded in asynchronously, making the page load faster. So next, of course, we want to know where the transcript URLs are and which language each URL represents. All this information is inside the caption tracks field, but this whole thing is still a string with information we don't need. So for our extension, let's create a new object, one that makes sense for us with only the necessary data, which will result in the list you see on the right. Here's another great example of how TypeScript gives us structure with types over plain JS. We can create a caption track interface for our new variable. As you can see, interfaces define the structure and shape of an object, including all the properties and methods. And so straight away in TypeScript, we can see how the final result of this getCaptionTracks function should look. Even people new to the project will easily understand the returned item will be a list of these caption tracks, language and base URL without troubling themselves with the logic inside the function. Big help when navigating giant code bases in the real world without the time to understand every line. Anyway, for us the logic is easy. We build this object by looping through each one of these caption tracks and mapping the URL and language to our new object. And all the code is commented with useful tips. So for example, above we can see exactly what we're working with. So if you're looking at the code, don't forget to read through the comments because it will most likely help. And that's getting the caption tracks. A nice bit of web scraping fun for a big first step in fetching the transcript. Next, we sort the captions by language, and we've set the function up so you can pass in the language you want, where this choice will be sorted at the top of the caption tracks list. The function will certainly look messy to newcomers, but the main points you should be picking up on are not the syntax, but the logic behind the code. In many cases, YouTube auto-generates the captions and names the language as such. English auto-generated, for example. So in our function, we make sure to always check if the desired language is included in our caption track language field and not only equal to. This function also allows us to easily develop more features in the future, like allowing a user to select their language. For example, you could make this a freemium extension where the language selection is a paid feature you select in the pop-up HTML. But I'll leave that up to you and we'll go with English. Sorting places the English caption track object at the top of the list. So back in the getYouTube transcript function, we can just take the first item, 0 indexed. And good news, even if there are no English captions, we'll still take the first language and still get an English summary later due to our prompt. Okay, so we've got the link to the English captions, we're halfway there. If you take this link directly from the HTML and try plug it into the browser, you'll get a 404. Remember our HTTP response codes? This means not found. That's because the base URL contains a lot of encoding. It's a string inside a JSON object, inside JavaScript, inside HTML, being passed over HTTP. On top of that, it's a custom design choice from YouTube in how they handle each layer of encoding. And in our code, we deal with unwrapping it all. I don't want to spend too much time on this, but I want to make sure we really understand encoding. I think this final example will make us experts. We fetch the HTML over HTTP first, decoding the binary using UTF-8. We've seen this in a few projects now, so our starting point and step 2 should be pretty clear. In step 3, our starting point is the entire HTML string. The URL we want is inside two things. First, it's inside a JavaScript object, our YT initial player response, and secondly, inside that object as JSON data. And sometimes we even have the JSON inside a JavaScript string and the escaping doubles up, case A and and case B. We're dealing with case A. We have JavaScript string escaping on one layer for keeping data valid inside a script tag and JS string literals, and JSON escaping to keep JSON strings valid within the JSON object itself. Not only that, but we can also include Unicode escape sequences. Remember, just a unique code that represents some symbol, like \U0026 represents an ampersand. Inside the JSON data, the URL of the captions uses an ampersand. YouTube knows this URL will be carried inside JS. To keep things consistent, the backslashes in the JSON must be escaped so the JSON survives being written as JavaScript. So by the time the URL reaches wherever it's going inside YouTube's page, it only needs to be JSON decoded, just as we did in our code using JSON parse. And this will conveniently work internally in YouTube after the JS engine passes the script, or for us pulling the raw HTML before parsing. Then in step 4, we've dealt with the JavaScript and JSON layers, and now we go one level deeper, the actual URL inside the JSON. Here we run into a different encoding system called URL encoding, designed to prevent URLs from breaking. To be clear, URL encoding isn't a codec or binary encoding, it's a substitution scheme. Reserved symbols are kept as literal symbols when used in their special roles. But if you want them to appear as plain data, you encode them. For example, if we want the ampersand as a query separator, that's fine, we leave it as it is. But if we want it as plain data, like some user submitted value, then we %encode it. This may feel a bit backwards, but the goal was to keep URLs relatively human readable. Luckily for us, the URL is already %encoded by YouTube, and we don't need to change this. Remember, we are going to use the base URL to pull the actual transcript text. The URL being encoded is what our fetch function wants. It's the language our browser speaks, so no need to change anything. So yeah, if you see something like %5c, 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 U0026, you know this is actually just an ampersand symbol. And after dealing with all the headache of encodings, we can now move on to see what the base URL captions link actually leads us to. What you're seeing here is the transcript in XML format, extensible markup language. Similar to HTML, it's a markup language, meaning it uses tags to define structure and instructions on the data inside. While HTML is mostly for displaying data in the browser, XML is for moving data between systems, like servers and apps. So this XML is how YouTube decided to store the captions. We could plug this directly into our OpenAI model, but I think it would be better to clean it up first. We're already giving the poor model so much to do. So getXML transcript is the last major bit of action in our getYouTube transcript function. We'll pass in the base URL from the caption track object of our desired language, then immediately fetch, which performs a get request. We'll take the response object and call text to get the raw body of the HTTP response as a string. Then we pass the string into XML using a DOM parser. Since XML is a text-based format, it only makes sense that we go bytes to string to XML. Now we can work way more easily with this XML DOM-like object inside JavaScript, navigating the tree with methods we've seen before, like grabbing elements in the tree by tag name or attribute. And that's exactly what we'll do. First, grabbing every tag named text in the XML document object, which is basically all the tags in the transcript. We'll convert every single one of these text nodes into our own TypeScript object called transcript item using another custom interface, and then return the full list of all transcript items. So end result, a transcript items list that looks like this, where each item gives us the caption and time period it covers in the video. Better than working directly with the XML and trying to pass that around with no guarantees as to what's inside. So back in the getYouTube transcript function, we've managed to grab our transcript, and for each of those timestamped transcript items, we'll call a helper function to convert the seconds to minutes. This will make the end output of the AI summary more user-friendly. Then final bit of cleaning in this step 2 transcript part is calling convert to string, where we loop through each transcript item and join them into one neatly formatted string our poor AI can have the pleasure of reading. And I'll leave these helper functions for those interested to check out in their own time. And with that, we can safely say transcript service complete. We scraped, we fetched, we cleaned, and now it's time for the ball. So in step 1 in our content script, we observed for video changes, upon which we inject our button into the YouTube page if we can successfully fetch the video title and transcript. Of course, we just went through this in step 2, our transcript service, also in the content script side of things. Now we have both items, our button will inject into the page. And so when someone clicks our big beautiful button, the getLLM summary function is triggered, requiring the video title and transcript. I'll keep it brief since it's really just one network request / API call at the heart of it. There's There's a little prompt I perfected through trial and error, as I'm sure you can tell by the explicitness of the message, where first thing we do inside our function is plug the video title into the prompt. Then comes the API call, where we include our API key in the header of the post request. Of course, we also turn the JavaScript body of our request into a string of JSON, since we know all too well by now that sending around JavaScript, an executable coding language, to other computers and servers is not the best idea in the world. So most modern APIs will accept JSON. Reminder, JSON is a subset of JS, keeping the structures like objects and arrays, but stripping out all the executable parts like functions, leaving us with a nice language-independent transport data format. JavaScript stores strings in memory as UTF-16, so the fetch API will hand the string to the browser's networking layer, which will encode to UTF-8 by default, as defined across web standards, put it in the request body, and send it down the wire. Server gives back the summary which we extract, and back in the button where we called the function, all that's left to do is display the summary text on screen. And in general, it's very affordable. I was using the tool over a few days and spent $1.35 on 56 requests, averaging out to 2 cents per request, a small price to pay to save hours on clickbait if you ask me. And we can also see the full list of available models on OpenAI, plenty to choose from. And there we have it, our very own super-powered, clickbait-avoiding Chrome extension tool to start downloading information into your brain like Neo from the Matrix.
I know Kung Fu.
Or you can productize it, put it on the Chrome store, and try to make some cash. We didn't cover the pop-up pathway, but after going through the content, I'm sure it will be a breeze. The main thing though is that we've now taken a deeper look at practical software engineering, build systems and app infrastructure, programming, testing and design approaches, all applied on top of the web browser framework which we know inside out. Built using Node.js plus popular libraries like React and Tailwind, and a lot more core computing concepts, all while building something actually useful. On top of that though, I hope this project has reinforced how sometimes things can get messy, and we just need to have the willpower to find a way to get things done amongst the overwhelming mess some of us have decided to base our careers around. And with that, I'm happy to announce Project 6 complete. Project 7 is a great opportunity to really solidify many of the concepts we've looked at so far. We'll be building a native iOS app using Swift, a language designed specifically for Apple platforms, a good shift away from our web work, and a nice comparison point to our cross-platform desktop project. We'll continue focusing on good programming and software design, and start looking at architectural design patterns we can follow, as well as more multimedia processing, since our app will work with video and images. Specifically, we'll be building an iOS app. That means iPhone, iPad, and iPod Touch if by some miracle you still have one of those kicking about. The app lets you upload images or videos from your photos library, then you can save an edited version in the style of a 90s VHS camcorder because we're so hipster and cool.
What band is this?
You've never heard of it.
And of course, we'll take the approach of looking at the fundamentals, so you can take what we build here and use all the same ideas to build your own iOS app. You can even upload it to the App Store and start getting downloads. You can make it free, ideal for sprucing up your CV, or make it paid and let strangers tear down hundreds of hours of work with one savage review. So let's not waste any time. We want to build a mobile app. We know how operating systems work. It's software that runs on the machine, managing hardware and software resources as well as program execution. Things like input from the keyboard or sending network requests out on the physical network card. We have open source operating systems like any of the Linux family, including Raspberry Pi OS, or closed source systems like Windows by Microsoft and macOS by Apple for PCs, or iOS for iPhones and iPads, touch-based and optimized for Apple's ecosystem. The iOS platform, like most of Apple's never-ending product line, prioritizes this seamless integration between hardware and software, giving the user a smooth experience. A core mission from the start.
Screen. Now, how are we going to communicate this? We don't want to carry around a mouse, right? So what are we going to do? Oh, a stylus, right? We're going to use a stylus. No. No. Who wants a stylus? You have to get them and put them away and you lose them. Yuck. Nobody wants a stylus. So let's not use a stylus. We're going to use the best pointing device in the world. We're going to use a pointing device that we're all born with We're born with 10 of them. We're going to use our fingers.
The system itself is written primarily in lower level languages like C and C++, with Objective-C to build on top of that platform along with Swift introduced in 2014. The Swift language is modern and fast, faster than JS and Python, although the syntax is a bit different from these popular languages, a little more verbose and a little less readable. Swift was designed to replace Objective-C as Apple's primary programming language due to all its shortcomings, and not just for use on iOS, but watchOS, macOS, tvOS, and all the rest OS, and for becoming more of a general programming language and modernizing existing Apple developer libraries like Core Location, which makes it super easy to interact with the device's GPS and location data, or adding new libraries like the SwiftUI framework released in 2019 for building user interfaces more easily, and we'll get our hands on that later. For developing native Apple apps, we can use Xcode, Apple's official developer environment, just like VS Code or PyCharm, but again centered and optimized around building Apple apps specifically. We can install it straight from the Apple Store, make a coffee, and come back when it's ready. The first thing you'll be greeted with after opening Xcode is this screen. Hit Create New Project. What's great is we have a bunch of templates to choose from, and immediately you can see the variety of platforms available. We'll be creating an iOS app, and even here there's a bunch of options. A Safari extension, Apple's browser like Google Chrome, or we can build on top of iMessage or any of the rest of the options here. Let's just go with the basic app template for now. There's a bunch of boring configuration to fill out, which as always is covered in the written doc on the Patreon along with the commented code for the entire app. The main point here is we'll be using Swift and SwiftUI, replacing the older Objective-C and UIKit. More on this later. Fill out the product name and everything else is pretty much optional. The Xcode editor will automatically open up the template app and you'll see this beautiful view. Welcome to the editor. On the left is of course your code editor area, and on the right is a device simulator giving you live updates on your app. We call this the canvas preview. Further left is the navigator, pre-populated with a basic Hello World template codebase. I'm sure most of you know what I mean by Hello World. If not, it's the classic program you write in any new language or system, printing the words Hello World just to make sure everything's working and feel a humble yet satisfying victory. In the navigator, you can also see we have some files for unit tests, which we've just seen in the last project. And you'll notice, despite the syntax differences, it takes the same format we call arrange, act, and assert. Hitting this play button, top left, just above the navigator, compiles and builds the app on your selected iOS device, launching a fully functional iOS device simulator. This is a runtime simulator, so our built app is literally being executed in real time, whereas the canvas in the editor is just a static visual preview. It runs just enough code to render the view, but not the full app runtime. With the simulator, we have a fully emulated iOS environment. We can tap and swipe, go to the home page, open maps, and all the rest, giving us a lot more control for development and debugging. We can build the app on here or on a physical device via USB or wirelessly. Pretty good. So we've got our developer environment up and running. Let's now run through the project structure and project files to understand the bigger picture before we go looking at specific code examples. Now we're moving up one layer in our software design levels table. In the last project, we focused on design paradigms concerned with the style and philosophy of our code, and we also touched on some design patterns. Now we're moving to structural/architectural design patterns, how the larger objects are all put together to form our entire system. Instead of making our project files and folders randomly, we'll be following the MVVM pattern, model, view, view model. Following a well-defined design pattern like this helps keep our code base organized, testable, and scalable, further modularizing responsibilities at one abstraction level higher than the code. So 3 main components. The model is responsible for all the data and application/business logic. This is the nitty-gritty side of things, where we'll be processing images and video, color schemes, and all that good stuff to get our VHS style effect. The view is pretty self-explanatory. It's responsible for building the UI of our app, and forwards business-related user interactions to the view model, like login button presses for example. Then there's the view model, less intuitive but still simple. It's the mediator between the model and the view, for example holding state variables like which media the user has selected, their image or video for editing. It also handles user input from the view and interacts with and updates the model, with the same communication occurring in reverse, fetching and formatting data from the model for presentation back in the view. Here's a simple coded example to solidify our understanding. Imagine a weather app. The model retrieves weather data from some API as the number of degrees Celsius. The view
model calls this function in the model when prompted by the view and formats the data in a user-friendly string, kind of like our last project where we tidied up the XML script. The view model then updates some state variable with the string value like current weather Celsius and exposes the variable to the view with this published attribute. The view automatically observes the state change and renders the new content on screen. Also, you can open the weather app to fake busyness when someone you kind of know walks by. Let's now see how this architectural pattern materializes in our app. What you see in front of you are our project files in Xcode. Let's go through them one by one. This VHS Effect top-level project file is an Xcode proj file, a format specifically made for Xcode, so if you open it up in VS Code, it will most likely look like gibberish. This top-level file is the root of our project and manages how the app is built. It keeps track of things like build settings, metadata, and a bunch of other general configurations used by Xcode. And let's not overcomplicate this. At its core, this VHS Effect.xcode proj file is just a text file, like our manifest in the Chrome extension or our package.json in Node.js apps. The info.plist also contains configuration, but more focused on providing instructions for iOS as opposed to an Xcode blueprint. The file is loaded by iOS at runtime to configure how the app behaves, including things like app name and version, supported device orientations, and app permissions like on our app will require photo library permission. Xcode might show you this in a user-friendly way inside the Xcode proj file, either way all just configuration. The readme I skipped over is just a markdown file, usually describing the project, how to set it up, and other important notes for developers. Now we get to the meat of the directory, the files containing the logic for our app. And of course you'll notice these are all written in Swift. We're going to study each one a lot closer, but for now let's stay on introducing the bigger picture. The VHS Effect app is the main entry point of our app, and it initializes the content view. The content view is the main and only view of our app, allowing media selection, previewing edited images or edited video playback, as well as saving the edited media to the photos library. The content view model is of course the view model of our app, managing things like state using variables exposed for the view to automatically observe and update. Like we said before, it's the middle layer between the view and the model. For example, after a user selects an image or video for editing, the view model keeps track of the state, which media the user selected, and calls methods in the model to apply the retro VHS effects before handing the edited media over to the view. This keeps the view clean and the codebase neat. The model we know carries out the work of our app, everything to do with applying effects to the media like changing the contrast and color and adding grain. Of course, the app would be completely pointless if we couldn't save the edited media, so the model takes care of that stuff too. And our final two Swift files are the image and video pickers. These are utility classes, kind of like helper functions which we've seen in practice before. If we had to bucket them, we can call them view components, since they pull up this page for media selection, which we call a picker, an overlay on our main view. We separate them out into individual files, image and video, again to keep our code clean and modularized, allowing the content view to focus on the main layout and structure of the page, which can then call the pickers when needed. Finally, we have our asset files, Xcode asset files, another file closely integrated into Xcode used to organize the app's assets, things like images, icons, colors, and other media-related resources in a structured, easy-to-use format. The main assets file is for our live app, included in the final build, while the preview is used only for mock data during design and development, things like placeholder profile pictures or sample product images that we won't have available during development. And that completes our project structure walkthrough. Before we continue looking at the app logic, let's get a grasp on using Swift and Swift UI. Although Swift is a general-purpose programming language, yes, primarily used for developing on Apple platforms, we can use it for other things too, like on Linux for example, writing CLI tools and servers, but much less common. Swift UI is a framework for building user interfaces with Swift in a declarative, state-driven approach. Let's break that down. It's packaged like a library. For example, we import just like we would anything else, but we call it a framework because a library is code you call to perform specific tasks, while a framework plays a bigger role. It defines the overall structure and calls your code within its predefined sequence of events. There's an inversion of control. And by declarative, we are back discussing a core programming design paradigm, a fundamental style of writing code within a programming language. The two most common paradigms are declarative, where we describe what the UI should look like based on the current state, and imperative, where we define the exact steps that should be taken to update the UI. Think of a language like C, way down by the hardware level, where we define exactly how to allocate memory and move values values around. This is a very imperative approach by necessity. Here's a short example in Swift. Don't worry so much about the syntax, just the overall approach. Straight away, we can see the step-by-step approach of imperativeness. Create the label, set the text, add a toggle, wire up a handler, manually update the label when the toggle changes. Compare this to the declarative approach, where we use the text and toggle objects from SwiftUI, and we simply declare the label's text as depending on the toggle's state and let SwiftUI take care of the updates. Basically, this is what I want, now go figure it out please computer. But it's worth mentioning, the very first thing we learn about computers is that they are input-output machines, and that input at the lowest levels is just instructions. We've seen in Project 5 in real depth how software and programs are just instructions. So really and truly, while it might be easier to write declarative code, the machine still needs strict instructions. And so in this case, and most declarative cases, we rely on SwiftUI or some framework to handle that imperative instruction layer under the hood. Remember, just increasing layers of abstraction that make it easier for us to express our ideas on the machine. So this declarative approach with SwiftUI was introduced as a replacement to the imperative UIKit framework, making it easier to build and maintain complex UIs by simply letting the system handle updates automatically as the state changes. The same declarative approach React uses. Remember our sidebar in the Chrome extension? We said what we want the UI to look like based on the state, whether it's loading the AI summary or has already fetched it, not the exact steps on how and when to update it. So that's Swift and SwiftUI at a high-level programming paradigm view. So Swift is the language and SwiftUI is the framework built on top. Just like JavaScript was our language and React the framework on top. Swift code, SwiftUI framework. JavaScript/TypeScript code, React framework. Python code, and as we'll see in Project 10, Flask framework. Dialing in on Swift will help us understand that at the core, most programming languages are similar. It's the reason job postings, junior or more senior, are usually open to candidates knowing at least one language, since even if the team develops in another, the core principles remain the same. So let's quickly run through this table of building blocks, which will help us understand the project code later. These larger object types in the first row, like structs and classes, are the larger building blocks used in most components like views and models, containing data and actions, also called variables and functions. Remember our OOP stuff in the last project. So these allow us to use Swift in an object-oriented programming approach. However, remember, it's how we use the language. So we could also use Swift in other styles like functional or protocol-oriented. And without getting too into the details, it should be mentioned structs and classes are pretty similar. As per Apple's developer docs, use structs unless you need some Objective-C interoperability. So we can make up our own structs or use existing ones from the standard Swift library or frameworks like SwiftUI and the older UIKit to build the larger components that make up our app. Side note, I've found Apple's developer documentation is pretty good and up to date, so that's always a solid source of info during your developing adventures. Protocols are a concept to keep our code structured and modularized. It's basically like an interface in TypeScript or an abstract class in Python, a blueprint for our objects to follow. For example, one protocol from the Swift framework is identifiable, which requires one property, ID. Again, they can be built in or custom defined by the user. Attributes are a Swift language feature.
But in the context of our application, it will mostly be SwiftUI attributes used.
These are special labels prefixed with an @ symbol that tell the compiler how to treat certain pieces of code. For example, the main attribute in Swift tells the compiler this is the entry point of our program, start here. Or the state attribute in SwiftUI, which marks a variable that holds dynamic data, allowing it to change over time and automatically trigger UI updates, like whether a menu is open or closed, or the piece of media the user selects in our app. This is basically the same as the useState hook in React. When the variable updates, React reacts by re-rendering the UI. And we use this in our button in the last project to keep track of a few things. Frameworks we've established, not unique to Swift, they are pre-built libraries to help achieve some functionality, providing us with the other building blocks we see in the table, like structs, classes, functions, and protocols to make it easy to work with that part of the system, like SwiftUI for user interfaces, core location, which provides easy access to the device's GPS and location data, or for us, core image, which simplifies working with graphics and image processing as we'll see. Functions we also know, a staple in any programming language, it's just a reusable block of code. And the syntax in Swift for functions is kind of similar to, say, Python or JavaScript, so that's good. And the last major building block in our Swift/SwiftUI setup are modifiers. Modifiers, specific to SwiftUI View components, are built-in methods used to adjust the UI by chaining the modification in a clean, declarative way. And that completes our foundation understanding of the SwiftUI Lego bricks, which we're now going to put together to build our app.
We have two major user flows in our app, image uploads and video uploads. The good news is we can reuse a lot of the logic, since of course an image is just one frame and a video is simply many individual frames in rapid succession. So we're either editing one image or looping through many images and editing each frame for a video. Today we'll be exploring the video editing pipeline. It's more complex than image editing, allowing us to cover more code, software engineering and computing concepts. To give us a guideline, we'll follow this map. It gives us a chronological journey through the app and the native Swift code that will be new to a lot of us. And this map is actually called a UML sequence diagram, a unified modeling language diagram. It's a visual representation commonly used in software engineering to display the structure, behavior, and interactions within a software system in order in a way we can easily digest without having to understand the lower level specifics like language syntax and libraries and all that boring stuff other teams or decision makers may not fully care about. So right before the user takes the first step in our diagram, they need something to interact with, a screen with buttons, also known as our view. We create this in our app's main entry point in the VHS Effect app.swift file. Like we said, the main attribute indicates the entry point, and it can be used on either a struct or a class regardless of the protocol. We create a struct called VHS Effect app, which conforms to the app protocol. The protocol, as we can see in the developer docs, requires a body that conforms to the scene protocol. So the app is the outer shell telling Swift this is our app, and of course there can only be one. The scene is a declaration that tells SwiftUI what kind of UI container to create. For us, we use the window group since we need a main window to handle our view. Another example is a document group for file-based applications. We define what goes inside that container, our view, while the system controls how and when to launch and manage those windows. Think back to our browser window in the desktop app Electron project. It's the same idea. So we use the window group scene type as the container for our view, and our view defines the user interface inside that window. Buttons, texts, images, and everything else you can think of to keep dopamine harvesting our users. So that's our main file, and worth mentioning, all these are protocols and structures coming from the SwiftUI framework, our framework for building the app. Alright, now back to our beautiful UML. The first action is for the actor or user to select the upload video button. We could have made one button, but I prefer this approach, because when the picker eventually displays, it's one media type, meaning we either see only images or only videos, neatly splitting the two flows of logic. This button comes from our content view, which we just initialized in the main file. Here's that file, clean code and commented. Specifically, our content view is organized using stacks, vertical, horizontal, or overlapping z-axis layout containers, kind of like div containers in HTML. For example, I can add a colored border to a stack. Remember, we call this a modifier, and you can immediately see the outline. Do this for all the stacks, and you get a good idea of how the front end is organized. And this is worth mentioning. Two lifesavers when it comes to software engineering. On the front end, adding borders, and on the back end, printing lines. Simple, but two debugging methods that have saved me time and time again. So be sure to add that to your software engineering arsenal. So back to these organizational stacks. Inside, we create a button. In SwiftUI, a button requires two things, an action and a label. The label we create is just another horizontal stack with an icon and some text. Nice and easy. The action will trigger the viewModel pick video function, and we now see our first component interaction in the declarative MVVM model. The view passing a user action to the viewModel. These two components are able to communicate because we connect them when we initialize the viewModel at the start of our content view as a private state object. This state object attribute creates the viewModel in a way that's owned by the view and automatically observed by the view for state updates, initialized once and maintains state despite view re-renders or full recreation. Specifically, when published properties of an observable object change, so these variables on the left in our content view model, the view will observe these changes and update whatever it needs to, all handled by SwiftUI under the hood. So our content view model holds the state, and content view remains a passive consumer of that state. That's what the pick video function does for us. View says, hey, the user tapped this button, I'll call the pick video function. View model says, okay, I'll update the show video picker to true. Cool. So at this point, the user has hit the select video button, we've updated the state in our app, and we know we need to react to this change by pulling up the photos library. That's what our video picker component does. In our SwiftUI framework, the way our view can observe these state changes is by using the $prefix to bind to a published property, the show video picker boolean. As you can see in our code, we do this on line 34. This binds the sheet's visibility to the show video picker property in the view model. When the variable is true, the sheet automatically shows, and when false, the sheet automatically disappears. Don't worry, I can read your mind. What's a sheet, you're asking? A sheet is just a view that slides up from the bottom, overlaying the current content without navigating away. Whatever we provide in the curly brackets is the content of our sheet. And it's worth mentioning, this binding we create with the $sign to the sheet is a two-way binding. The state variable can open the sheet, and if the user closes the sheet, SwiftUI handles writing the variable back to false. So inside those curly brackets, we provide the content of the sheet, our video picker component. This is our SwiftUI wrapper struct to the UIKit UI image picker controller class, so we're combining the two frameworks. This controller class is what we use to manage the screen view and user interface after rendering the sheet. The video picker class is a good showcase of how we can use UIKit in SwiftUI, as maybe you'll want to support older iOS versions, or the older UIKit structures may provide more features like customization and you'll want to use them then. Not uncommon for us in software engineering to need to bridge between old and new technologies, so it's good practice. So let's take a look at video selection with our video picker struct. First things first, the struct conforms to the UI view controller representable protocol. This is a SwiftUI protocol made to enable integration with UIKit view controllers. A view controller is part of UIKit's imperative approach, responsible for directly managing a view. We are bridging a gap by using it within our declarative SwiftUI content view. Think of it like this. SwiftUI is autopilot, declaratively updating our content view from state. UIKit view controllers are manual driving, imperatively managing the picker screen. UI view controller representable is the bridge that lets autopilot use those manual controls when needed. Eventually, our picker will need to send data around in our app, for example, to update the state with the selected video and also to close the picker. Remember, video picker is basically just another view, and in our MVVM architecture, we're communicating with the view model to update the state. So to observe and update state changes of larger objects, we use the observed object attribute as opposed to bindings to update and observe a single state. This tells our video picker struct to subscribe to the view model, which we initialized in the content view and passed into the video picker, and auto refresh whenever any of its published properties change. But you'll remember the content view also connects to the content view model. So why did we use state object in the content view and observed object here in the video picker? Well, since content view is the first place the content view model is created, it needs the model to persist for the lifetime of the app. If the content view didn't own the view model with the state object attribute, SwiftUI could recreate the view and wipe the state. For example, under the hood, SwiftUI might recreate content view like when the app goes into the background and comes back. The picker doesn't have this problem. It doesn't need to own or create the state. It's a temporary helper screen. We just need it to observe and update the state in the view model, so we use observed object for that. This UI view controller representable protocol requires two methods: make UI view controller and update UI view controller, which we don't use but must include,
and an optional make coordinator method. So two required functions, one optional. Make UI view controller, one of our required functions, the other we add with no body. So this make UI view controller is for us to return a type of UIKit view controller we want to show on the sheet. In our case, this is the UI image picker controller, managing the system to either take pictures and videos or select existing ones. So we instantiate the picker, assign the delegate, we'll get back to this, choose the media selection source, of course we'll choose the photo library. Alternatively, choosing something like camera will open up the camera to take a live picture or video. And then we can constrict this media selection to only display videos to improve the user experience. Pretty similar in the image picker, we just restrict this to images instead. Then at the end, we return the picker. So when our content view creates the video picker struct, SwiftUI sees that it conforms to the UI view controller representable and automatically calls make UI view controller, returning our UI image picker controller, populating the sheet with this view of the photo library. Okay, so making the picker sheet is easy enough, but what's going on here with this delegate stuff? Well, UIKit uses the delegate pattern, another software design approach, an object-oriented one. It's fairly obvious. The delegate pattern is one where an object, the delegator, hands off responsibilities to another object, the delegate. Here's a little diagram I cooked up. The delegator object, our UI image picker controller, doesn't handle events itself, instead passing off the responsibility, request, or action to a delegate object. In our case, that delegate object is the nested coordinator class, and the action functions are video selection or picker cancellation. Put simply, the coordinator is active when the UI video picker is on screen, ready to handle events. We'll take a look at what happens inside the coordinator to handle those actions and continue the logic in our app in a second, but we've actually already seen it. At the core, it's just a pretty straightforward content view model update. The final key in this pattern is the context, which acts as the bridge between SwiftUI and UIKit. In this UI view controller representable protocol, SwiftUI calls the makeCoordinator function on first creation of the video picker, stores the result, and injects it into the context, which is automatically passed into the makeUIViewController function. So of course, we can access that coordinator property inside the context object and assign it as the delegate of UI image picker controller. We're telling UIKit, here's the object that will handle your delegation requests. Have fun, don't throw errors, thanks and bye. It can be a bit confusing, especially if you're new to the Swift language, on top of which we are combining the SwiftUI and UIKit frameworks. But the main thing to understand is that we can wrap UIKit view controllers or other imperative and delegate-based UIKit components with SwiftUI protocols to make them work in our declarative UI framework. The how we do it, as we've just seen, can be a bit entangled. Luckily, the docs are pretty clear, and I'm sure there's plenty more examples online. So in summary, user presses the select video button from our SwiftUI content view. We update the content view model, observe the state change with our two-way $ binding, create the video picker, and present the sheet with the SwiftUI wrapper for the UIKit picker where it delegates events to the coordinator. So I promised you we'd come back, and here we are. Two actions our coordinator handles in two functions. Video selection with the image picker controller function, automatically called by UIKit when the user selects a video, and picker cancellation with the very creatively named image picker controller did cancel function, also automatically called by UIKit when the user cancels the picker, for example hitting the cancel button or sliding the picker down manually. As we can see in the docs, two optional methods of a UI image picker controller delegate. For us, of course, this is our bridging coordinator class taking on the delegate role. Anyway, continuing with our app's logic, after the user selects a video, we extract the video's internal URL. We do this using the info dictionary. This is an object representing metadata about the selected media, automatically passed to the image picker controller function after the user makes a selection. Then, pretty simple, the view model's picked video function is called, passing in that URL, and we also update the show picker state in the view model to false, closing the sheet back in the view due to the two-way binding we created. If you managed to follow all that so far, even if you had to pause and go back, you've definitely got the hang of things, how the larger architecture interacts, as well as the lower level details and code that brings our project to life. So that's good. So let's see what this picked video function does back in the view model. It's simple really. Like we said, the view model is the mediator between views and models, facilitating communication. 3 steps. First, call the model to apply the VHS effects to the selected video. We'll look at this step first in a second. Then, once it's done, create a video player for the user to play back their edited video in the app so they can see if they like it. And finally, update states at the end of the function in preparation for saving the video. The model has a lot going on: VHS effect application and media saving logic. The Patreon tutorial and code will of course explain every bit of logic in detail. So for now, let's cover the most important parts of the model: 1 class variable and 5 functions. To make things run, we use AVKit for playback and AV Foundation for processing, 2 iOS SDK frameworks that work together with AV Foundation as the engine and AVKit as the interface. This composition variable of type AV Mutable Video Composition comes from the AV Foundation framework since it deals with lower level video processing work. To be specific, the composition doesn't hold the video content itself. That is our AV asset. If you remember our deep dive into MP4s on Project 4, this understanding should fit into your mental knowledge tree nicely. So no need to deep dive what videos are again, or audio for that matter. So we'll see this AV asset in code in one of the 5 functions shortly. Instead, back to this AV Mutable Video Composition. It's a set of instructions on how to render each frame when playing or exporting a video from the AV asset. So in other words, a timeline-based container from the AV Foundation framework that describes how media tracks from an AV asset, video, audio, metadata, are combined while also applying extra effects during processing to produce the final output. It's essentially the final edit blueprint, ready to be applied on top of the original video when previewing or exporting with an AV asset export session. Of course, another item from our low-level engine AV Foundation. Okay, so those instructions, what are they and how do they end up in our composition variable ready to edit the video? In our app, they're the VHS style effects, color shifts, image noise, text overlay, and more, starting in the first function in our model, apply VHS processing. this applies a series of core image filters. Core image is another Apple framework just like SwiftUI, except core image provides image processing tools we can use in an easy way without writing complex graphics code. The function works by taking a CI image, a core image, which is just an image data type designed for processing within this framework, and we apply a bunch of filters like color adjustments, sharpening, and adding noise directly to the image for that retro VHS feel. Now, I'm not exactly Beeple or Pablo Picasso, so I played around with the filters as much as I could to get the best VHS effect possible. No need to go into each one, but of course, adding noise, for example, is a staple for that grainy VHS look, as well as lowering the saturation for a more faded, true to the old technology style. So that's our core image edits. Yes, you heard it right. Image edits, because remember, a video is many images. So this function can be used for when a user selects a single image, or as we'll see, the function can be applied in a loop to all the video frames. You'll also notice at the end, after layering on all our edits, we call another function in our file, add text overlay. This adds a timestamp overlay to the filtered image, giving it that classic VHS footage feel. It uses a bridge from core image to UIKit by converting the CI image into a UIKit UI image using UI graphics, and then converting it back to a CI image once the job's done. UIKit's text rendering within the core image processing pipeline. So we've made all our edits in these two functions. It's now time to package them up into our composition variable. Remember, this is the AV foundation object that we use to output an edited video by applying the filter instructions frame by frame. So we package this composition in function 3, create VHS video composition. The function starts by taking the video URL and wrapping it in an AV asset, the actual object that holds our audio-visual media. We pass in the URL not because the instructions change from an effects point of view, but so AV Foundation can read the video's duration, dimensions, and frame layout to know how to apply those instructions. So each composition is unique and tied to the asset. We then create an AV mutable video composition, which automatically generates a single AV mutable video composition instruction covering the whole asset, and uses our closure as the render instruction for each frame. The closure is all this good stuff between these curly braces. A closure is basically a block of code that can be passed around like lambdas in Python or anonymous functions in JavaScript, not bound to a specific name. Swift syntax aside, what the closure is doing is the important part.
Extracting each frame's CI image in the AV asset,
and applying our VHS processing to it, and handing back that processed image with this request.finishLine. So the composition is a blueprint storing the closure that AV Foundation will run later when the video is played back or exported. The result of this function is not the edited video, it's the instruction set ready to be applied to an AV asset. Then finally, we take the video composition we just made, our reusable rule set for frame processing, and store it in our class variable from earlier, ready for playback or export. So onto function 4, create player. I'm sure you can guess this creates an AV player capable of playing back video. At the function's core are these 3 lines. Again, the function takes a video URL, wraps it in an AV asset, and we put that in an AV player item, a container for videos where we can make edits like timing, adjusting audio, adding subtitles, or in our case, applying a composition. After which we take the player item and assign it to an AV player, ready to play back the processed video, applying the composition in real time, frame by frame. And the final function in our model, save modified video. This exports the processed video complete with VHS effects to a temporary file, ready for the user to save permanently if they want. The function starts by setting up an AV asset export session, a class from AV Foundation that lets us export an AV asset to a new file with custom settings. For example, we generate the custom output path for the export session, as well as assigning the composition we previously configured and an MP4 file type. Then finally, we use Swift's modern async await syntax to handle the export asynchronously. Once the export is complete, it returns a new file URL pointing to the exported MP4 video, or nil if something went wrong. Great, so that's our model file. We've covered all the logic, now comes the fun part. We get to piece these Lego bricks together to build something cool. So let's remind ourselves where we are. User hits video button, we update the show picker state in the view model. The updated state launches the sheet and creates our video picker, and this pulls up the UI for selecting a video. User chooses a video, and this automatically triggers the image picker controller function, which calls the picked video function from the content view model and closes the picker by updating the state also in the content view model. And this is where we reached before going through the model file. So picked video does 3 things. First, it calls create VHS video composition from the model, which as we've just seen leverages the core image and UI graphics frameworks to apply our VHS effects and ultimately create our composition variable. model. Then second, we use the create player function from the model to apply that composition on the original picked video inside an AV player which is returned to us. And finally, we keep our app up to date by making sure selected image is nil in case there was a previous selection and updating selected video to the user selected video URL. So let's pause there because we skipped over this player arrow. As a test, I'd recommend you maybe take a pen and paper, maybe look at the MVVM architecture or previous interactions in our app and write out some ideas on what you think happens next, how the content view might interact with the content view model and the player variable, and what attributes might be involved in order to show the user their edited video. You can also do the same for the observed state after updating our selected video variable. Otherwise, if you're too cool for school, let's continue as we come towards the end of our user flow. Since the player is a published property in the content view model, and the content view model itself is owned by the content view via the state object attribute, we know by now SwiftUI sets it up so all the published properties are automatically watched, and any change will re-render the view. So of course, the player update triggers the view to create a video player, passing in the AV player in this line here to display the edited video on the screen. The AV player from the AV Foundation framework provides the actual playback engine that loads and controls the media, while the video player from the SwiftUI framework is the UI wrapper around this AV player engine. And here's what all that logic looks like in action. A beautiful moment of someone's child attempting to blow their candles out that I farmed off the internet, and we can see our player with the edited video including the audio. How wonderful. We can also hit this save button, receive a nice blue notification and the video in our photo library with the audio track too, of course. So we've covered the user interface, editing and the player, and we've just seen saving, our final feature in this native iOS app. Let's now check out the logic behind saving. So we last saw the picked video function in the content view model update the selected video state. Again, same MVVM data flow, which I'm sure we're sick of by now, but just hang in there, we're almost done. The updated state of the selected video in the view model causes a re-render in the view to display the save button. Again, in our classic declarative way of what things should look like based on state SwiftUI approach. One button, a label with some modifiers, and the action of saving, of course defined in our logic-centric model, communication facilitated by our view model. Well, that would be the standard approach, but we share the save logic with the model and the view model. Sometimes you have to make design choices that make sense in the context of your app. For us, since the view model already manages a lot of the user-facing state, like loading or save success state, it made sense to keep some of the saving logic in here. Ultimately, like with everything, it's a trade-off. In this case, stricter architecture pattern adherence versus more readable and cohesive code. Either way, it's clean and makes sense as we're about to see. So user hits that save button we just rendered in the view. This calls the save video function in the content view model. Then, after updating the loading state, this shows the user this loading screen due to another two-way binding back in the view in case the user wants to slide the view down and cancel out. Then we call the save modified video function in the model, which we've already seen, handling the heavy lifting of applying the frame-by-frame composition to our video. So no need to revisit that again, I'll spare you the pain. But one positive side note, the save image function in the content view model doesn't have to go back to our model. Since we're passing around a single frame, it's a lot simpler. So that's a small blessing in this turmoil of code. After the model returns the temporary URL of where it stored the processed video, the content view model cracks on with saving the video to our photo library. Remember, at the start of this project, we mentioned users will be prompted for photo library access, so we ask for permissions in our info.plist file. Well, it's at this point they'll see that iOS pop up with the message we entered. Earlier, when selecting media, the system picker ran outside of our app's sandbox to select one item. Typically, this means no prompt, but at this point we're writing to the library, so iOS will confirm with the user via the prompt if we're allowed. If we are, we use the Photos framework from the iOS SDK. That's what the PH stands for in the code. We'll request to perform a change where we create a new PH asset, copying over our processed video into the new photo library item. We do this using a dispatch queue object, just a bit of asynchronous work on a background thread, allowing operations to continue on the main thread, all wrapped in a code block to neatly handle any errors and update states at the end whether successful or not. If successful, for example, the saved state is updated to true using the saved successfully helper function, triggering a re-render in the view which shows our beautiful blue save notification. And with that, I'm happy to announce we can can now save our media, and also that we've reached the end of our UML diagram and the end of our journey building an iOS app. We've covered a lot of native mobile development, Swift, Xcode, iOS frameworks from image processing to working with the system photo library, as well as building the UI. By looking at the building blocks of this new area of software development, we can now walk away with an understanding of how we can build any type of mobile app, not just a media editor, especially by completing this project with language-agnostic programming principles in mind, like declarative and imperative design, as well as looking at larger concepts like architectural design models. So from native mobile apps to cross-platform desktop, at this point we've seen it all and are ready for a real change of pace with this next project. This next project has the potential to be the most technical of the lot, blending code and different areas of mathematics to build a scripted application for neural style transfer. In plain English, that means we can take a regular image, our favorite art piece, and create a brand new piece that combines the both, giving us the power to create something that art students will study for years to come. It's definitely a fun project with a lot of complexity under the hood that we can dive into, and I promise by the end, this math, these pictures, and this model will make perfect sense to you, and you will be ready or completely against exploring machine learning and artificial intelligence even further on your own. As always, for grasping complex subjects, we start with the trunk of our knowledge tree. So we'll first build an understanding of AI models in general, the neural net model type, and the math that powers them. The second half of this project will be looking at the style transfer project directly, the Python code, our model, and working with images to produce the final result. So it's that time again. Gather your things and join the campfire for a brief history of AI, because it's really something to behold how we went from banging rocks together to creating literal godlike silicon minds.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
The study of logic and reasoning dates back to the deep thinkers in ancient Greece, which, skipping ahead, led pioneers like Turing to develop the theory of computation, a foundational area of theoretical computer science studying the capabilities and limitations of computers and algorithms. Turing didn't just ask what machines could compute, but whether one day they may also think, leading to the famous Turing test in 1950, a basic measuring stick for machine intelligence. A few years later, in 1956, we can say AI as a formal field was established by researchers out of Dartmouth College in America. This work focused on reasoning through rule-based programs and symbolic representation. Great at well-defined tasks, but poor for generalization. GoFi they're now called. Good old-fashioned artificial intelligence. A notable learning program during that period in the 50s was Arthur Samuel's Checkers Agent. Working out of IBM, it used Minimax search trees to evaluate future moves and an evaluation function capable of improving over time through self-play by adjusting the function. He called this process machine learning. Towards the end of the 1950s, this guy, Frank Rosenblatt, who dabbled in astronomy and injecting the brains of rats into other rats, no, seriously, he did that, sounds a bit serial killer vibes, but he knew what he was doing, as amongst all that, in the field of computer science, he developed the perceptron. After McCulloch and Pitts introduced the threshold logic unit in the 1940s,
a purely theoretical model that proved networks of TLUs could compute any logical rule, like the ones inside digital circuits,
Rosenblatt picked up the idea when technology had finally caught up, taking the TLUs and arranging them to build the perceptron. So the TLU by itself is a simplified model of a biological neuron. It sums weighted inputs and applies a function, outputting 1 or 0, made to simulate logical operations like and, or, and not, triggering only if the weighted sum of inputs exceeds the threshold. So the perceptron took these units, stacked them in a single layer, and combined them with a learning system. Weight update rules based on reducing error between the model's predictions and the pre-labeled expected outputs. A foundational step forward for AI, but narrow scope.
It produced only binary outputs,
cat, dog, yes, no, and limited by the hardware and math to linearly solvable problems. And by linear, we just mean fancy math speak for a straight line relationship between input and output.
So collectively, these limitations applications across the field led to the first AI winter, with the next boom being led by expert systems, AI systems that simulated the expert-level knowledge of humans in specific fields like medicine or finance. For example, MySyn was a milestone expert system made to diagnose infections and recommend treatments. Structured patient data input, symptoms, test results, known conditions, and output of a percentage certainty diagnosis with recommended treatment. But let's be clear, the dominating interest at the time, these expert systems were not capable of learning. This was handcrafted machine intelligence. For example, MySyn was rule-driven, over 450 lines of if that, then this. Although more than a hard-coded script, the system could reason, chaining together logic, inferring conclusions, and prompting the user for more information. Impressive for the time, but these systems hit a wall. No learning meant things stayed broken unless someone fixed them, so they were hard to scale, and the underperformance of these systems relative to the funding from corporations and governments led to the second AI winter.
Winter is coming.
The next major breakthrough came in '86 with backpropagation. Rumelhart, Hinton, and Williams showed how to train multi-layer neural networks. Rosenblatt's perceptron was great, but he saw it as a biological model, an attempt to simulate how brains might learn using binary neuron-like units, a single layer adjusting weights through a simple linear error rule, and each neuron used a step activation function, which outputs either 0 or 1 with a sharp jump. This made the network output non-continuous, limiting its use to data that can be separated by a straight line. Cat, dog, yes, no. Rumelhart and the boys shifted this focus by reframing the neural net as a mathematical function approximator. The entire model's goal is to estimate an unknown continuous function, and they achieved this by applying an existing mathematical method named gradient descent. This shift replaced hard thresholds with differentiable activations, and if this makes no sense, don't worry, we'll look at the math that powers this learning process we call backpropagation later. Also, honorable mention goes out to this guy, Yann LeCun, one of the three godfathers of AI, credited with building the first convolutional neural network in '89 and continuing to improve it in the years that followed. Linnet he called it. And yes, he is French. So CNNs are a type of neural net designed to detect patterns in images, which Linnet pioneered by recognizing handwritten digits. For example, imagine a program that takes in a grid of 28 by 28 pixels and outputs a probability of which value that image is showing between digits 0 and 9. Eventually, Linnet 5 became one of the first architectures to be trained with backpropagation on a major scale, on a dataset of 60,000 grayscale images, achieving state-of-the-art accuracy, eventually to be commercialized in banks to read checks, as well as reading zip codes for US mail. The CNN is the model type we'll be using in our style transfer project. Good to know it has practical roots early in the AI lore. As influential as backprop was in the 80s and 90s, compute was limited, data was scarce, and so generalization and commercialization was relatively minimal. In the period that followed in the 90s to the early 2000s, often called the machine learning era, neural nets remained an academic pursuit, and other more purely statistical methods dominated. Support vector machines, decision trees, random forests, and Bayesian methods. Heavily statistical and probabilistic focused, easier to interpret and faster to train. For example, out of this period came spam email detection using naive Bayes classifiers based on word probabilities and patterns. What followed was a turning point in the 2010s when big data, GPU acceleration, and improved neural net design all aligned. AlexNet in 2012, a deep convolutional neural network trained on GPUs with over 1 million labeled images, dominating a competition called ImageNet. It was developed by our old friend Geoffrey Hinton, who worked on backpropagation, one of the three AI godfathers, Ilya Sutskever, most known for founding OpenAI and for his time there as chief scientist, and Alex Krizhevsky, who was the lead architect behind the model. So yeah, you really don't want to be up against these guys. They didn't just think outside the box, they invented a new one and blew the competition up. The model was deeper in terms of layers to the standard at the time, made possible by introducing design innovations like ReLU activations, which meant faster training, especially when combined with GPU-based training. And we'll see why this is better when we look at the math later. But But quickly, here's Jensen Huang, CEO of NVIDIA, talking about how these boys use GPUs to train their network.
In 2012, Jeff Hinton's lab, this gentleman I was talking about, Ilya Sutskever, Alex Kershevsky, they made a breakthrough in computer vision, a piece of software called AlexNet. Its job was to recognize images. And it recognized images at a level, computer vision, which is fundamental to intelligence. If you can't perceive, it's hard to have intelligence. And so in 2012, AlexNet was able to recognize images so much better than any human-created computer vision algorithm in the 30 years prior. Took a giant leap above it. And the way it ran, the way they made it work was literally buying 2 NVIDIA graphics cards.
They were also the first major model to apply dropout, a technique to reduce overfitting by randomly deactivating neurons, which when all combined was the first real proof deep learning could scale and generalize, accurately classifying a dataset of over 1 million images into 1,000 categories. This was the deep learning era. From there, as you can see, things escalated pretty quickly. CNNs, RNNs, LSTMs, GANs, all pushing the boundaries across artificial intelligence. And then came the introduction of the transformer in 2017, a new deep learning architecture designed to handle sequential data like language, replacing recurrence with self-attention. This shift meant a bunch of things like faster training, a lot more long-range context, and a lot more scale, powering language models like the GPT for text generation or Stable Diffusion for image generation. And finally, we arrive at today, foundation models, massive pre-trained models like GPT trained on insane amounts of web data, then fine-tuned and adapted for tasks ranging from writing code to composing music. All that history, around 70 years of dedicated research, model and hardware improvements by some of the greatest minds to exist, all so you can ask ChatGPT to write your 30-second cover letter while you lie in a ball on the floor wondering whether it will take all the jobs too. Great stuff. Campfire over, and now we know the historical beginnings of these silicon gods. Let's now channel our inner Euclid and check out the math and logic that powers deep neural networks. So we have AI, machine learning, and the deep learning subset. The neural network, with its origins being inspired by the human brain, made up of lots of layers of interconnected neurons, where layers can be fully connected dense layers or sparsely connected layers. The first layer is called the input layer, which can accept the raw data. It could be images, text, or pretty much anything. The hidden layers accept input from the previous layers, and there's the output layer, which takes data from the final hidden layer and produces our final prediction. Let's dive into a single neuron and work our way up. One neuron, a single computational unit in the network, receives input X, applies a unique weight W and linear bias B to the input. We take that sum and pass it through a function we call an activation function, shown here as G but sometimes as the letter F. This outputs a value Y for the neurons in the next layer connecting to this neuron. So simply put, we can think of the neuron as a tiny function that results in this equation. This Y hat equals G W times X plus B. And let's make sure we really understand this by looking at the output of a neuron equation in full. The X values are the input to the current neuron from the previous connected neurons, or if we are looking at the input layer, it would be the raw input values themselves, like the value of each pixel in an image. The W values, the weights, define how strongly our neuron should care about a given input, and these will change through training, which we'll look at later. So W times X in the compact version is the total weighted sum, just before adding the bias. And we can also represent it mathematically with this Greek letter sigma, a fancy symbol for summation. And side note, these fancy math symbols, you've probably encountered them before in code, so nothing to be scared of at all. B is the bias, a constant value that allows the neuron to shift the weighted sum up or down. Also a trainable value to help the neuron and the entire model learn better. And remember, when we say learn, we mean the model is trying to approximate the underlying function that captures the patterns in the data we are looking for. As a simple example, a model might learn the function that maps house size and number of rooms to the price. This sum of W times X plus B is then passed through an activation function. This is most usually a nonlinear function like ReLU or sigmoid. For example, in ReLU, the function outputs 0 if the input is negative, or the sum value remains unchanged if positive. And this is pretty clear in the ReLU graph. By introducing nonlinearity, activation functions allow neural networks to learn more complex patterns, and they are chosen based on task. For example, sigmoid is great for binary classification tasks because output values are between 0 and 1, and ReLU is popular for hidden layers because it's efficient and helps avoid vanishing gradients. And of course, the result of our activation function gives us the output. The math should be clear now, and we'll take a look at a practical example in a second to give some real meaning to it all. Inputs, weights, biases, and activations. But I think it'll make more sense if first we zoom out to the layer level and up the math a bit. So we should be able to understand this image. Individual neurons receive inputs, scaling them with some weight W and applying bias B, taking the sum and passing it through an activation function, eventually passing the output to any connecting neurons. We also know in a dense layer the output will be accepted by all neurons in the next layer. Data flows forward towards our output layer and learning we'll explore later. But in actuality, these arrows and functions are vectors, matrices, and linear algebra. Let's break that down. What you're seeing here is a single layer's computation, the mathematical combination of all neurons in a layer to produce an output. And before we dive into this, let's quickly clear up some more fancy math terms we'll be using from now on. We have tensors, a general term for dimensional arrays, including 0 dimensions, which is a scalar, a single number. We have vectors, a one-dimensional array, and I'm sure we've all worked with these while programming, sometimes called lists. Two-dimensional arrays are maybe less common, but if you've done any LeetCode practice, I know there's a great question on matrices in the last video. You'll know they're just a list of lists. There's also 3D tensors, and we can keep going up from there, but it'll keep getting harder for our tiny human brains to comprehend, so we'll stop there. Now back to our layer. The highlighted squares in this image across all 3 tensors represent the computation of a single neuron. The first matrix on the left is our weight matrix. If each row corresponds to a single neuron in the current layer, then each column corresponds to a neuron in the previous layer. If we look at a single weight value and call it WKN, then it represents the weight of the kth neuron in the current layer connected to the nth neuron in the previous layer, or the raw input. I know it sounds confusing, but bear with me for a second. Focusing on just the weights, W01 for example, is the weight used by the 0th neuron in the current layer to scale the input from the first neuron in the previous layer. Likewise, W10 is the weight used by the first neuron in the current layer to scale input from the 0th neuron in the previous layer. If that didn't make sense, play it back a couple times and I'm sure it will become clear. It's not too difficult at all, just a lot of notation. Main point is, one row is a single neuron in the current layer, and each weight in that row is a connection to a different neuron in the previous layer. So in these diagrams, we have A instead of X to represent our input values. Again, this could be from previous neurons if we're looking at a hidden or output layer, or these could be raw inputs in the input layer. So our weight matrix is multiplied by the input vector. Pretty simple this part. These A's, the outputs, also called the activations of the neurons in the previous layer, stacked vertically, multiplied by their respective weights. Let's see this in action. To calculate the weighted input of the 0th neuron in the current layer, we take the output of the 0th neuron in the previous layer. In this example, that previous layer is layer 0, so it's shown as A00. We take that and multiply it by W00, the weight representing the connection between the 0th neuron in the current layer and the 0th neuron in the previous layer. Then we take the next neuron in the previous layer, A10, the corresponding weight, W01, representing the connection between the 0th neuron in the current layer and the first neuron in the previous layer, and repeat. If we continue doing this down the input vector and along the weight row, we get our long version of the single neuron equation. The inputs from the previous layers times their weights. That's all it is. We can condense this down into WX or WA, and we can also use the sigma notation if we want, showing our for loop going through all the weights and inputs. And if we do this for each neuron in the layer, we get the total output of the layer. Each one of these multiplication operations is called a dot product. When we look at the entire layer, the result is the batch of dot products, also called the matrix vector product, resulting in the W times X in the compacted version of the neuron output function. To the result of each dot product, the bias is added, or we can say the entire bias vector is added element-wise to the result of the weight matrix multiplied by the previous output vector. For example, we would take this 58 and simply add the first value in the bias vector. This gives us the one-dimensional output vector for the next layer. For example, here we've been looking at the previous layer, layer 0's output vector. Then finally, the result of that computation is passed through a nonlinear activation function, shown here as sigmoid, again added element-wise to each neuron's result. result. And don't be confused by the fact it's wrapping the entire layer in the diagram on the left. So in summary, we can represent an entire layer's expression as the following, where AL is the output vector of the current layer's total neurons, and AL-1 is the input vector from the previous layer. Not easy stuff if you've never seen it before, but once it clicks, it's quite manageable. So that's the mathematical foundation of neural networks. Let's now reinforce the idea with a practical example. So in the hidden layer, it can be unclear which representations or connections the neurons are establishing, which is why you'll often hear neural networks called black boxes. Looking at a practical example will help break that down a bit too.
So there's kind of two common ways people talk about explainability. One is I need to know what's happening with every neuron in there. I need to be able to x-ray it and, see what happens if I change this weight to that. Not something we get to do with humans either. I don't get to look in your brain at the way every neuron is firing and say, okay, well, it's no longer a black box, I understand.
Going back to our digit recognition example, a simple input representation that makes sense is setting each of the 28 by 28 pixels in an input image to correspond to one neuron, resulting in an input layer of 784 neurons. And each neuron will receive an input grayscale value of that pixel, white being 255 and black being 0. It's unclear exactly which patterns the neurons in the hidden layers are detecting, but we can imagine it would be subcomponents of the number and the image as a whole. Maybe a few neurons in a layer are detecting smaller lines in the lower middle section of the image, and others representing the strength of curved lines in the upper right section. And when pieced together, the next layer can begin to detect larger patterns like full circles in the upper section of the image. So this is where the weights between the neurons come in and are crucial. If we zoom into this small group of neurons and assume it's looking for something like this line of pixels in the upper half of the image, then we can begin to understand the meaning and purpose of weights in action. For example here, the network looking for this line would assign positive weight values, the green area, from the input neurons in the line area we're looking for, amplifying their influence and increasing the neuron's activation, indicating the line pattern exists. And the network would also assign negative weights to the surrounding pixels, helping the neuron ignore noisy or incorrect patterns. And all other weights would likely be 0, meaning they have little influence on detecting this specific pattern. And moreover, the value of each neuron could come out to be anything. So activation functions not only introduce nonlinearity to approximate more complex patterns, but can also help to normalize the neuron activations across the model. So we pass the outputs through an activation function like the sigmoid function, and maybe there's a threshold of activation we want. So the model introduces a bias for determining activity, and ultimately the model learns, fine-tuning all these parameters over time to best fit or approximate the underlying function. And at the end of this digit recognition neural network, we have 10 neurons, one for each digit 0 to 9, where the most activated or the highest value neuron is the network's prediction. And that's it for the mechanics of a neural network. Nothing too crazy, right? But what's that I hear? You want more math? Good, as now we're going to see the training process. Because all this means nothing without the ability of the model to learn how to adjust the thousands to millions to trillions of weights and biases, which output is good and which predictions are bad. So let's do some more math. Generally speaking, neural networks train on data, training data. A common approach is to train the model on say 80% of the data and see how it performs on the remaining 20%, the test data. For example, for handwritten digits, we label all the digits, give the model 80% to train on, and test it on the remaining 20%. It could be more complex, like inputting medical data, symptoms, lab results, historical info, and the output being the diagnosis. So the big question is, how does the model learn? How does it learn the underlying pattern, or in math speak, how does it approximate the underlying function? And how do we end up accurately predicting outputs? To begin, the network is initialized with random values for all the parameters, the weights and biases. At this point, it will give us very poor outputs, so obviously the network needs some target, a goal that it should aim towards. For example, imagine you're in Paris. Without a target of, say, visiting the Eiffel Tower, you have no idea whether the steps you're taking are good or bad, measured by whether where each step is getting you closer or further from the tower. This measurement for you is the loss function for the neural network, also called the cost function, a fixed mathematical formula that quantifies the difference between a model's predictions and the actual target values. We can think of the loss function as having an input of the neural network's output, which itself is essentially a function of all the weights and biases, and the output of the loss function, a scalar cost/loss, one number. So the loss function is an abstraction layer above the neural network, and that should be clear from the table. For example, in high school math class, on a simple graph, the line of best fit is the result of using a loss function. We're attempting to get the loss, or in other words, the total error, as small as possible by finding the line that minimizes the total error distance of all the points to that line. So important point, the loss function is a general term for this mathematical measurement tool, and we have specific implementations of it. A pretty good one, and one we intuitively use to find the line of best fit on that 2D graph, is the mean squared error. This calculates the average of the squared differences between all the predictions and their actual target values. For example, if we are predicting people's weight, maybe based on their height, we take the numerical error value, the difference between our guess and the truth, and square it. We square it, making all the values positive, ensuring under and overestimations do not cancel each other out, and also to penalize larger errors more heavily than smaller ones. So we take these squared error values and plug them into the MSC formula you see again on the right. 1 over n, the number of entries, to give us the average of all prediction errors multiplied by the sum, notated here as I, so from the first entry, 1, to n, the last, of all the error differences squared, and a nice reminder of the equation from where these predictions are coming from in our neural network. So applied to our example, that's 1 over 3 multiplied by 25 plus 25 plus 4, giving us a mean squared error of 18. Ultimately, of course, our goal is to get this value as low as possible, since of course due to the squaring the MSC will never be negative. So best case MSC of 0 tells us our predictions are 100% accurate. And it's the exact same principle for the neural network, we're just going to beef it up a bit. Going back to our numerical digit recognition example, where our output layer of 10 neurons represents each digit, at first the random initialization of parameters will produce outputs all over the place with poor predictions. So to calculate the loss, we begin by taking the prediction vector of the output layer and compare it with the labeled training data of what the digit's value actually is, taking the squared error for each output neuron in this single training example and finding the average, or the mean. If that was the mean squared error for one example, then the next step is the combination of all training examples by calculating the total MSE. So we do this by taking the sum of squared errors from each training example and dividing by the total number of training examples. This final single numerical value is the loss value we aim to minimize across the entire network as our target, whether we're getting closer or further from the Eiffel Tower. Now of course we can tweak the parameters of the model, the weights and biases, to get different output results and a different loss. We could increase the loss or hopefully decrease it with each change. To help us find the best parameters, we can think of the loss function as a landscape, a multi-dimensional graph where every point on the graph corresponds to a unique combination of the network's parameters. Here we're looking at a 3-dimensional graph. Any more dimensions and our tiny human brains begin to struggle again. So 2 parameters here, but remember we said the state-of-the-art models have reached the trillions. And in fact, let's actually kick it back to a very basic model with 1 parameter. To put this into perspective, we can imagine our earlier example of predicting a person's weight in kilograms has 1 parameter A that we can adjust, some multiplying factor applied to their height, and that's our model. This will produce a simple 2D plot like the one in front of us, where there exists some single value for A, our parameter, that gives us the minimum loss, the most accurate results possible. Okay, but I'm pretty sure you know well enough life is never that simple. Sometimes the loss graph has multiple minimums, or local minima, and we want the global minimum. That's one complication. On top of that, like we said, we don't just have 1 parameter in our model, we can have thousands to trillions. Regardless, the premise still stands. Our goal is to find the global minimum point on this loss graph. That's where the model will be fine-tuned with the parameter values that give us the most accurate results based on whatever the task or training data is telling us is the desired output. And that's an important point. Our model will only ever be as good as the data it's given, which leads to a whole range of key AI challenges, shown in this table. Nevertheless, the question becomes, how do we find this minimum? Enter gradient descent. By definition, gradient descent is an optimization algorithm. It iteratively adjusts a model's parameters to minimize the loss function by calculating the gradient of the loss function with respect to the parameters. Let's break that down. So imagine we've just calculated the loss, resulting in a point on our loss graph, and we'll keep it 2D for now since the core principles still stand regardless of dimensionality. With some clever calculus math dating back to the 1600s and an infamous battle between Newton and Leibniz over who should be credited, we can figure out the slope of the loss graph at that exact point, also known as the gradient. We've now reached slightly more advanced high school level math. Differentiation is the mathematical process for finding the rate of change of a function at any given point, which basically means finding the slope of the graph. It's probably not the best time to give a full rundown on the inner mechanics of differentiation, how it was invented and how it works, but we can take a look at an example to wrap our heads around it. Here is the graph x squared. The derivative of x squared is 2x, notated like this. We say the derivative of y, which is x squared, with respect to x. We notate it with respect to a parameter, since as we'll see in a second, we can have multiple parameters in our function. So in plain English, the derivative of y with respect to the parameter x tells us how fast y changes when x changes, the slope at that point. So let's see some examples. At point x equals 2.5, we have a slope of 5. Intuitively, that means roughly for every 1 unit we move to the right along the x-axis, the function's value on the y-axis increases by 5 units. What's nice is that the calculation not only tells us the steepness of the slope, but also the direction. For example, when x is negative 2.5, the slope is negative 5. And you'll also notice at the point x equals 0, the graph is flat, giving us a slope of 0. Okay, so we know how to calculate the slope of a graph. Great, but how does this help our model learn? Well, we can use this math to figure out which direction to move our parameters to minimize the loss, even when we have trillions of parameters. For example, when x is 2.5 and the slope is positive 5, we know reducing x will move us down that slope, bringing us closer to the minimum of the loss graph. Let's now see a training example end to end so we can take a look at the gradient calculation in action. Step 1. Initialize the model with random weights and biases. That's easy. In practice, we just hand this off to whatever machine learning framework we're using to randomize and assign those parameter values. Step 2. Forward pass. We pass our training data inputs through the network to compute predictions. We covered this earlier and should be well aware of what these formula on the screen represent for a single layer, and we also know what that would look like for a single neuron. And so if we extrapolate this out across the network, we get an equation that looks like this, which should be fairly straightforward given our earlier practice. Step 3. Loss calculation. We compare the model's output predictions to the true values using the mean squared error and the mean of the mean squared error for all the training examples collectively, providing a measure for our prediction error, or in other terms, the model's accuracy. I think it's safe to say we've got that covered too. Step 4. Gradient calculations. We've seen the core mathematical principles behind calculating gradients. Let's now take a minute to dive into applying this math to our neural network. Since we have so many layers and parameters, the final output is the result of multiple nested functions, and figuring out exactly how much each parameter contributes to the total loss is difficult. Luckily, we can use the chain rule. It's another mathematical formula in calculus, one that lets us compute the derivative of a function that's made up of other functions. We don't need to know the ins and outs, but we should recognize that using the chain rule will help us figure out how much the activation of an output neuron, and ultimately the loss, depends on the previous activations, which themselves depend on their respective weights and biases. So we want to know how much each parameter contributes to the final loss. So for each parameter, we compute the partial derivative, or the gradient, indicating the direction and magnitude of change to the loss if we were to increase or decrease that single parameter. Let's say we have this very simple network of 4 neurons, and we want to evaluate the change that this weight, W3, has on the loss for a single training example. Now, some of you may find the rest of this step a bit complex, but that's fine. It's not necessary for completing the practical project, but it serves as a good insight into the real mechanics of machine learning for those truly interested. On screen, we have the same 4 neuron network, but we've zoomed in on the last 2 and added the cost calculation at the end. There's nothing new here at all. A change in this weight, W3, or generalized to WL, causes a change in the output of neuron AL, L of course referring to the current layer, and we also know this will ultimately cause a change in the final cost, that's standard. We can also condense this linear term, WL times AL minus 1 plus BL, into a single symbol, ZL, representing the
the weighted input of our last neuron before applying the activation function. So key point, this change in WL will ripple forward through ZL, affect the activation AL, and ultimately the cost C. What we want to know is the derivative of the cost with respect to that weight WL. In other words, on our loss function, where each point represents a new combination of all the model's parameters, if we were to keep all other parameters fixed, what is the size and direction of the change of the cost if we slightly change the value of WL? Using the magical rule, we end up with the following partial derivative, the rate of change of the cost with respect to WL. And if we want, same as we did by differentiating x squared to 2x, we can actually compute this derivative. I won't go through the math of using the chain rule to arrive at this result, but it's there in front of us. The important point is this: when we initialized the random parameter values and completed our forward pass in step 2, we calculated all the real values for these variables. So we know the activations AL and AL-1, and inside ZL, we know BL and the current WL, and we know the value of Y from the training data. So to calculate the slope, we simply plug all these numbers into the derivative expression, and out comes a single gradient value telling us exactly how sensitive the cost is in size and direction to changes in that specific weight WL. But let's not forget, this is the derivative of the cost function with respect to this one weight in a single training example. Of course, we have many training examples, so in actuality, we compute the gradient with respect to one parameter for each example and take the mean, giving us the final mean gradient of the total cost function with respect to this weight across all the examples. And don't forget again, this is just one averaged gradient for one parameter in the entire gradient vector which we calculate, containing the partial derivatives of the cost with respect to every single parameter in the network. Now this whole process we just went through, gradient computation using differentiable activations, we call this backpropagation. The error gradients we calculate flow backwards through the model, hence the name. Pretty amazing to think these guys took the existing algorithm of using the chain rule to compute gradients in layered functions and applied it to multi-layer neural networks all the way back in 1986, laying the groundwork for some of the most influential AI technology today. So we have our gradient vector of all the parameters, and that leads us to the final step. Step 5, updating the parameters. So a gradient value of 5 for a weight, DCDW1 for example, means that slightly increasing the weight would roughly increase the total loss by 5, assuming the loss function is locally linear around this point. Of course, in reality, the loss surface is highly non-linear, but the principle still stands that these gradients give us the best local signal for which changes will reduce the loss. So in this step, we take every parameter in the model and update it according to the gradient descent update rule. Let's explain it with a practical example where we have a model with 3 weights and no biases, giving us a gradient vector like this. And let's say we choose a learning rate of 0.01. The learning rate is a small positive number to control how big of a step we take in our gradient descent, updating the parameters gradually to avoid overshooting, allowing us to steadily converge to the minimum instead of wildly bouncing around the loss surface. You'll see this part is surprisingly friendly, especially given all we've just gone through. We first multiply the gradient by the learning rate. Nothing crazy, we're just following our gradient descent rule. And then we take that result and subtract it from the old parameter value to give us the new parameter value. We then update all these parameters in our model, of course, and that gives us one incremental step in the gradient descent process. And finally, step 6, repeat. A step we take again and again and again, repeating the entire process without the random initialization, of course, forward passing, calculating the loss, backpropagating to calculate the gradients, and updating the parameters. And quick mention, depending on our learning strategy, we update the parameters at different points, after each training example, after each batch, or after the entire training dataset, each with its own trade-offs. But once you know the inner mechanics, the rest is just implementation details. However, that's pretty much it for neural networks. Their origins, their architecture, how they're used in practice, how they train and learn, and the math behind it all. Hopefully now we can see that nothing is really too difficult. We just need to take the time to steadily build up our knowledge tree. Or now that we are math experts, we can say knowledge is a function of time and work, maybe even with some efficiency focus factor coefficient. Now let's take a look at the neural network we'll be using for our project before applying all this knowledge we've acquired through the power of code. The Convolutional Neural Network, CNN, a neural network of the convolutional kind. A convolution in the general sense is a mathematical operation describing the rule which combines two functions or pieces of information to form a third. In CNNs, the two functions are the input
input data and the kernel, where convolution refers to the process where a kernel, also known as a filter, is slid or convolved over the input data like an image, computing dot products at each position to produce a feature map. Let's break this sentence down. A kernel is a matrix used to transform or extract features from data. Features like edges, textures, and spatial patterns. We take our kernel and slide it across the input image, which itself is just a matrix of pixel values. In this animation, the input is a 5x5 pixel image, where each pixel is a value from 0 to 255, representing the intensity of a grayscale pixel. Our kernel is the blue 3x3 matrix. The values inside the kernel determine which kind of feature it will detect in the image as reflected in the output. Here are some kernel examples that might be used to detect or transform different features of an image. For instance, to sharpen this image of this squirrely kangaroo thing, we apply a kernel to enhance the contrast between neighboring pixels. Even though we slide and apply the kernel across the entire image, in positions where the center pixel is very different from its neighbors, like along edges or fine details, the difference gets exaggerated, resulting in a sharper image. Or in our case where we're performing edge detection, it's quite similar to sharpening, although sharpening attempts to keep the original image details and enhance the edges, while edge detection looks only to highlight the sharp edges and remove the rest of the information, so any areas of large imbalance pop out. For each slide, or stride as we call it, we perform an element-wise multiplication with each section of pixels the kernel covers and sum the result. In this second convolution animation, we can see some extra pixels or padding added around the original image. This is to preserve the original image size, since applying any kernel greater than a dimension size of 1 by 1 without padding reduces the dimensions of the original image due to the fact not every pixel can be centered under the kernel during the convolution operation, particularly near the edges, leading to shrinkage. The result of convolving one kernel across the entire input is the matrix of values we call the feature map or feature channel. Okay, so kernels are a neat little image processing tool. How they are used in convolutional neural networks is the next big idea, and then we can finally get into the project. On screen is a very basic CNN, one used for some classification task like our digit recognition example. We can define CNNs as a type of deep learning model designed to process grid-like data using convolutional layers to extract different spatial features like edges, textures, and patterns. A convolutional layer is a component of the model that applies multiple learnable kernels to process the input data or output from the previous layer, performing the convolution operations to extract local patterns. If we stick with our grayscale input example, we can slightly expand the complexity by following this diagram I put together. A kernel is no longer this simple 2D matrix, but a 3D tensor of many matrices, a stack of kernel slices. In the input layer for our grayscale example, our first convolutional layer, let's imagine we have two kernels, and each kernel processes one grid-like input and produces one feature map output. That's fairly straightforward, and we've just seen that convolution process in action. In this case, each of the two kernel stacks in our input layer is a 1x3x3 stack, one slice or matrix of size 3x3. Then let's assume we have another convolutional layer, this time with 4 kernels. Each one of these kernel stacks accepts as input the entire feature channel output from the previous layer. So in this case, 2 feature map inputs. But the key point here is this: each one of those 4 kernels also outputs one feature map, regardless of the number of input channels. Each of the 4 kernel stacks is now of size 2x3x3, 2 matrices or kernel slices of size 3x3 corresponding to each feature map input. So slice 1 is applied to feature map 1 and slice 2 is applied to feature map 2. The result of the convolutions are added together, giving us one feature map in the final part of the image. And that's the process. Let's now take a look at a more full end-to-end diagram of this convolution process in a CNN. What we're looking at here is one convolutional layer. We're taking a look at one kernel stack of dimensions 3x3x3. Of course, most models will have multiple kernels in each layer, but we're just focusing on one for now. Each slice processes one of the 3 feature channels it receives. The result after summation is one feature map as we've just seen, and to this result we add the bias and pass the result of that through an activation function which gets handed off to the next layer. Now we can see all the parameters in the model. The bias is right there, and our weights, well, our weights are the kernel values for each slice's matrix. Through the power of backpropagation, the kernel values will update over time as well as the bias. So we can loosely think of this one kernel producing a single feature map as the neuron in our model producing one activation, which when stacked give us the layers feature map stack or the layers activation vector. Also worth a mention, since in our project we're dealing with a colored image as the input, you may know that it's not single pixel values like in grayscale, but instead color images are made up of 3 channels: red, green and blue, RGB. We can think of each channel as its own 2D grid, and stacked together the 3 channels make up the colored image. In this case, our input layer is no longer kernels of 1 slice, but however many kernel stacks we decide to have, where each will be 3 slices, 1 for each color channel. So that's how CNNs work in the convolutional layers. Just a couple more things to mention before we can say we've completely mastered these models. We said the kernel values are learned through training, and for traditional convolutional tasks, these values will be fixed. That's fine, regardless they operate the same. We also said there's many convolutional layers with many kernels. Why? Why not one layer with all the kernels, or many layers with one kernel? Well, it's the same idea as our regular deep learning network. Each layer learns increasingly more meaningful features and high-level representations, although they may look abstract to us. Like we said, it's a bit of a black box to the human eye. But in general, the deeper layers capture more semantically rich patterns, whereas the earlier layers more simple features. CNN or DLN, the principle is the same. Each layer builds on the output of the previous one, learning to detect patterns in a hierarchical approach. And that's the architecture and inner workings of a CNN. We have extra components that we might add to the model and switch out depending on the task at hand, like pooling, or most often for classification tasks, a fully connected network after the convolutional layers to take the feature maps and categorize them into class probabilities, just like AlexNet in the ImageNet competition we saw earlier. Right, with that out of the way, we can finally take a look at Project 8 and the specific model we'll be using. Style Transfer. It's a fun project, one that is a great introduction into the math-heavy world of machine learning, less practical than say our iPhone app or Chrome extension, but the good news is the core mechanics remain the same whether we're recognizing digits or training an AI toaster. It's a simple concept. The project takes the content of one image and combines it with the style of another, generating a new image. And honestly, you can make some pretty cool stuff. These are some from the original Style Transfer research paper, which we'll be drawing inspiration from, and I generated a couple more of my own and from members in the Discord, which I'll share at the end. For a quick overview, it works like this. We first set everything up, initialize the model and classes in our script. It's all one file, so the code is pretty manageable. Then we put our images through a small processing pipeline, things like resizing, converting and normalizing, which we'll see in a second. After that, we extract the content features of one image, the main basis and structure of our eventual generated image, and the style features of another, like the textures and patterns. We then calculate this thing called the gram matrix and use it to gradually optimize our generated image, starting from the original content image, adjusting the pixels so its deep features match the content features and structure of the original and the style characteristics of the artwork. And if all that made no sense, don't worry, it will definitely come together as we look at the implementation. Fun side note, originally I tried to create a new model from scratch, a GAN, a generative adversarial network which we briefly mentioned earlier, built to generate totally new images after being trained on a dataset of existing images. For me, that was 1908 Van Gogh pieces. I created the model from scratch, plugging in similar components like convolutional layers to extract features from the paintings. And I guess it worked to a point. It learned something, definitely not in generating new Van Gogh pieces, but you can see over time that it was somewhat moving in the right direction. I guess creating a new deep learning model from scratch is more difficult than it sounds. Definitely possible, but days of training this on a remote server with powerful GPUs while you tweak the model begins to burn a hole in your pocket. Especially when even the smallest GANs trained on the simplest images still typically require tens of thousands of training examples. Like MNIST in our digit recognition dataset, 70,000 total images. So in the interest of completing this video before the universe ends, I switched over to the Style Transfer project, which uses a pre-existing model. And honestly, unless there is a specific reason for developing a novel model, it's a pretty good idea to trust the researchers who have already put in the sleepless nights and countless dollars into their GPU bills. The model we're talking about is VGG19, a 19-layer deep convolutional neural network designed for image classification by the good folks in the Visual Geometry group out of the University of Oxford. Let's run through a breakdown of the model before seeing how we can actually import it in our script. And here's the cool part. We're not going to be using the entire model, only the first half, since we're just working with images, no classification needed. So let's start with the input layer. The model accepts image inputs of 224 by 224, where each pixel is represented by its
RGB values. If we take a simple input example like the one on screen, it's a list of lists of lists, and each innermost array is 3 values, together representing 1 pixel. So if we separate out the color channels, the formation might become clearer, because remember, we also said you can think of it as 3 sets of 2D grids stacked on top of each other, one for each color channel, red, green, and blue. It should also be evident then that this example image would have 9 pixels in total, 3 rows and 3 columns of pixels, where we can describe the image matrix as a 3D tensor of size 3 by 3 by 3, 3 rows and columns of pixels and 3 color channels. Just imagine the 3 2D grids stacked on top of each other. And note, in most programming environments, working with and storing images in memory, the origin of the image starts at the top left and the y-axis goes top to bottom. Don't let this fool you later if you're looking through the code, although all these little details are fully explained in the Patreon tutorial and commented code. After input, we have 16 learnable convolutional layers stacked into 5 convolutional blocks, each using 3 by 3 kernels with some padding. As we can see in the depth labels, for example, each layer in block 1 has 64 kernels, whereas every layer in block 3 has 256 kernels. And as we know, each layer producing the same number of feature channels. For example, layer 1 in block 1 uses 64 kernels and produces 64 feature maps, passes this to layer 2 in block 1, which also outputs 64 feature maps, and of course each layer in block 3 will produce 256 feature maps. And as we can see in this architecture diagram, each single convolution result, meaning the output feature map of each kernel, is passed through a ReLU activation. We also have non-learnable max pooling layers in grey, one after each block, which use a 2 by 2 kernel with a stride of 2, halving the spatial dimensions of the feature maps after each block. So we have padding during convolutions to maintain the image dimensions and feature alignment, meaning the XY positions of the features, and max pooling, which reduces spatial size to really focus on the most distinctive features by taking the maximum values, or the strongest activations, to the next layer. But this also helps to reduce computation, a balance between detail and efficiency. After our final convolution layer, we have a 3D tensor of feature maps, 7 by 7 by 512. To pass this into the first of the 3 dense layers, we need to flatten it into a 1D vector of length 25,088. So we have a flattening layer, not explicitly shown in the diagram, in between convolutional block 5 and the first fully connected layer. Since this model was originally designed for image classification, the final layer is made up of 1000 neurons, which outputs raw unnormalized scores corresponding to the 1000 ImageNet classes it was trained on. Finally, the model passes those values into a softmax activation function, which converts the vector of raw scores into probabilities, ensuring the values sum to 1, highlighting the most likely ImageNet class. And that's the architecture of the convolutional neural network we'll be using: VGG19, 16 convolutional layers and 3 fully connected layers. Now we can finally take a look at the code. We have 6 classes, each with a dedicated responsibility. Main concern in getting this VGG19 model into our code is where to pull it from. We also don't want to go through the trouble of buying GPUs, setting up a bunch of racks, and training this thing over a few weeks. Luckily, PyTorch, an open source machine learning framework developed by Meta, provides this pre-trained VGG19 model, and so we can bring it into our script with this one line here. Accessing just the feature attributes of the model, meaning the convolutional blocks, excluding the classification parts like the flattening and fully connected layers. Obviously, like we said, this is because we're not classifying anything in style transfer, we just want the feature extraction capabilities of the convolutional layers. Finally, since the model is pre-trained, we can freeze the parameters, basically telling PyTorch not to compute gradients of VGG19's parameters when we pass data through the model. And that's the main points of our model setup, alongside some other minor points like deciding which device, CPU or GPU, to run on. Next, we want to load in our images, both style and content. So let's peep the image processor class. We have 3 functions and 2 main responsibilities: loading an image in and transforming it, both style and content going through the same pipeline. After initializing all of our classes, of course, we can then use the image processor to either provide the file path of an image stored locally or the URL of an image hosted online on some web server, and we know all about the inner workings of both options. If it's a URL, we download the image using requests, a Python library for sending HTTP requests and handling responses, and we've already seen similar Python library usage in project number 4. Then we prepare the downloaded image for use in our model. The content attribute of the response object will contain the raw binary data, of course, the HTTP
body in bytes, and side note, in Python this is represented as a \x, and we can see this if we print the content indicated by the B prefix, where each block of 2 characters prefixed with an X escape sequence is a hexadecimal representation of a single byte. Feels good to say we know all about that too. And these very first markers here, like FFD8FF, inform us it's a JPEG image, letting us know the image encoding. Of course, different file types will begin with different unique signatures called magic numbers in their headers. These identify the file format, letting us know what we're working with. So to work with this data, we wrap the response content with this built-in bytes.io Python object, turning the raw bytes into a byte stream. This enables us to interact with the raw bytes as though they were a file in memory, making it compatible to be open and read using the image class from PIL, the Python imaging library. Then finally, whether it's a web-hosted or local image, we ensure it's converted to RGB, 3 channels of color data consistent with the VGG model. Whether that's converting from RGBA, CMYK or grayscale, it doesn't matter. Once loaded, the image still needs to go through a processing pipeline, resizing, converting and normalizing. I think this is one of those things best left for you to look at in your own leisure, but as you can see, all explained right down to every dimension. Next up, we reach some meat and bones of the machine learning side of things. The start of the magic, it's time to look at feature extraction. The feature manager class, which acts as a controller or coordinator delegating the computation to the feature extractor class. Where have we seen that software pattern before? Let's start with the feature extractor class, responsible for, as you can see in the appropriately named function, getting the features. When using these classes, we first call compute features, and the feature manager delegates the bulk of the work to the feature extractor. The main point here is we pass both content and style images through the pre-trained convolutional layers of VGG19, grabbing the intermediate feature maps or activations at each layer and storing them in a dictionary which we'll use later. An important part of our script here is that we are passing the image only through a select few layers. For reference, here is our model again, but with each layer labeled, block number followed by layer number inside that block. We've chosen these layers based on the original style transfer paper, which, as we already know, found that different layers capture different levels of abstraction. Specifically, that lower levels, like conv11, capture fine details and structures, and deeper layers of the model, like conv41, capture more abstract, higher level patterns and spatial arrangements of the image. They also figured out that we don't need every layer to get the job done for this task, just a strategic selection of layers to capture content or style features depending on which image we're working with. As we'll see later, conv layer 42 we use for extracting content features and the rest for extracting style features. Also, the keys of this dictionary on the left are just a reference to the layer indices in PyTorch's implementation of the model architecture, nothing to really worry about. Here's a visualization of a style image passing through a few of these layers so we can put some visuals to the logic. As we said, and as we can see, the earlier layers like conv11 do extract the fine details like the edges of the image, particularly the flower edges. And as we go deeper into conv block 2 and 3, the feature maps produced capture increasingly more abstract patterns, combinations of textures and complex patterns less recognizable to the human eye. And the visualization code using matplotlib is also included in the script if you want to have a play around. Okay, so that's all well and good. In a sense, we've completed our forward pass step, and here's a preview of what we'll be doing later. To optimize our generated image, we'll be comparing its feature activations from the selected layers of the network with the feature activations of the content image and also the style image, reducing the losses between them. But more on that later. Because first, we need to generate an image to begin with. Our starting point is to take the original content image as is and begin to adjust the pixels in a way that aligns best with both content and style. Like we said, we'll be minimizing the loss for both. So it only makes sense to take the original image, well, the one that we pre-processed, and clone it. We're also going to tell PyTorch to track operations on this tensor so gradients can be computed later for the optimization process. Basically, we're treating the entire image tensor as a trainable object where each individual pixel value acts as a parameter that PyTorch will update to minimize the content and style losses. That's our learning process, optimizing the generated image pixels, not the VGG19 kernel weights, as we would when training this model traditionally. And this requires gradline tells PyTorch to track every operation done to this tensor, every convolution applied, every activation, every loss calculation, and all the rest, so that later, as we'll see during backpropagation, PyTorch can trace the full chain of computations and figure out exactly how changing each
pixel value would affect the final loss. Speaking of optimization, let's now take a look at the process, coordinated by a single function in our style transfer class, which overall is the unit responsible for managing the entire optimization process. After generating our starting point image, we call the optimize function with a default number of 5000 training steps, saving images every 250 so we can track the progress. Here's our optimization function inside the style transfer class. We use the Atom Optimizer, something we cover in the tutorial, but simply put, it's the algorithm that will carry out the pixel adjustments, a type of gradient descent update rule, and I've found a learning rate of 0.003 works quite well, balancing fast convergence with stable updates. So in this line, we're just creating the optimizer. We're not actually doing anything with it just yet. Then in the next line, we're creating a progress bar that will run for the total number of training steps using the TQDM library. Then inside our optimization loop, for each single one of these training steps, the very first thing we do is pass the generated image through the same pre-selected layers of the VGG model to extract its features, just like we did for the content and style images. Now we have three separate components at the heart of our optimization: the feature map dictionaries of the generated content and style images. This allows us to compare them separately, meaning we compute the content loss by comparing the generated image features to the content image features, and the style loss by comparing the generated image features to the style image features. And then after, we'll combine them into a single scalar value, our total loss, which will serve as the optimization objective for how we'll adjust the pixels of our generated image. So this next section on how we compute the losses is everything we've been building towards, particularly the style loss, an awesome bit of genius math mixed with programming know-how and machine learning theory. This compute losses function in our style transfer class returns both content and style loss. Let's begin with the content loss since it's a lot simpler. Essentially, we compare the feature maps of the generated image to the content image feature maps we extracted earlier. In other words, comparing the current state of our model's output to the target. Of course, we are trying to balance both content and style, so this is just one of our targets for now. And this is exactly the same process we did with our earlier model's digit recognition predictions, comparing them to the labeled target, what we actually want the model to output, except this time we're comparing feature maps, not digit prediction scores. And we do this comparing the feature maps by calculating the mean squared error between the two sets of feature maps at one specific layer, block 4 layer 2. Why? Well, this was another design choice based on the findings from the original style transfer paper. Choosing this single deep layer is not only much more efficient, but is also a good representation of the features we want to retain for the content specifically, the spatial arrangements of objects and major forms in the image without being too heavily influenced by low-level features like edges and textures, where we're happy for the style to take influence. So again, even though we have the full dictionary of the original content image feature maps, we are only using this one layer. And so that's it for calculating content loss, summarized neatly for us in this one image. Now for the style loss. We first initialize the scalar style loss value at 0, and in this case we do go through all those pre-selected layers we extracted the feature maps from, conv11 to conv51, executing the code you see in front of you on the right for each single one of those layers. We'll approach this by breaking down the style loss computation into 6 digestible steps you see on the left. So before step 1, let's quickly see how we're kicking off our style loss code. We loop through this thing called style weights. This is a dictionary where the keys are the names of the pre-selected convolutional layers in our model, and the values are some weights which we'll see in action later. So step 1 is to grab the feature map of the generated image from our generated image feature map dictionary for the current layer. That's easy, we just index that dictionary which we called target feature set, using the layer name of course. That's the key from our style weights dictionary which we're currently looping over. This gives us the feature map tensor for the layer we're currently iterating over, and then we calculate its gram matrix. Let's pause there on our style loss calculation and ask ourselves the question, what is a gram matrix? I promise you this is the last bit of math we'll do for this project, but it's a cool bit of math. It's another linear algebra computation. As we can see defined on Wiki, it's a generic mathematical operation we can apply to vectors, but we don't need to read all that. More relevant to us in image processing, a gram matrix is a matrix that captures the correlations between the different feature maps produced at a given layer, how strongly patterns or features like edges and textures co-occur across different feature maps. This correlation will give us the style fingerprint, not where the features occur in the image, but how frequently and how strongly, a true representation of style. And as you can see in the image on screen, we're calculating the gram matrix for a set of 5 feature maps per row. We can imagine this set of 5 is the output for from one convolutional layer, our feature map tensor. We can pass in as many feature maps as we want, we just end up with a larger and larger gram matrix. The point is though that eventually we can compute the gram matrices of the generated image and the style image at each layer to measure the similarity in terms of feature correlations regardless of where those features are located spatially. So this will make more sense as we walk through an example, and you'll be pleased to hear only two steps in computing a gram matrix: reshape and multiply. To reshape, let's remember that each feature map is the output of a single kernel in a convolutional layer, each capturing some specific visual pattern or feature in an image. Naturally then, the spatial information is embedded into the output, whereas the essence of style is to care about the features themselves, not their specific spatial XY positions. That's for the content to worry about. So the shape of a feature map tensor is channel height width. To compare for computing the correlations between features, we flatten the spatial dimensions into a single dimension. We do this by flattening the feature map stack from a 3D tensor to a single 2D matrix, where each row corresponds to one kernel's activations. So each feature map is now squeezed into a single row. And let's be clear at this point, the spatial features are still represented in the flattened 2D matrix. For example, the top right activation of each feature map corresponding to the top right pixel region of the original image will be the last value in each row of the flattened 2D matrix. But the key point is, when we come to calculate the gram matrix, the spatial patterns will be removed. But first, let's see the reshaping in action. Here's a feature map tensor of two channels, each a 2x2 grid of height and width, an overall feature map of shape 2x2x2, and as you can see, we flatten each channel into a 4-column row, making the total feature map tensor a 2x4 matrix. Now this reshaped matrix is ready to be used for computing the gram matrix. It's a simple step 2. We multiply the flattened matrix by its own transpose. The transposed matrix, as you can see from the middle of the image, is just the same matrix with each row and column interchanged. Taking the dot product of the feature map matrix with its transpose gives us the gram matrix, a matrix of shape CC where C is the number of feature channels. As you can see, full circle, the diagonal values are the self-correlations, how strongly a single filter activates across all the different spatial locations of the image. So if a filter detects brushstroke-like textures, a high diagonal value means this texture appears strongly and frequently across all the different parts of the image. The off-diagonal values in the gram matrix represent how strongly two different filters activate together across the image based on their feature map activations. For example, if one filter detects curved edges and another detects dots, a high off-diagonal value means those two features often appear in the same regions, a combined stylistic pattern. So ultimately, you can see how this gram matrix captures the different style relationships that exist in an image. Let's see a quick example of this second multiplication part in action. We take the reshaped 2D matrix from step 1, transpose it, and perform the multiplications, the dot products between the rows, and that gives us the gram matrix. More importantly though is what we can discern from this gram matrix, the feature correlations. It's definitely not the most intuitive bit of math, especially layering in so much context of neural nets, kernels, feature maps, and the objective of our style transfer project. But having said that, let's get back to what this math is powering. Reminder that we want to calculate both the content and style loss of the generated image so that we can use both values to guide our pixel adjustments. The content loss was simple. It was the MSE of a single convolutional layer. And step 1 in computing the style loss was calculating the gram matrix of the generated image for the current pre-selected layer in our loop, capturing how strongly different feature channels activate together, essentially measuring the patterns without the spatial information. Step 2 is to get the gram matrix of the style image for the same layer. Well, we've just seen how to do that in principle, so in step 2 we can see the code for it, since it will be the same logic regardless of the generated or style input image. Thankfully, PyTorch has gone to the trouble of writing all the complex mathematical code for us to implement this easily. We just need to handle the reshaping, the first of our two simple steps, so we flatten by multiplying the height and width of each feature map into a single dimension. Then we pass in the flattened matrix and its transpose, taking the dot product of the rows for step 2. Easy.
Nice.
The only thing worth mentioning here in step 2 is we're just getting the style gram matrix for the layer which we actually computed earlier. We did this when first initializing the style transfer class, making a dictionary where the key is the layer name and the value is the gram matrix. Of course, the gram matrices for the style are not going to change at all. We're optimizing the generated image, not the style. That's why in step 1 we compute the gram matrix for the generated image for each layer at each training step and not the style. Regardless, at the core, the code for for computing the gram matrices is still the same. So it's good to see our conceptual knowledge in practice in Python. Now that we have the 2 gram matrices ready, we can finally compute the mean squared error between them for that layer. So pretty straightforward for step 3. Step 4, all layers are created equally, but some more equal than others. We apply weighting to the loss depending on the layer using the style weights we mentioned earlier, which we're actually looping over. And as you can see, earlier layers are weighted more heavily. This is to emphasize the finer textures and low-level patterns like brush strokes and edges, low-level aesthetics that are more prominent in the earlier layers, helping emphasize the visual style. Step 5 is to normalize the loss. When we compute the style loss for a given layer, we're taking the difference between the gram matrices, which themselves come from a layer's feature map tensor. Layers with larger feature map tensors, for example more channels or bigger matrix dimensions, will produce larger losses. Of course, because there are more numbers being summed in the MSE. By dividing the loss by the total number of elements in the feature map, we're removing the size bias and making the loss for each layer fairly comparable across different shapes. In other words, by normalizing the style loss, we're ensuring the strength of the style mismatch is the focus of our measurement, independent of the raw size of feature maps for a layer. And finally, step 6 is to take this normalized loss value for the layer and add it to the style loss we initialized at 0 at the start of this journey. Then we repeat this whole process for the next layer and the next and the next. And that's all in one single training step, giving us a single scalar total style loss value. And here's a neat little overview of the entire style loss process. Pat yourself on the back, soldier, because now we're through the worst of it. Now back in our optimization loop, we have both the content and style loss, so we can combine them to get the total loss. Again, adding another layer of complexity by applying weighting with how we wish the generated image to lean towards, more stylistic or more grounded in the content. We set these hyperparameters with default values when first initializing our style transfer class. Generally, we want a significantly larger style weight so the style can dominate the optimization, giving us the cool images we've been working so hard towards. So adding the 2 scalar values gives us another scalar value which we can finally start reducing, our guide for walking towards the Eiffel Tower. And we do just that through a classic 3-step loop in the second half of our optimization function. First, clearing any previously stored gradients from the previous training step. That's just common sense since we want to calculate new gradients after parameter updates and new loss calculations. Of course, on the very first training step, there will be no gradient values. Either way, these are stored in the grad attribute of the generated image tensor itself, managed by the optimizer since we set that up when passing the image tensor into the optimizer. Second, we call total loss.backward. A bit of low-level framework specifics, but regardless, what happens here is PyTorch takes the computational graph that began when we initialized our generated image with requires grad equals true and was fully constructed in the forward pass, taking that graph and traversing it in reverse, backpropagating through the network using the chain rule, calculating how each pixel in the generated image should change to reduce the total loss. The important thing is we know all about the fundamentals of this backpropagation process, so whichever machine learning framework we're using will be okay, and in that case I'll spare you the headache of going through the mechanics once more. Then finally we can update those pixel values using the optimizer by calling optimizer.step, which applies the gradient descent update rule, slightly adjusting the RGB values of each pixel in the direction that reduces the total loss. And that's one training step complete, each one edging us ever closer to our image of reptilian Zuckerberg. After all this math and code, I was a bit lost for more creative image ideas, so I reached out on X and nobody replied, sadly. So if you want to be my friend and help me out in the future, give me a follow at Stony Codes. So I reached out to the Stony Codes Discord and luckily the Patreon members had my back. Thanks guys. And this image of Michael Jordan and this weird, slightly scary abstract art piece also turned out pretty nicely. And here's also a few more favorites I cooked up. Also, don't forget to run the script yourselves and feel the satisfaction of watching this progress bar trot along, knowing that you know every single detail behind every single training step. And with that, I can finally say we've reached the end of our deep learning project. I promised you at the start you'll understand these images on screen, and I think it's safe to say that's covered and then some. No doubt one of our most technical projects so far, so if you managed to follow along, even just the general ideas behind why we were doing things, then that's a big win. Hopefully then this gives you the starting point to experience the mechanics behind machine learning and neural networks, the type of code and math at play, and most importantly, whether you like it. One more area of computer science and software engineering we can tick off our list. Project 9 is one of my personal favorites. It all started from a meme which I'm sure we've all seen before if you're as chronically online as I am. Originally posted on Reddit, this image of a snowy walkway by a lake in Istanbul blew up in the fellow memer community as people took it to other platforms and captioned it, "The masculine urge to slowly bleed out here," a reference to the noble fate many male heroes face as they meet their end, slowly passing alone in a peaceful setting. Spoiler alert, here's a few examples. Officer K, Logan, Jon Snow, Boromir and Arthur Morgan, all facing a true hero's end. Seeing the meme made me want to go out like that, or at least to experience it, to be inside the image, hear the blizzard and feel the snow. So of course I did what any builder, developer, engineer would do. I made the image a whole new world, one I could visit whenever I had the masculine urge to bleed out in the snow. We'll be building this virtual reality world with Unity, one of the two most popular game engines, the other being Unreal Engine. So first, we'll take a look at how to navigate our way around the Unity editor and the main foundational building blocks that allow us to build any Unity application we want. 2D, 3D, mobile, PC, VR, AR, games, simulations, and all the rest. We'll see how to set up a VR app, all the developer configuration, and along with the basic building blocks are systems, like the physics and rendering system. We'll choose to take a deeper look at one, the input system. Then, more specific to VR, we'll take a look at how we can set up rigs, the bones and joints connecting a character's 3D skeleton to our VR controllers. Then finally, we'll switch it up and see how we can build the environment of our world. Terrains, trees, buildings, audio, snow, fog, water, and more. So let's start with Unity, a game engine first released in 2005 for macOS and subsequently extended to support all types of platforms. Starting with Unity 1.0, now sitting at Unity 6.0. What we're looking at is the Unity editor. We also have Unity Hub, a standalone application for managing our Unity projects and any installations like build support modules to target certain platforms. We can loosely think of these build support modules like Node.js packages, optional add-ons you install depending on what you want to do. Except in Unity's case, they enable building for specific platforms rather than adding runtime features. Let's create a new 3D project using the Universal 3D template. Universal refers to the Universal Rendering Pipeline. It's one of Unity's rendering pipelines, a system that defines how graphics are rendered. We could get deep into the differences, but the main thing for now is URP is a happy medium between quality and performance. After creating your project, Unity Hub will launch the editor. This is where you will become the architect of brand new worlds. If this is your first time opening the editor, it will look something like this, quite bare. You can click and drag different windows however you like, but I prefer a setup like this. Let's go through each window and at the same time all of the fundamental concepts for building projects in Unity. In the center in red is our scene view, the container for our application or game environment. The scene view holds all the objects, characters, lighting, player cameras, sound, everything that makes up a specific scene. And an application can have multiple scenes. For example, different levels in a game, leaving the sandbox world and entering a building, two separate scenes, or more simply in Flappy Bird for example, one scene for the main menu and another for the game. The green box is our game view, which we can switch out for the scene view or display both, it's totally up to us. This view displays how the project will look from the player's camera perspective after building and running the project. It's another useful view to help us organize and manage objects. And here's a note to save yourself some pain. You can run the game and play via game view for a real runtime experience without having to build and deploy a full standalone application. But any changes made in play mode from the scene view, like moving an object's position, do not save, since they're happening at runtime. Flashback to an earlier project, and you'll know this means Unity is loading our scene and all the contained objects into the RAM for running our game. And when we exit the simulation, Unity will discard these changes and revert to the state of the project on disk. On the left, I like to put the hierarchy view. This is the window that lists all the objects in the current scene, including cameras, lights, and 3D models. Game objects is the official term Unity
Unity uses for all these items. Everything in the scene view will be represented in a digestible way here in the hierarchy, where we can nest different game objects, creating a tree-like structure. We can also make custom folders, color code, hide and unhide objects, and every other file directory feature that makes a game manageable to develop. On the right is where I've placed the inspector. This displays detailed information about a game object selected from the hierarchy or directly from the scene view. The inspector allows us to edit the object's properties, such as changing its transform properties, meaning its X, Y, Z position in the scene. In the inspector, we can also apply components to the game object. Components are the functional building blocks we can attach to game objects that apply some behavior or appearance change to the object. For example, rigid body, a built-in Unity component that adds physics behavior like gravity to game objects, or the built-in light component which gives an object the ability to emit light, illuminating the scene. We also have the option to attach custom scripts, C# code modules that again control some aspect of a game object's behavior. Scripts are a type of component, but we can think of them as custom written compared to built-in Unity components, which are also just scripts under the hood but pre-written. For example, we can create a custom script like the one on screen and call it playercontroller.cs for C# with a method like run and attach it to our game object, some 3D model which represents our player. And don't worry about the details of the code for now, we'll be making our own scripts and using all different types of components, so at the moment just recognize that components and scripts are a thing to manipulate our game objects. Anytime we select a game object, either in the hierarchy or the scene view, the inspector will display the object's information and attached components. Down in purple at the bottom, we have the project window. This contains and displays all the possible files related to our project. We call all these files the assets, a branching terminology which covers everything: the game objects, textures and materials, audio clips, even the scenes themselves. Everything is an asset. Or more specifically, everything in the project window is an asset. And when opened, the scene is instantiated and all the elements inside being instances of those assets. Prefabs, which you can see all over the screen in both project window examples, are also an asset, an important one. Another fundamental concept in Unity, the prefab is a reusable template for a game object. We can create and configure a game object, complete with all its components and property values, even its child game objects, and store it as a prefab. A super useful tool which obviously speeds up development by orders of magnitude. For example, when we visit the Unity Assets Store, an online marketplace with all types of free and paid assets you can imagine, anytime we download a game object, whether it be a character model or an environment object, we're getting a prefab. So we can simply click and drag it into our scene, saving us from reinventing the wheel every time. And finally, we have the console in pink here down by the project window. This is very much like the developer console we've seen before in our JavaScript projects. Here we can check outputs like logs from builds, warnings, errors, and any other message essential for developing and debugging in Unity. These messages come from our project's code whenever we write debug.log, error or warning, much like console log and console error in JavaScript. And this is an important note. Everything we've just described, game objects like characters, components like light and rigid body, Unity's systems like physics, it's all just code. Think back to our desktop application project. All these built-in tools that make it easy to work with the project in the editor, even the editor itself. It's all code. Processes executing on the machine's CPU in conjunction with the RAM, handled by the OS to render it all on the screen. Of course, this is an insanely large and complex task to put this game engine together, along with the editor that allows us to build and manage global games and applications like Pokemon Go, Among Us, Superhot VR, and NASA's EYES visualizers, interactive 3D applications for all kinds of spacefaring journeys. And Unity is even being used by AI labs like DeepMind to train and test state-of-the-art AI agents. So commendable shout out to the founders and team behind Unity. Let's now use this foundation we've built to set up a basic VR game. We'll use another of the templates Unity provides, the VR Core template. This will save us a lot of development time by setting up some VR basics like hand tracking and headset rigging, which we'll see in a second. First though, regardless of the project we create, there are a few configuration steps we should always take. First, we'll check out the project build settings under the File menu option. Here we can choose the target environment, or build profile it's called. For example, we can target Android devices, Vision OS, macOS, which is active by default since I'm working on a MacBook, or we can target any of the other platforms you see in front of you. And to keep it simple, a build profile is essentially just a settings file which includes instructions on how a project is compiled, packaged, and optimized for that specific platform. For this project, I'll be using a second-hand MetaQuest 3 I bought off eBay for almost $500 RIP bank account. The MetaQuest headset runs Meta Horizon OS, an Android-based fork.
We are releasing Meta Horizon OS, our operating system that powers Quest virtual and mixed reality headsets. We've been building Meta Horizon OS for about a decade. We started building it off Android.
So you heard Zuck. We'll switch the platform to Android since that's where the app will be running on the headset. Next, we'll head over to the full project settings under the edit menu option and scroll all the way down to XR plugin management. You'll have to install this for each VR project you create since this package isn't shared across Unity installs. So this Unity package acts as a system that helps streamline the management of XR software development kits. These are SDKs that include APIs, device support, and libraries for building apps on platforms like Oculus, Windows Mixed Reality, and all the rest. XR is the umbrella term for all immersive technologies like VR, virtual reality, AR, augmented reality, and MR, mixed reality. And all these options, the plugin providers we can select in the project settings, refer to the XR runtime environments Unity will use. For example, as we've seen before in Project 6, Node.js was the runtime that provides all the tools necessary for JavaScript to execute outside the browser, like the compiler inside V8 and different libraries for things like handling networking and cryptography. Well, the XR runtime is similar, providing all the tools needed for XR apps to execute on a given device, bridging the gap between your Unity code and the hardware. So let's break this down. At build time, so when building our app, Unity will include all the appropriate native libraries from the chosen SDK in the final build, setting up our application to work with the APIs and systems provided by the selected XR runtime, the runtime of our device. For example, if we use the Oculus XR plugin, we can call APIs from the Oculus SDK like OVR input to read controller input. Oculus being the XR runtime for MetaQuest devices, the company that built the headsets which Meta acquired. So then, of course, we need the intermediate libraries from the SDK included in the build. The libraries that bridge the gap between the Oculus SDK and the Oculus runtime, which Unity ensures are packaged in the final build based on our selected XR plugin. So in summary, the runtime is the low-level environment, the collection of software that enables our build to actually execute by interacting with the hardware. The XR plugin is a higher-level abstraction, Unity's package that wraps the vendor's SDK so we can use it inside the Unity environment, for example by wrapping its native libraries and APIs in Unity-compatible components. So at runtime, the XR runtime environment, enabled via the selected plugin, can handle all the communication between the application and the XR hardware, managing tasks like head tracking, controller input, rendering, and any other device-specific features. The desktop options are for VR headsets that support PC-based running, built to run on the PC, which handles all the heavy processing, and streams the output to the headset in real time. We'll be running our app on the headset directly, so in the Android options tab, we'll enable Oculus. This tells Unity we'll be using the Oculus XR runtime environment when building for Android. We could also select OpenXR, a growing cross-platform standard compatible with many devices, including the Quest. In practical terms, VR devices come with the OpenXR runtime pre-installed, as well as their own runtimes like the Oculus runtime. Targeting the OpenXR build in Unity makes our app compatible with all these OpenXR-supported runtimes also. However, for this project, I'm targeting a single MetaQuest device, so I went with the Oculus plugin. But for most production or multi-device projects, you'll want to use OpenXR, which has now become the industry standard. So to recap, the build profile is the overarching target platform, and XR plugin management is the Unity layer beneath it where we enable the XR plugin for the provider appropriate to that platform. The plugin integrates the vendor's SDK, allowing our Unity app to communicate with the XR runtime installed on the device or PC. And here's an overview table which should help make these different use cases a little more clear. There's a few more configuration things we have to set up if we're we're targeting the Quest 3, but it's a bit boring and doesn't teach us too much more, so I'll leave that for you to read in the tutorial on the Patreon, and instead let's focus on something else, the actual project we just created. Here's the expanded hierarchy of our scene set up for us by the VR Core template. Let's run through this and develop an understanding of the building blocks that create a VR application. Of course, project to project this may differ, but the core pieces remain the same. At the very top we have the XR origin. This represents the user's physical space in the virtual world. In practicality, it's a container that manages all this user stuff: camera, headset, controllers, and locomotion, meaning movement, all centrally managed by the XR origin component script attached to the XR origin game object. It's responsible for things like setting the tracking origin mode, which defines where Unity places the origin 000 relative to the user. Is it the floor, the headset, or some unbounded, unfixed point that will differ depending on the app? As you can see in the code example, particularly the first snippet, the script component is able to accept and use variables from the Unity editor in the inspector. We call these serialized fields, or serialized properties, initialized in C# using the serialized field attribute. And what's good is we know all about the power of attributes from our mobile app project. The offsetting of the camera is applied to the child camera offset game object. There's not much else to the camera offset object apart from what it's a container for, because the next level down in the hierarchy we have the main camera. This is the actual camera that renders the scene from the user's point of view, our eyes in the virtual world linked to the VR headset. Taking a look in the inspector panel, we see the main camera has a few critical components attached. We won't have the time to go through every game object and component in this template scene, but for sure we'll highlight the most important ones as we continue to go through the setup of a VR project. A very important one is of course the built-in camera component. In standard Unity projects, you can add as many cameras as you like and switch between them. In VR, the XR runtime expects one headset-driven camera, so switching perspectives means changing that camera's transform properties. For this template though, we'll keep it simple and stick to the one default XR camera and not do anything crazy with different perspectives. There's a bunch of options we can tweak here under the camera component in the inspector. I'll give you two: the culling mask and clipping planes. The clipping planes determine the range of objects rendered by the camera, preventing objects that are too close from blocking the player's view and excluding objects that are too far away to avoid unnecessary rendering. We can also select which layers of objects the camera will render, our culling mask. For example, imagine we're entering a cutscene or we're in a game mode like hardcore in Call of Duty. We will probably choose to hide the player's heads-up display, the minimap, the health bar, and all the rest. Another important component is the tracked pose driver. This component applies the current pose value of a tracked device to the transform of the game object. The pose value is the position and rotation. So the component takes the position and rotation of a tracked device like the VR headset or hand controllers and applies that positional change to the transform property of the game object, usually updating it every frame. The transform property, like we said before, is just the position, rotation, and also scale of the game object in our virtual 3D world. So as you can see in the component in our template app, we choose to track both position and rotation as well as which inputs. In this case, it's which physical pose inputs should update the transform of the camera. Of course, that physical device will be our extended reality input XRI headset. So that's our camera. And of course, not every game object needs a physical presence. Here, as indicated by the camera gizmo, this white indicator, it exists purely as a kind of logical object. Even our empty parent containers in the hierarchy, game objects too. Next, let's take a look at the controllers, starting with the left, which is basically the same as the right, both created with pretty similar concepts to the camera/headset setup. In the inspector, we can again see a bunch of components, each responsible for enabling some modularized functionality. The tracked pose driver again, managing the controller's position in the VR world. A controller input action manager script, a kind of traffic controller for ensuring user movement, teleportation, object manipulation, and in-game UI interactions all work and switch smoothly without any conflict. For example, these functions in the script which enable and disable movement while interacting with objects, where array is this in-game laser-like line to help a player interact with distant objects. These controller actions fields in the controller input action manager script are the different controller actions/button mappings and provide a reference for the script to know which actions to listen for on the controller and what they should do in the game. We call each one of these fields an input action reference, and it's coming from Unity's input system, which will take a
closer look at later. We also have a haptic impulse script which enables feedback through the physical controller with vibrations when interacting with virtual game objects, for example when picking something up. Under the left controller game object, we have some child game objects, mostly for handling interactions with the VR world through the controller like poking things or teleporting, as well as the left controller visual, a 3D model to help increase the immersion and improve the in-game user experience. Also inside the XR origin, on the same hierarchy level as the camera, we have the locomotion game object. It's the container that manages at a high level the various movement systems in the template project. 360 thumbstick movement, snap turning by flicking the thumbstick, teleportation by holding the thumbstick forward, climbing, jumping, and all the rest. Managing this heap of action are two script components. The locomotion mediator, which is the central manager, for example ensuring only one type of movement is active at a time, and the XR body transformer, responsible for actually applying the movement to the entire XR origin by transforming its position. Hence why we pass in the XR origin as the target game object for the script. And here's a snippet from the XR body transformer to help remind us it's all just code under the hood. Details and syntax aside, the main point is the method manages how transformations are queued and applied in priority order to smoothly control the player's movement. Within the locomotion object, we have containers for the different actions. Let's see how we can move as an example. Attached to this container is one script named Dynamic Move Provider. This script takes in a bunch of properties like the move speed scale factor, the forward source, defining which object's forward direction is the forward direction for the movement, and we also have the action input source, meaning which controller input will trigger that movement, as well as a few more configuration options. Inside the Dynamic Move Provider script, we use all these properties to enable smooth thumbstick movement with either controller using functions like compute desired move to calculate the move direction and amount. You'll notice the input parameter is a 2D vector mapped to a 3D output. This is because we can only move left and right and forward and back with the thumbstick mapped to our virtual 3D world where our Y position stays fixed, meaning our up and down position, since that vertical movement is handled inside our jump logic. Now I'll quickly mention the game objects outside of our player. These are a bit simpler. For example, the interactables. Here we have a bunch of objects we can grab and throw about. As you can see in the inspector for one of these objects, we use a prefab to make life easy. And of course, we can place them around the scene by adjusting the transform component. Since it's a physical object in the virtual world, we need to attach some physical properties like a box collider, defining the cube's collision boundary, and a rigid body, enabling physics like gravity and movement through space. And there's also a couple of self-explanatory grabbing scripts handling the lower level logic for that. Finally, at the bottom here, we see the material. This defines how the surface of an object looks, its color, shine, smoothness, and more. Within the material, we can assign a texture, a 2D image that adds visual patterns or colors like wood grain or scratches. We also see a map field. This can add the illusion of 3D surface details like bumps and dents using clever lighting tricks, even though it's still just a 2D image. What's good is we can find everything we would ever want in the asset store. Who knew stone, dirt, and grass could be so popular? By now, I'm sure you're getting the idea of how all these different building blocks piece together to create different bits of functionality in our project. And let's not get it twisted. It's definitely not simple, especially from the perspective of the codebase, the biggest codebase we've encountered in this series so far. Although working with the editor does make life a bit easier. Now that we understand the building blocks of a VR project, like game objects and scripts, as well as how they all piece together to build a basic scene in Unity, let's now take a look at systems. Systems in Unity are built-in frameworks that manage some core aspect of the engine's functionality, like input, physics, or rendering. We'll pick one to focus on, the input system, which helps us manage inputs from various device types, from keyboards to touchscreens, console controllers to VR controllers. The execution flow of the input system goes physical device, actions asset, player input component, which can be optional, and the script. Let's see how this works in a 2D game. It will be easier to understand at first, and then we can mentally extrapolate to 3D and VR applications. In Unity Hub, I'm going to create a new 2D project using another Unity template. It gives us nothing but a camera and a light. We can run the game, but of course there's nothing to run. So let's add a game object for our player using the sprite preset and go for a good old square. A sprite is just a 2D image or animation, some kind of graphic, used to represent characters, objects, or UI elements in a 2D game. So we'll also add a rigid body 2D to give our square player some
physical presence within the 2D world, and we'll see this come into play later. So with our player ready to go, and of course we can't press any buttons on our input device since we've not set anything up, step 1 becomes creating a new input action set. Pretty easy actually. Inside our project window, right-click, create new input actions, and call it something like player controls. Double-clicking this will open the input actions editor, where we can easily create new action maps. So to be clear on the understanding, the input actions asset we just created is the top-level file storing all our action maps. An action map is a group of related input actions. We can group by device like left and right controller, or by context like movement, interaction, or combat. So we'll create the player action map and define a new action inside named move forward, a value of type button. Nested inside an action, we define bindings. A binding is the link between the physical input control, like a key on the keyboard, and the action it triggers, like jumping or moving forward. Let's create a new binding under the move forward action and set the path to the W key on the keyboard. And let's not forget to save the asset once we're done. After this, we have multiple options for step 2. Like we said, the player input component is optional, so with the manual script approach, we write a custom script, instantiate the input action class, and manually subscribe to input events for full control over the behavior. Alternatively, we can use the built-in player input component. This still requires a script, but is intended to make the process less verbose by leveraging the editor to hook some things up. Within this approach, we can choose to invoke Unity events, where we connect methods from the script directly to the input actions, or the send messages approach, which automatically looks at the script without any wiring in the inspector. The tutorial covers all approaches, so for now we'll pick one. Let's go with the player input component and invoke Unity events behavior. So to work with the input system through the player input component, let's first write the script that defines the player's movement. So we'll quickly create a new player controller script, open it up, and it gives you this bare bones boilerplate. But here's one I made earlier to get the forward movement working. We first import core Unity features with the Unity engine and import the Unity input system for accessing the input system classes. Then we create a player controller class that inherits from the mono behavior class, a fundamental base class for most C# scripts attached to game objects. It provides predefined lifecycle functions known in Unity as messages that are automatically called by the engine if they are defined in our script. For example, the awake method immediately called when the script is loaded, or fixed update called at fixed intervals tied to the engine's physics system update cycle. After that, we declare a few variables like move speed of type float, and since it's declared as a public variable, Unity automatically serializes it, making it an editable property in the inspector, as we can see on the left. The rigid body variable, which we use to apply the physics-based movement to the player object. We use Unity's built-in getComponent function to automatically grab the rigid body 2D component, avoiding having to manually assign it to the script in the inspector. The third and final variable is move input of type vector2, used to store the direction in 2 dimensions, x for left and right, and y for forward and back. Controllers will also be able to register the strength of the movement via the thumbstick, but we're using a keyboard, so it's either a 0 or a 1 on each axis. Let's now see how these variables come together to give our square a breath of life. Starting with the onMoveForward function. The context read value float line from the Unity input system import gives us a 1 when the key is pressed and a 0 when released based on the context passed into the function. And we'll see how this function gets called with this context parameter in a second. Then the important part, we use that input value, 1 or 0, to update our move input vector. For now, you can see we're just updating the y-axis. Move forward when 1, or do not move forward when 0. Also, a bit of lower level computing for you. Each time onMoveForward is called, we create a new vector2 value. But flashback to stacks and heaps, it's not a problem since it's a lightweight struct that lives on the stack. So this vector gets used back in the regularly called fixed update function to define how much force to apply, along with the move speed multiplier, to the square player using the rigid body component and its linear velocity property. So the last piece of the puzzle with this approach is to tell Unity to call this onMoveForward function in our script when the user presses W, otherwise the linear velocity will never change. Thanks to the player input component, we can easily configure this connection under player in events, dragging the square game object from the hierarchy as our object to act on, and also by linking the MoveForward action from our input action asset we created earlier to the onMoveForward method in our script. And it's as simple as that. Now if we hit play, our little guy can move up. Just look at him go. We can even add gravity in the rigid body component and give him some resistance
distance. So much fun. Truly a AAA game. Now let's quickly speedrun how we can give this little guy full 360 movement. Back in the input actions editor, let's rename the move forward action to move and make it a vector2 value. This means the action will now capture two-dimensional input, in this case a directional axis like WASD or a gamepad stick instead of just a single on-off button press. Then we'll remove the existing binding and create a new up-down left-right composite binding and assign the movement keys. This 2D vector composite is a special type of binding that combines multiple key inputs like WASD or the arrow keys into a single 2D vector value representing directional movement. The alternative is to treat each key as separate, requiring an individual function to handle each direction on move forward as we had before, but also on move left, right, and backwards. Using this composite input setup, all we need to do back in our script is update the name of the moving function to match our input action on move and replace the two lines with this one. Move input equals context read value vector2. Since now Unity is automatically handling the direction calculation for us through the special 2D vector composite binding, merging all the directional keys into a single vector value. Let's not forget to update the player input component since we changed the function name, same input action asset we created named player controls, and acting on the same square object but a new function. And now if we hit play, our character is free to roam this beautiful blue wasteland to its square heart's content. And that's honestly all the core mechanics of the input system. We can of course scale up the complexity with 3D models, different controller support, and start tying in different Unity systems like animation and physics. However, for now I think we get the idea. A good case study to deep dive one of Unity's systems and see how we can create functionality working with both the editor and through custom C# scripting. Not too bad, eh? Now we have a feel for general game development in Unity and VR specific development, we're ready to look at building our game. Although game feels like a bit of an understatement. What we're really trying to build here is a realistic and fully immersive experience. As you can tell, building this all from scratch is a big undertaking, and quite frankly can be an unwise approach. It would be like writing the backpropagation algorithm from our last project from scratch, instead of just using the existing PyTorch modules. And believe I tried. Kinematics, targets, constraints, animations, custom scripts on Mixamo models, the lot. Ultimately, I settled on VRIF from the Unity Asset Store, a VR interaction framework. If you watched my previous video, you'll know my philosophy on paid products. The very first programming course I took, I paid for on Udemy. I think 1, paid products are usually a better standard than free alternatives, since the creator has an obligation to fulfill expectations. I think 2, they almost always come with regular updates and maintenance, including written documentation, YouTube tutorials, and in this case Discord support, where the main dev himself is quite active. 3, you feel a sense of obligation to yourself to commit to using the product, finishing the course, or completing whatever the product is offering. And finally, 4, it's a good way to support the community and developers who are trying to give back value and create something outside of big companies. So the setup is easy. We can begin with a brand new universal 3D project to avoid any potential conflicts between the XR template we used earlier and VRIF's own XR setup. Like most assets we download from the store, we open up the Unity package manager and install our purchased asset. You can think of this in some loose sense like doing an npm install, pulling the assets and dependencies into our project. After that's installed, we'll find the package folder in our project window. If we load up one of the demo scenes, you can see the framework provides a monumental amount of functionality. We're talking full body rigging, animations, interactions, movement, and a great deal more. Although we still have work to do for creating our custom projects, of course. To get us started, we'll open up a full body demo scene that contains a full body player rig. I hate to stop the fun these guys are having, but we've got things to do. So we'll remove everything in the scene except for the player and the environment for now. As you can see from the hierarchy, it's a very similar setup to Unity's VR template which we walked through earlier. We have a dedicated game object for the XR player, our central container for all things player related, interactions, headset and controller tracking, locomotion and more, as well as mapping this all to the full body avatar. The tutorial on the Patreon goes through the full setup in this hierarchy, like all the components you see here on the XR full body rig, including this input bridge component, a standardization layer to integrate various input systems from Oculus to Steam VR, mapping different buttons to the default VRIF input action asset. We also go through all the components here on the player controller object, object, as well as others like the camera rig and the soldier rig, so we won't go through it all here. It's there for those of you interested in learning more, plus I think we've already managed to develop a strong sense of how these VR Lego bricks might work in a project like this anyway. Instead, we'll look at the implementation of full body tracking and animating this full body into a seated position, because remember, the whole objective is to enter this meme, and this spot right here on this bench seems a pretty good place to be. So as we've seen before, we have the camera set up, in this case a center eye anchor object with the main camera component attached, tracking and translating headset movement to the VR world, and the same for our left and right controllers, again through the tracked pose drivers and custom VRIF scripts. To make our avatar's body follow these same tracked physical device movements, we use inverse kinematics. Kinematics is the study and calculation of motion, including position, velocity, and acceleration without considering the forces that cause the motion, basically how things move rather than why. And there's two types of kinematics. In the context of controlling avatars, there's forward kinematics, which calculates the position of the end of a limb from known joint angles, and inverse kinematics, which does the opposite, where a desired end position determines the necessary joint angles working backwards. The VRIF framework through Unity and custom scripts already set up a lot of this tracking for us.
Full body avatar, which does not use Final IK. This actually just uses a built-in Unity IK with some kind of clever code to help keep the body centered under the head so you don't see through your head object. But you can still see it on a camera and in shadows.
So in that case, I'll quickly walk through how we can use inverse kinematics in Unity on a fresh project and a fresh character model to drive limb movements so we can get an idea for the underlying mechanics behind pretty much any modern character-driven game like GTA or Assassin's Creed. So we'll grab a free model from the asset store and bring it into the project, same as we did with the framework. At the end of the day, it's just another package. We'll also bring in Unity's animation rigging package, which will help us streamline the inverse kinematics setup process. For example, we can select our new model and hit Bone Renderer Setup under Animation Rigging, automatically adding visual gizmos for each bone in the model's body. And from here, we can grab bones, rotate, and extend. Of course though, if you are a human being watching this video, you know this kind of thing is not supposed to happen. So with the character selected, let's create a rig setup, again under the new Animation Rigging dropdown, which will configure a rig on the character, our digital skeleton system. A rig and a rig builder, preparing our character for constraint-based control, segueing us into the mechanics of how rigging works. Constraints are used to control an object's transform, position, rotation, and scale based on another object's transform. Specifically for bones, constraints can limit their movement and rotation by aligning them to follow targets, the reference that a constraint follows. Think Puppet on strings but inside Unity. So this walking animation demonstrates these concepts in action quite well. The foot bone of this weird headless square character is constrained to follow the target object, the red and green blocks going back and forth, without which there would be no forward foot motion. This is done using 2-bone IK, a rigging constraint type that automatically positions and rotates two connected bones like an upper and lower leg or upper arm and forearm, and this usually works well enough for realistic animations. Another practical constraint type is a name constraint, used to make a character's head bone automatically rotate to follow a target object, like another character or the player's camera, creating a natural looking head turning movement. So as a child of the rig we created earlier, we'll add the empty IK right hand game object, attach a 2-bone IK component where the tip, our end effector, is the right hand. So we'll lock the inspector to this new game object and click and drag the right hand in from the scene view. And here Unity is smart enough to detect the rest of the connecting bones in this inverse kinematic setup. So we can click the 3 dots in the corner of the component and hit auto setup from tip transform to build the rest of the IK chain. This will also create 2 helpers for us. The target, the red cube you see in the scene view, which defines the position the limb should move towards, and the hint, the red sphere, which is a guide for the bending direction of the joint, like the elbow or knee. So we can take the right hand and command or control select it with the target and hit align transform under animation rigging to line them up, making sure there's no sudden snapping at runtime when the IK constraint activates and the rig begins driving the hand towards the target position. And for the hint, we'll place it roughly where the elbow should point when the arm bends naturally. Usually in this case, it's slightly behind the model's upper arm, which looks about right in the scene view already. So now if we hit play, grab the target, and move it around, you can see wherever the target goes, the hand is constrained to follow, and the chain of connected bones up to the shoulder should track in a realistic way. Position and rotation. That's inverse kinematics for you. The next steps in achieving full body tracking are of course to repeat this for the remaining body parts, including the head and the legs. And now, going back to our VRIF full body demo, things should begin to click a little more. We have the XR full body rig tracking live positional data from our headset and controllers using components we've seen before like the tracked pose driver. And then we have the in-game soldier rig which responds to all that data through inverse kinematics. For example, looking at either of the hands under the player controller, you'll find the IK hand target object, and you'll also see, if we check the soldier rig, the target's transform which the hand is constrained to follow, updated based on the physical device tracking through a custom character IK script, effectively bridging real-world motion with in-game animation. Closely related to full body tracking is the animation system. We cover the full details of the system in the tutorial doc, like the animation state machine in front of you and keyframing, as well as the project specifics of manipulating this avatar into a seated position, like disabling certain locomotion scripts, updating the animation state machine, and of course removing kinematics on the feet, otherwise you'll get this nausea-inducing experience like you're on a sea cruise in a dream and the captain is playing with inverted controls. I mean seriously though, nobody uses that, right? Regardless, it's certainly an interesting process, dealing with animation, a core mechanic of game development, but instead I want to dive into something we've not touched too much on yet, which is creating the game world and seeing how we can develop a truly immersive experience. I'm talking about the environment. We'll structure our entire world hierarchy into 6 categories: the larger world terrain, the city view across the water, the nearby player area, the weather system, audio, and finally the player himself. Let's kick it off with the terrain. Back in our empty full body scene, we'll create a new built-in terrain game object and hit the paint terrain brush option in the inspector. With this brush, Unity makes it really easy to style the terrain however we like. We can choose a brush size, brush shape, and start painting. We can build the terrain up and we can also flatten it down. If we clear up the other areas of the environment in the final project, we'll see the curved riverbed is implemented using the same terrain painting technique. So the way we're gonna do this is by raising the entire terrain in one shot and lowering out the y-axis for where the river will flow opposite to the seated player. For the horizon in the distance, we can easily add neighboring terrains too, filling out the player's view of the background. For the ground the player is seated on, we'll need a bit more precision and a sharper edge. For that, we'll create a poly shape using Unity's Pro Builder package. After installing it from the package manager, we'll get the option in the scene view toolbar to create a shape. Dot to dot, we'll build out this curved shape, matching the opposite terrain and the shape in the snowy meme image. It's a bit of an arduous process, adding all these points and making sure the curve is smooth by entering the game view for the player's perspective, but it's simple to use and gets the job done. To emulate the snow-covered floor, I cycled through a bunch of materials from the asset store and landed on this grass package. I'll be using it for pretty much everything: the terrain, poly shapes, and even the benches and bench handles. To go from grass to snow, I'll create a new material in the project window and add the grass 01 AO PNG as the albedo texture. It's a clever little trick actually. Basically, the AO grass image, the ambient occlusion map, is a grayscale texture showing how much ambient light reaches each pixel, meaning how much of the surrounding light manages to hit and reflect off that surface. White meaning exposed and dark meaning crevices. The albedo of the material basically means the color texture, so by using the AO map, we're creating a desaturated, colorless look where bright areas stay white like frosted snow and darker crevices stay shaded, giving us the illusion of a snow material. So if we apply this to the poly shape, for example, you'll get the idea. We can also play around with the tiling and the brightness to fine-tune the look to be as natural as possible. Since each terrain, poly shape, and snow-covered object has different dimensions, it's a bit of a trial and error process, but it's a lot more important for objects closer to the camera. The terrains further away are less critical. And since we'll be throwing in a few more benches of identical dimensions to clone the meme, we can create a new material to lock in the tiling and call it something like wooden snow, and another with slightly different properties like a lower brightness called metal snow for the bench's armrests. We're on the terrain still, but the nearby player area also uses a lot lot of these snow-covered poly shapes, so we'll throw these in now. Although, due to the curse of perfectionism, I noticed these raised edges didn't match up to the meme quite so well. So here we can create and apply another darkened version of the snow material, again with adjusted tiling compared to the upward-facing surface. Next, we'll bring in this water shader from the Assets Store. A shader is a program that tells the GPU how to render the appearance of a material by controlling its own texture and property data based on external lighting, surrounding objects, the camera view, and other visual influences. So we'll bring in a prefab from the package that uses the water shader, expand it out to fill just under the terrain's top level surface, increase the scale, and tweak the saturation, contrast, and other color properties to match the meme. And now it's time to breathe some life into the world. So we'll bring in some low poly trees and bushes from the Asset Store. Poly refers to polygon, a flat surface, like a triangle, pieced together to build 3D models. Low poly models are great, since they reduce computational load, preventing the game from lagging under the stress of all the rendering. So back on our terrain, we can select the Paint Trees option, add the different trees and bushes we brought in, and get to painting. We can even play around with the brush size and density to easily control the look and feel of the forestry. After cosplaying Bob Ross,
hello, I'm Bob Ross,
we can cleverly block off the emptiness and end of our city skyline from the boundless emptiness that exists beyond. And that's pretty much the larger terrain covered. We'll skip over the city section, but in short, we bring in a massive city asset pack, take a complete city from a demo scene, and spend a good few hours removing a bunch of useless assets, unseeable by the player to reduce the load, and spend some more time positioning everything, jumping back and forth between the player's in-game perspective and the editor to get things looking just right. And well, eventually, that will give us a city skyline across the river that doesn't turn my GPU into a fireplace. Now onto the player and nearby player area. We've already created a few of these poly shapes, so we'll add in some bins and dot in some more benches to match up with the original image. We'll also throw in a few lampposts. Again, we're trying to keep as true as possible, finding single branch lampposts for the front and double branch for the back. As you can see, the lamppost can emit light without a light component attached. It does this by using an emissive material with real-time global illumination. Simply put, this means the material itself glows. A regular material but with emission enabled, and Unity uses that glow to simulate light bouncing off nearby surfaces, creating the illusion of real lighting. We'll also need to throw in these dead trees here with the support stands. For the stands, we'll use regular 3D cube objects and apply a bark material for the woody effect. Copy and paste a few of those, play with the positioning, and we have tree support stands. The trees themselves were a bit harder to create. I found something similar in the Asset Store, but as you can see, the original prefab is a lot chunkier and a lot taller, so we'll have to play around with the transform properties, particularly the XYZ scale, to match it up to the meme, using different tree prefabs from the package and rotating them about. You'll notice in the inspector panel for these trees this weird colorful LOD scale. LOD stands for level of detail. It's a system for reducing GPU load by swapping out high detailed game objects for simpler ones as the distance from the camera increases, balancing performance and graphics. If we take ourselves to the player, keeping your eye on the LOD scale, you can see that as we select dry trees further and further away, the increased distance from the camera automatically swaps in lower detail models. At the end of the scale, the maximum distance threshold, the tree is culled, meaning it's no longer rendered at all. We can also open prefabs in isolation for a closer look. In prefab mode, we can see the different models at each level of distance. We can see the threshold distance, as well as how many polygons or triangles each model contains. Fewer polygons and a simplified geometry as the LOD increases means a reduced computational load. Other methods to optimize performance include simpler textures or certain shader changes. So we'll also add a few more of these dry trees in the player backdrop, paint some more green trees and bushes, and add a hedge to match the image and act as another barrier to the endless Unity universe. Alongside that, we'll add a similar environment on the opposite side of the image, with this truck, which I think is a nice addition, adding some mystery and story to the experience of how our character arrived on this bench. Speaking of which, you may have noticed our player here and the bench are covered in blood. Another addition I thought might add some story benefiting the meme's iridescence. These are just blood decals. A decal is an overlay projected onto a surface adding visual detail like graffiti, dirt, or structural damage, a material layered layered on top of another. We can simply take the decal and slap it onto the avatar's vest object, layering it on top and doing the same for his pants and for the bench. And well, that's pretty much the player and nearby player area covered in terms of environment, and 4 of the 6 world building categories complete. Let's up the immersion one more level and introduce some weather into our project. We'll start with the sky background before moving on to the dynamic elements like the snow and fog. I quickly learned how we add a sky in the game after my very first attempt at recreating the meme VR world that ended like this.
Why isn't it possible?
It's just not.
Why not, you stupid?
A skybox is what the background is called in Unity, a panoramic sphere or cube map material projected onto a sphere or cube to create the illusion of a horizon. If we head over to Window, Rendering and Lighting, we'll get this settings menu full of options for controlling light in our scene, where under the Environment tab we can set a skybox. First, I tried this sky background from Counter-Strike, which would have been great, but it didn't quite work. I guess like we said, the image needs to be made with Unity's skybox formatting in mind, like a panoramic wrapped image or a 6-sided cube map. So I found a bunch of skybox materials built specifically for Unity, on the asset store of course, and this dark storm one worked great. Next up, we have 2 much more dynamic weather elements, snow and fog. We'll make both using Unity's particle system, another built-in system like the input, physics and animation system, with the aim of creating fluid effects that are difficult to develop using sprites or models. We're talking smoke, rain, liquid, fire, magic, even galaxies, and of course snow and fog too. Let's start with snow. We'll create a new particle system under effect in the hierarchy, and immediately you can see it in action. Make sure looping is on as well as pre-warm, which starts the effect when the project begins as though it's already been running. We'll place the particle object above the player and set emissions, which is the rate of particles over time, to a value that makes sense with the dimensions and desired effect. 500 in this case will work fine. We'll set the start size of each particle to a random value between 0.05 and 0.2, giving some natural randomness to the snow and more realistic immersion. To double down on this realism, we'll also set the velocity over lifetime as a random between 2 constants. Setting 2 negative y values reverses the particle movement, simulating a downwards backward vertical drift of the snow, while the x and z values add a subtle horizontal drift, making it seem like the snow is being pushed by the wind. So it's looking okay, but you can see the snow snaps out of existence when it reaches the ground. This kinda kills the realistic feel. So along with the velocity over lifetime, we want to configure the color over lifetime, blending both color and transparency to make the particles fade in and out. We'll also configure the size over lifetime, which will plot on a curve, a steep rise that quickly scales the particles to full size, holds it for most its lifetime, and shrinks the particle to fade out amongst the snowy ground. If we change the shape of the particle object and make sure it aligns with the ground cleanly, we'll get a natural appearance of the snow in and out, rather than seeing the particles pop suddenly out of existence as they meet the ground. And we can also play with the max particles to get more of a blizzard going. Plus, for the final cherry on top, we'll add some noise to the particle movement. The higher the strength, the more erratic the random turbulence to the particle's path. For example, a value of 10 here could simulate something like a group of flies. We'll keep it quite low however, 0.1, just for that final touch of realism. And that's our beautiful snow. At this point though, I couldn't quite put my finger on it, but the ambience of the scene was missing something. It didn't hit that ethereal, masculine urge to bleed out here just yet. And that's when I remembered one of the most legendary games to ever exist, Silent Hill on PlayStation 1. It was fog we were missing to achieve the perfect ambience. I won't go through the fog setup in the video, it's a little more complex than snow since we're using an image instead of built-in particle shapes and making it 3D to add the depth we need. However, we're working with the same particle system, and so the principles remain largely the same, and you can instantly see the difference it makes to the ambience. I'm suddenly now getting the masculine urge to bleed out right here. Although there is just one more thing. We need an epic soundtrack. Boromir had his own score made by Howard Shore, Officer K had Hans Zimmer, and Jon Snow had Ramin Djawadi. Don't worry though, our VR character has Stony Composer. So the first thing I'm going to do is whip out my keyboard and start playing a sad melody. We'll record this in FL Studio and throw in a bunch of heart-wrenching voicemails and an ambient sound to fill the empty space. Export this and we have an MP3 file ready for Unity, although I recognize some people may just prefer the sound of the raw environment.
I'm happy here.
So we'll grab this 10 minutes of WinSounds video, we'll convert it to MP3 using FFmpeg in the terminal, and now we have 2 tracks. We just need a way to switch between them both. Back in Unity, we'll open the Input Actions editor and select the action map for the XR right hand, and we'll add a new action named Switch Audio. We'll add a binding to the primary button which maps to the A button on the MetaQuest right hand controller. We'll also add a binding to the spacebar so we can test out the feature while developing in play mode. Then over in the hierarchy, we'll create a parent audio game object with 2 audio source child objects. These will be the Windy Blizzard sound and our composition. On the parent, we'll attach a custom script named Audio Switcher, passing in the 2 audio sources we just created, as well as the action that triggers the switch between the 2. The script is pretty easy to follow and looks like this. We have a few public variables for the audio sources and a reference to the input action that triggers the audio switch. As we've seen, these values are passed in from the Unity editor. We also utilize inherited methods from the monobehavior class we saw before, like start, where we immediately begin playing audio source 1, on enable, where we subscribe to the input action's performed event, assigning our onSwitch music function as the callback. This in turn calls toggle music, responsible for flipping the playback between the 2 sources with some simple logic. And finally, an onDisable function to unsubscribe from the input event. Finally, we can build the app and port it over to our headset. And that's how we build a whole new world. Weather, buildings, trees, water, sound, sky, a place to sit, and a body to experience it all. We just need to learn a bit of Unity, some C#, rigging, animation, physics, input and movement, lighting and environment design, and then finally we can see how it really feels to slowly bleed out here.
Cute. You sound so formal. I never really realized that until now, but I miss you.
This final project is all about cybersecurity and how attackers target passwords, bank details, session tokens, and more, all through a simple free Wi-Fi access point. You see, you may not have noticed it, but every time you connect to an open Wi-Fi point, whether you're in a cute coffee shop working, in a hotel, an airport, library, or restaurant, you're exposing yourself to Greg in the corner, sipping the same venti iced white mocha with sweet cream foam and 3 caramel shots, except while you're procrastinating via doom scroll, Greg is seeing your every move. This is bad. Greg will go to prison. Do not copy Greg. For those interested in cybersecurity and defending against attacks, we will understand how these exploits happen and build a more secure networking awareness. For those looking to explore more, there is material on the Patreon. And to be clear, there is no instructional misuse of any kind, education and defense only. So it goes without saying, but I must say it, unauthorized use of this knowledge for malicious purposes is very unethical and very illegal. So please don't end up behind bars on my account. I will not be there to save you. And that's all 10 projects. If you made it this far, whether it took you a day, a week, a month, or even a year, it tells me 2 things. 1, you have the sheer determination and grit to stick through difficult things to the end. Whether you're just trying to pass software interviews or build cool things, it's a rare ability and a very good sign of someone who's destined to go far. And 2, you can now undoubtedly call yourself a real engineer. Programming, clean code, CPU execution, architecture design, build systems, processes and threads, networks, the internet, OSI, cybersecurity, game development, virtual reality, embedded systems, physical security, web apps, databases, CLI tools, reverse engineering, web scraping, neural networks, math, image and video processing, blockchain, cryptography, APIs, mobile desktop cloud. We've covered it all here. And honestly, I would be pretty proud of myself for making the effort to learn and get better. What's next? next? Well, that's up to you. Pick one of the projects and go through the code, learn from it, improve it and add features, or build your own version. Remember, you have to do the real thing. And if you're one of the rare few who have completed the projects and made it to the end of this journey, try building something new. Ultimately, the decision is yours. Good luck, because this is only the beginning.